Vintage, eBooks, Earth, and Intimate History. Richard Fortey. Richard Fortey is a senior paleontologist at the Natural History Museum in London. Life was shortlisted for the Rhône-Poulenc Prize in 1998. Trilobite was shortlisted for the Samuel Johnson Prize in 2001, and The Hidden Landscape was awarded the Natural World Book of the Year in 1993. He was awarded the Lewis Thomas Prize for Science Writing by Rockefeller University in 2004. He was Collier Professor for the Public Understanding of Science at the University of Bristol in 2002 and is now a Fellow of the Royal Society. He lives in London. Acknowledgements. It would have been impossible to write this book had I not been awarded the Collier Chair in the Public Understanding of Science and Technology at the University of Bristol for 2002. I am most grateful to the Institute of Advanced Studies, University of Bristol, and particularly Professor Bernard Silverman for granting me time in a quiet attic to escape the hassles of my normal life. Corrine Taylor, secretary to the Institute, was helpful in countless small ways which made my stay in Bristol a pleasure. I thank Paul Henderson of the Natural History Museum in London for facilitating my sabbatical leave at Bristol. While researching the book, I was compelled to explore parts of the geological column that are not my usual habitat and to extend my expertise into new fields. I profited enormously from the generosity of several geologists who guided me over territory well known to them, but novel to me. Jeff Milnes and his daughter Ellen were charming guides around the Eastern Alps and patiently tolerated my naive questions. Graham Park took me around the Northwest Highlands at a time of the year when most sensible people, even Scottish people, are sat round the fire with a hot toddy. Jeff and Graham also revised the appropriate parts of my manuscript and corrected mistakes and misapprehensions. I need hardly add that any infelicities or inaccuracies that remain are entirely the responsibility of the writer. Several years ago, Dr. Ajit Varkar of Pune arranged my trip to the Deccan Traps in northwestern India, negotiating with drivers and guides alike. I could not have completed this excursion without his help. Paul and Jody Moore provided unstinting hospitality in Hawaii for me and my family, and were the best possible company in the tropical evenings. I hope they got the sand out of the carpet. I cannot thank them enough. Sam Gon helped me understand aspects of Hawaiian culture. Several colleagues generously gave me advice in return for no more than a free lunch. I may still owe one or two. I particularly thank Claudio Vitafinzi and David Price of University College London for advice on the Bay of Naples and the middle of the earth, respectively. Bernard Wood of the University of Bristol spent an afternoon showing me how rock samples can be crushed so hard as to change their character, which was invaluable for my chapter, Deep Things. I also thank John Dewey, Tony Harris, David G., Bob Symes, Joe Ken, and my old Newfoundland friends for advice of one kind or another. Adrian Rushton and Derek Siviter provided moral support in the pub at times of crisis. I am particularly indebted to Robin Cox, John Cope, and Heather Godwin, who read through the first version of the book and made several suggestions for its improvement. Heather has always had a crucial role in my writing career as an infallible arbiter of taste and exciser of bad jokes. Arabella Pike at HarperCollins has proved again an enthusiastic and supportive editor, and her organizational skills ensured that the whole work came together. I sincerely thank my wife, Jackie, for once again tolerating the writer at work, and more specifically, for organizing several of the field trips which comprised the core of the book. Jackie and my daughter, Rebecca, did much of the picture research for the color plates. Robert Francis provided me with many excellent photographs, which greatly enhanced the attractiveness of my natural history of the earth. I thank Ray Burroughs for his skillful drawings, James Secord, Ted Neal, John Cope, David G., John Morby, Jerry Ortner, Graham Park, and Jeff Milnes also provided illustrations, for which I am much indebted. Preface. For some years I have been thinking about how best to describe the way in which plate tectonics has changed our perception of the Earth. The world is so vast and so various that it is evidently impossible to encompass it all within one book. Yet geology underlies everything. It founds the landscape dictates. The agriculture determines the character of villages. Geology acts as a kind of collective unconscious for the world, a deep control beneath the oceans and continents. For the general reader, the most compelling part of geological enlightenment is discovering what geology does, how it interacts with natural history, or the story of our own culture. Most of us engage with the landscape at this intimate level. Many scientists, by contrast, are propelled by the search for the inclusive model, a general theory that will change the perception of the workings of the world. In most scientific papers, the intimacies of plants or places are hardly given a second glance. Plate tectonics has transformed the way we understand the landscape, for the world alters at the bidding of the plates, but much of the transformation has been expressed in the cool prose of the scientific treatise. The problem is how we can marry these two contrasting modes of perception: the intelligent naturalist's sensitive view of the details of the land with the geologist's abstract models of its genesis and transformation. My solution has been to visit particular places, to explore their natural and human history in an intimate way, thence to move to the deeper motor of the earth to show how the lie of the land responds to a deeper beat, a slow and fundamental pulse. I have chosen my examples with some care, for they are all places that have figured in unscrambling this complex and richly patterned planet of ours. I have visited them all so that the reader will also have this particular guide's reactions to the sights, sounds, smells, and ambience of the critical localities. At the same time, I have endeavored to show how knowledge of the deeper tectonic reality has changed over the last century or so. Great minds have pondered the shape of the world and have purveyed theories of everything that have come and gone. Many past theories have been founded on good reasoning for their time and place, and it would be a complacent scientist today who would claim that present knowledge is as far as it goes. Understanding advances by building upon and criticizing the work of those who went before. It is a messy and complicated business in which the human heart has as much a part to play as human intellect. This, too, is an ingredient in my story. The most difficult decisions I faced were not what to include, but what to leave out. I am acutely aware that there are areas of science that are merely sketched herein, any one of which would merit a book of its own. Geochemical cycles and their role in Earth systems are a case in point. The antecedent of extraterrestrial events in our history is another fascinating field in which many recent advances have been made. The omission of such things in the interest of a coherent narrative was a painful necessity. What my story lacks in omniscience, I hope it makes up for in coherence and accessibility. Chapter 1. Up and Down. Vesuvius is more of a continuous presence. The ground rises gently towards its brown summit. New buildings cling on to the side of the mountain, even high up among the low trees and broom bushes that clothe its flanks. The buildings are indistinct, however, hidden by a creamy yellow haze of petrochemical smog spreading outwards from the frantic center of Naples. Towards a mountainside, you pass a road sign to Pompeii, but from the road, there is little to distinguish this suburb from any other, for all its fame. When the road rises into the hills that abut the southern margin of the Bay of Naples, the urban sprawl begins to thin out. The orange groves are more orderly, with the trees neatly planted in rows inside cages made of makeshift wooden struts draped over the top with nets. The slopes become much steeper than on the volcanic flanks close terraces piled one upon the other, each banked up with a wall of pale limestone blocks. Medium-sized trees, with small gray-green leaves which appear almost silvery in the afternoon, light cling to the most precipitous terraces. These are olive trees, the definitive Mediterranean survivors, oil producers and suppliers of piquant fruit. Their deep roots can seek out the narrowest cracks. They relish limestone soils, however poor they are in comparison with volcanic loam. The villages in this part of the bay are, as you would expect of regular tourist Italy, with piazzas and ristorante pizzerias, and youths with slick hairstyles on the lookout for a fast buck. Even this long before the summer season there is opportunity for a smooth operator. You find yourself agreeing to hire a cab for a day for €200 to hug the congested roads, when you could travel faster on the excellent Circumvesuvian railway for a tiny fraction of the price. Somehow, you, the visitor, have become the rich volcanic soil primed to yield a good harvest. Near the tip of the southern peninsula, Sorrento commands a wonderful prospect of Mount Vesuvius across the entire Bay of Naples. From this steep-sided town, Vesuvius looks almost a perfect, gentle-sided cone. It could be a domestic version of Mount Fuji, the revered volcanic mountain in Japan. It can appear blue or gray, or occasionally stand revealed in its true brown colors. On clear days, Vesuvius is starkly outlined against a bright sky, a dark, heavy, almost oppressive presence. Or on a misty morning its conical summit can rise above a mere sketch or impression of the lower slopes, which are obscured in vapor, as if it were cut off from the world to make a house for the gods alone. At night, ranks of lights along Neapolitan roads twinkle incessantly. Vesuvius is often no more than a dark shape against a paler but still Prussian blue sky. The lights might persuade you that the mountain was still in the process of eruption, with points of white illumination tracking lava flows running down the hillsides. From Sorrento, you can make of Vesuvius what you will, for within a day it will have remade itself. The Bay of Naples is where the science of geology started. The description of the eruption of Vesuvius and the destruction of Pompeii in AD 79 by Pliny the Younger is probably the first clear and objective description of a geological phenomenon. No dragons were invoked, no clashes between the Titans and the gods. Pliny provided observation, not speculation. Not quite 2 millennia later, in 1830, Charles Lyell was to use an illustration of columns from the so-called Temple of Serapis at Pozzuoli, north of Naples, as the frontispiece to volume one of the most seminal work in geology as Principles of Geology. This book influenced the young Charles Darwin more than any other source in his formulation of evolutionary theory. So you could say that the Bay of Naples had its part to play, too, in the most important biological revolution. Everybody who was anybody in the 18th and 19th centuries visited the bay and marveled at its natural and archaeological phenomena. For geology, a latecomer to the pantheon of sciences, the area is the nearest thing to holy ground that there is. If you were going to choose anywhere to retrace the growth in our understanding about how the earth is constructed, what better place to begin? Where else more appropriate to explain first principles? The long intellectual journey that eventually led to plate tectonics started in this bite out of the western shin of Italy's boot-shaped profile. A voyage around this particular bay is a pilgrimage to the foundations of comprehension about our planet. Everything about Sorrento is rooted in the geology. The town itself is in a broad valley surrounded by limestone ranges, which flash white bluffs on the hillsides and reach the sea in nearly vertical cliffs, an incitement to dizziness for those brave enough to look straight down from the top. Seen from a distance, The roads that wind up the sides of the hills look like folded tagliatelle. Stacked blocks of the same limestone are used in the walls that underpin the terraces supporting the olive groves. In special places there are springs that spurt out fresh, cool water from underground caverns. These sources are often flanked by niches containing the statue of a saint or of the Virgin. Water is not taken for granted in these parts. There are deep ravines through the limestone hills, probably marking where caves have collapsed. The country back in the Bay of Naples is known as Campania, and the same name, Campanian, is applied to a subdivision of geological time belonging to the Cretaceous period. If you look carefully on some of the weathered surfaces of the limestones, you will see the remains of seashells that were alive in the age of the dinosaurs. I saw some obvious clams and sea urchins belonging to extinct species emerging from the cliffs as if they were on a bar leaf. A paleontologist can identify the individual fossil species and use them to calibrate the age of the rocks, since the succession of species is a measure of geological time. The implication is clear enough. In Cretaceous times, all these hilly regions were beneath a shallow, warm sea. Limy muds accumulated there as sediments and entombed the remains of the animals living on the sea floor. Time and burial hardened the muds into the tough limestones we see today. They are sedimentary rocks, subsequently uplifted to become land. Earth movements then tilted them, but this is to anticipate. What one can say is that the character of the limestone hills is a product of an ancient sea. The massive limestones continue westwards on to the island of Capri, which is a 20-minute ferry ride from Sorrento and bounds the southern edge of the Bay of Naples. The island rises sheer from the sea, circumscribed by steep limestone cliffs, and your first thought is how could it support the smallest village, let alone a town? The town of Capri lies at the top of a vertiginous funicular railway running from the harbor. The buildings are ancient and quaint and, naturally enough, built of the local stone. The blocks themselves are often concealed under stucco. There's a fine medieval charter house where the pale limestone is put to good effect in columns supporting cloisters. Almost everything else is fabricated of limestone: walls, floors, piazzas. In the bright Mediterranean light, there is an overwhelming sense of whiteness. Some of the villas glimpsed on the hillside have the appearance of frosted cakes tucked under umbrella pines. Only dark basalt must have been imported from Vesuvius to make the surfaces of the streets. This volcanic rock is less liable to shatter than limestone. It is not difficult to imagine the racket that iron-rimmed wheels made as they clattered over these roughly matched, large blocks. On the inner side of the island, there are truly astonishing vertical limestone cliffs dropping hundreds of meters to the sea. The Roman Emperor Tiberius spent his declining years in a palace on the island, the ruins of which endure. According to the prurient accounts of his chronicler Suetonius, he indulged every kind of sexual perversion in a life of epicene self-gratification. Small boys were favored. Those who displeased him were liable to be thrown off the monstrous cliffs. There is a subtle undercurrent in the Capri's atmosphere that hints at such darker things. Just offshore there are two enormous and forbidding sea stacks, masses of limestone isolated from the main cliff by the relentless erosion of the sea. According to Norman Douglas, this was the abode of the sirens, whose alluring and fatal song Odysseus was able to resist only by being strapped to the mast of his vessel, while his muffled crew rowed onwards to safety. Capri makes you wonder whether an idyllic hilltop haven might eventually also deprave and destroy one of the grandest villas, now a hotel, overlooking the fearsome cliffs, was built by the Krups dynasty, once the armorers of German ambitions. Unexpectedly, the builder apparently immersed himself in studying the growth of lampreys, a primitive and parasitic fish. On this island, there is a seamless continuity with the past. With Hellenic myth and Roman decadence and medieval devotion, the island gardens have seen the ages come and go, perched high upon the hardened sediments of a sea far more ancient than human frailty. There is something different about the cliffs behind the harbor in the middle of Sorrento. From afar they have a grayish cast, a dull uniformity, lacking all the brilliance of limestone. The streets career downwards towards the sea, below the central piazza, following a steep-sided valley. Now you can see the rock in the valley sides. It is brownish, like spice cake, and displays little obvious structure. Look closely, and you see that embedded within it, like dates in a home bake, there are darker patches. Some are little more than wisps, others are larger, angular pieces of another rock, here nearly black, there umber brown, some including little bubbles. Then you notice that the same rock has been recruited by the local builders to construct the high walls that line the steeply sloping path, comprising blocks a few tens of centimeters across, neatly cut and used like bricks. Clearly, this rock is softer than the rough limestones that bolster the hilly vineyards and terraces. Then you notice that the same stone has been used to construct the older buildings. Down by the port there are shops and cafes painted jolly ochre and sienna, but where the stucco has peeled or where warehouses have simply been left undecorated, the same rock is revealed as having been used for their construction. Much of the town has grown from the identical rock that forms the steep cliffs backing the harbor. This rock is called the Campanian ignimbrite. Its origin was a catastrophe that happened 35,000 years ago. A gigantic volcanic explosion threw out at least 100 cubic kilometers of pumice and ash. The evidence still covers an area of more than 30,000 square kilometers around the Bay of Naples, extending from Roccamonfina in the north to Salerno in the south. The violence of this eruption would make the event that buried Pompeii seem like a small afterthought. An explosion of steam and gluey lava blew out a great hole in the earth at the edge of the Tyrrhenian Sea, not so much a bite out of Italy's profile as a huge punch. A vast cloud of incandescent material buoyed up with gas flowed like a fiery tidal wave across the limestone terrain. Lumps of volcanic rock were carried along willy-nilly in the mayhem. Destruction of vegetation was complete. When the cloud settled, in many places it was hot, enough to fuse solid. The wispy remains of volcanic fragments testified to this. Welding asterisk, there were almost certainly Paleolithic human witnesses to this destruction, who must have thought the gods had gone berserk. The legacy of the Earth's ferocity is this apparently mundane rock that looks like cake. The angular fragments of rock within can now be seen for what they are, pieces of a destroyed volcano. It is ironic that this destruction has now been reversed into constructing buildings that are safe as houses. Naturally, nothing is safe in this uncertain world. Looking down from the limestone hills, you can imagine the hot, devastating clouds settling over where Limoncello is now. Brood and pizzas are spun, dumping down on the low ground as a thick, lethal blanket. These kinds of rocks were deposited from proclastic surges. Another eruption about 23,000 years later was marginally less devastating and did not spread so widely. It produced a different deposit known as the Tufo Galliano Napoletano, the Neapolitan yellow tuff. Rather than the color of cake, it is the color of Dijon mustard. Once you can recognize it, you spot blocks of it in many walls and buildings around Naples itself. It is almost reminiscent of the London stock bricks that make the Georgian parts of the English capital so appealing. It is there in the walls of Roman remains. Most experts believe that the volcanoes that remain to this day in the Campi Flegrei are aligned around the edge of the massive hole, or caldera, left behind as the legacy of the second huge eruption. The Bay of Naples itself hides most of it. It may yet blow again. It must be appropriate now to visit Mount Vesuvius. It is 1,281 meters high. Not a great peak, but grand enough. Strictly speaking, only the cone itself should be called Vesuvius. The wider region, including older volcanic remnants, should be called Somma Vesuvius. To reach the mountain, go to Herculaneum Station and catch the bus waiting outside in the bustling suburb. The route climbs upwards through improbably narrow streets and then out into fields planted with almonds and vines. The mountain produces a wine called Lacrimae Christi, the Tears of Christ, as evocative a name as you could wish for an indifferent Rosso. Now you can see close up the random assortment of houses that were visible only as flashes of light from the other side of the bay. They seem perilously close to the volcanic cone and, unplanned, as if dropped haphazardly from the sky. Higher still there is dense scrub, and then looming above you, the cone itself. The bus disgorges its passengers, who must then climb to the summit along a relentless upward trail. You are following in famous footsteps for the poets Goethe and Shelley were here before you. Nor are you ever alone. The view provides an irresistible photo opportunity for tourists of all nationalities. The conurbation of Naples stretches away below, as insubstantial as postage stamps pasted on. The landscape, the dominant color is a warm brown-black. Nobody could pretend that a huge slope of clinker is aesthetically pleasing. The waist of the mountain has a curiously industrial feel, like slag from a smelter. It is easy to understand. The classical notion of Vulcan's forges working away in the Earth's interior. An excellent guidebook by Doctors Kilburn and Maguire of University College, London, reveals that these unpromising pieces of debris are scoria and lithic fragments of the March 1944 eruption. Looking down, you can make out the edges of these latest flows in Vesuvius' long history extending beyond the base of the cone itself, like chocolate sauce sliding off a steamed pudding. By the path side, there are occasional large boulders that show black crystals the size of a fingernail. These are pyroxene minerals that had time to crystallize. Out deep within the chamber of liquid rock or magma beneath the volcano, like everything else around, these rocks are igneous in origin, formed in fire, cooled from melt derived from the Earth's depths. The crater itself is the kind of gaping hole that induces despair in those suffering from vertigo. It is 500 meters across and 300 meters deep. From the far side of the rim path, you can just make out the amphitheater at Pompeii, with the misty blue of the Bay of Naples beyond. It seems entirely plausible that destruction could be meted out at a distance by suitably violent explosions. The crater sides are sheer. Wisps of steam still arise from one side, like smoke from a poorly extinguished cigarette. Looking across the crater, you can readily see that it is made of piled layers of lava meters thick. You can also make out where flowing lava was replaced by explosive pyroclastic deposits, which are crumbly and easily eroded. Here is evidence for the origin of the kind of lethal clouds that wiped out Roman Herculaneum in the AD 79 eruption. The crater is not stable. Listen, there is a continuous tinkling, like ice in a glass, as pebbles fall from the sides into the interior. The volcano is temporarily quiescent, but there are many descriptions of it while awake. Here is a little of what the philosopher Bishop Berkeley had to say about it in 1717. I saw a vast aperture full of smoke, which hindered me from seeing its depth and figure. I heard within that horrid gulf certain extraordinary sounds, which seemed to proceed from the bowels of the mountain, a sort of murmuring, sighing, dashing sound, and between whiles a noise like that of thunder or cannon, with a clattering like that of tiles falling from the tops of houses into the streets. Sometimes, as the wind changed, the smoke grew thinner, discovering a very ruddy flame and the circumference of the crater, streaked with red and several shades of yellow. Nowadays, handwritten labels creak in the wind. On the top of the cone you can make out a solar-powered global positioning system. So often in Italy, there is this odd mixture of the improvised with the latest technology. Vesuvius is an irritable mountain. It has been erupting for 25,000 years or so. It will do so again. It is a classic in geological literature because several of its eruptions have been accurately described over 2,000 years. It also demonstrates many kinds of different volcanic activity, from sluggish flows that slowly and inexorably eat up landscape and houses through ashfalls that suffocate, to pyroclastic flows and surges that run faster than a racing car and engulf the plains in heat and terror. It is a volcanological casebook. After the AD 79 debacle, which killed 2,000 people and buried Herculaneum and Pompeii, there was a great eruption that began in the morning of December 1631. Within a day, ash from Naples had reached Istanbul, more than 1,000 kilometers distant. This eruption killed almost twice as many people as had died at the time of the Roman Empire. The rich volcanic soil had once more encouraged the growth of a prosperous people who had spread over vulnerable areas. Massive pyroclastic flows took their toll. So did the engulfing slurries of mud and ash that flowed downhill when heavy rains blend with volcanic outpourings. Ironically, the particles thrown up by a major event served to seed rain clouds in the atmosphere. Thus, in this tragedy, the four ancient elements, earth, air, fire, and water, conspired towards a common deadly destruction. Naples itself, however, was spared. There were many subsequent minor eruptions, usually about 11 years apart, all of which avoided it. An eruption is now overdue and might well be a big one. The latest 1944 eruption was studied in detail. Something like 37 million cubic meters of magma were expelled within a few days in March of that year. Much was released in the form of ash and bombs, black masses often shaped like horns or twisted loaves. There were several eruptive phases, separated by periods of quiescence, when the crater collapsed temporarily to block the throat of the vent. The almond blossoms everywhere shriveled on the branch. The villages of Massa and San Sebastiano were destroyed by slow-moving lava flows. The Times of London correspondent eloquently described the process. The progress of destruction is almost maddeningly slow. There is nothing about it like the sudden wrath of devastation by bombing. The lava hit the first houses in San Sebastiano at about 2:30 a.m., but by dawn it still had not crossed the main street only 200 yards away, but was nosing its way through the vines and crushing down the small outhouses more slowly than a steam roller. For a while it seemed as if it would engulf the houses as they stood. But then, as the weight grew, a crack would appear in the wall. As it slowly widened, first one wall would fall out, and then the whole house would collapse in a cloud of rubble over which the mass would gradually creep, swallowing up the debris with it. Masses of steam of slightly darker quality rose as cellars full of casks of wine exploded. Over all one heard a steady cracking as the monster consumed hors d'oeuvre of vine stalks, olive trees, and piles of faggots stored in backyards. If it had been a proclastic surge, the whole thing would have been over in a second. A geologist amongst the crowds at Pompeii would probably be there to observe the effects of an ash fall that destroyed a whole city, as much as to wonder at the level of luxury enjoyed by the Roman elite. Nonetheless, the city's sheer size comes as a surprise. The discouragingly large crowds at the entrance soon disperse, and you are left to pick around at your leisure. Some of the roads allow a clear view of Vesuvius, and it is not so difficult to envisaged a huge shower of hot ash that so effectively entombed this wealthy city for the archaeologists. The warning earthquakes, the great boom of an explosion, the dark clouds shooting into the atmosphere above the looming cone, the sky blotted out, wonderment turning instantly to horror as the fall began. The bodies of the inhabitants were molded by the ashes that covered them. The most pathetic testimonies to the catastrophe are the casts that have been taken from these molds, which are now stored at one end of a vineyard. In particular, a figure half rising from sleep, hardly stirred from private oblivion before returning to it forever, thereby preserving something of the monumentality of a sculpture, but with a vulnerability that is wholly personal. Even the stones have their own story to tell. The streets were shod with pieces of tough basalt fitted together in a coarse jigsaw. There is something peculiarly eloquent about seeing the grooves that generations of cartwheels wore into these roads. They are imprints of time itself upon what is inevitably described in the tourist blurb as a time capsule. The surfaces of the roads are lower than the sidewalks, and the curbs are marked by courses of large basalt blocks. The walls of the houses and shops and temples were often constructed of alternating courses of large blocks of ignimbrite and small sienna-colored Roman bricks. The corners were often entirely of brick, since the larger blocks chipped easily. The architects knew their local geology. In the Villa di Misteri, there was much use made of the tufo galliano, napoletano, often built into a lozenge pattern. Originally, the surfaces along the streets would have been rendered as they are inside the villas. But since cement was originally discovered by the Romans from grinding up tuffs, so even the dressing of the buildings is geological. In the smarter buildings, the walls were painted and ornamented with figures and curlicues. Mosaic floors consisted of patterned tesserae, the common black and white ones being made of marble and basalt. Discovery of pattern books has shown that these floors could be ordered by the yard. There is a section of the hypocaust, or plumbing, on display that shows the use of lead pipes. Who knows if some of that lead could not have come from as far away as Britain, where the geological circumstances are just right for lead ores? In short, Pompeii grew from the geology, just as it was eventually consumed by it. Herculaneum was destroyed by pyroclastic flows. The inhabitants had time to attempt to flee to sea, but no time to succeed in their flight. For a small tip, a guide will let you see the skeletons of the huddled bodies down by the former harbor. The temperature must have been sufficient to kill instantly, but not to calcine the bones. Why should the outlines of the flesh at Pompeii be more affecting than these horrific accumulations of bones? It must be something to do with gesture, with individuality. All skulls smile alike. Both Pompeii and Herculaneum have geological bones. The fire has done no more than expose them. This is not only true of famous archaeological sites. Whatever the surface decoration, geological truths determine much of the reality and character of cities. The stone that builds them, the height to which towers can rise. This is a subtler connection than that with agriculture. It is more obvious that the dark, rich soils around some of Vesuvius are the product of the weathering of old flows, and that this explains why men and women have always repopulated the area after the latest disaster. If San Gennaro, the patron saint of Naples, looks after us, Deo gratias, we will prosper. The geology, in turn, is often related to tectonic plates, a deeper reality still, arbiter of the shape of the world. It seemed appropriate to pay our respects to S. Gennaro. There is a chapel dedicated to him in the Duomo in Naples. In the 3rd century, the saint was martyred for his Christian beliefs. He was first sentenced to be torn to pieces by animals, but this was commuted to beheading. The decapitation took place At Solfatara north of Naples, where a shrine has been erected, some of the saint's blood was scooped up after the execution. This is still preserved as a precious relic. It supposedly has the extraordinary property of turning back into blood when it is brought out on religious occasions 3 times a year. Thus is Naples' safety guaranteed, or so the Neapolitans believe. The Duomo is reached by walking through narrow streets where squalor and splendor rub shoulders. Dark alleyways draped with washing lines and oozing suspicious liquids are cheek by jowl with churches and courtyards of decayed magnificence. The silence in the Duomo is all the more impressive for the noise and chaos outside. The Saint's Chapel is an ebullient confection of columns and gilt, with masses of marble and serpentine, panels of onyx busts, and paintings. The saint is depicted above the right-hand altar emerging, unscathed from a fiery furnace sanctity, rises above mere volcanics. The 16th century crypt is an extravaganza of marble. The floor is constructed from marble lozenges and triangles of every imaginable hue, yellow and pink, and all manner of mottled and blotched shades, framed in white. The walls have ranks of white marble niches capped by huge marble scallops and flanked by urns and flowers, drapes and putty. The whole is supported by rounded marble columns white, with gentle streaks of gray wilder. Ceiling sports square panels painted with the effigies of saints, angels, and bishops. A pearly marble statue of Cardinal Carrata kneels on the floor facing towards a locked bay containing S. Gennaro's relic. It is like being inside a palace of spun sugar. More mundanely, the crypt serves as a reminder of the third great class of rocks besides those of sedimentary and igneous origin. These are metamorphic rocks. They may have started out as either of the other 2 categories, but have been altered or even completely transformed by heat, pressure, or by any combination of the 2 when caught in the great mill of mountain building within the depths of the earth. Marble is one kind of metamorphic rock and comes in 1,000 shades, although it started out as humble limestone as plain as the cliffs of Capri. Along the Apennine spine of Italy there are many places where heat and pressure have altered limestones in this fashion. Renaissance architects made luscious use of these rocks. They can appear to resemble anything from blue cheese to slices of liver, or they can be pure white, like the Carrara marble favored by great sculptors such as Michelangelo. Naples was just following the fashion. Gennaro's niche is clad in the products of the infernal heat to which he is now impervious. Early visitors to the Roman antiquities of the Bay of Naples were following the tradition of the Grand Tour, a cultural perambulation around Italy made by young gentlemen with pretensions to enlightenment. 18th century, English aristocrats would have been as familiar with the classics, with the writings of Virgil and Horace, as they would have been with the salty, homegrown vigor of Chaucer or the sonnets of Shakespeare. They would have known about the hot springs that supplied the baths in which Roman gentry lounged for the good of their health. They would have been familiar with the ambulatoria along which the pampered rich strolled with their favorite philosophers for the good of their minds. The archaeology of the area was the latest sensation. Sir William Hamilton is known now mostly for his marriage to Lord Nelson's mistress, but he was a considerable archaeologist and antiquarian, and the purchaser of treasures that still grace the collections of the British Museum. He also appreciated the uniqueness of the Neapolitan landscape and strove to make known its volcanic features. While he was British envoy in Naples towards the end of the 18th century, he published a book about the Phlegrean fields, Campi Phlegrii, which well described the area to which he was devoted. Perhaps it is this for which he should be remembered. Certainly, his work was known to the young. Charles Lyell. Lyell had traveled to Italy in 1828 in the company of Sir Roderick Murchison, who was then the most influential British exponent of the young science of geology. If classic areas are made so by the observations of perceptive eyes and measured by the hard currency of influence on subsequent thought, then there is a claim to be made for this modest Roman site in the middle of the town of Pozzuoli, west of Naples, but no plaque records it, no signs direct you to it. You simply come across it as you might a standing stone in England or a roadside shrine in Italy. The Phlegrean Fields. The very name sounds like some version of Arcadia. It is in fact derived from Greek for burning. I had seen Sir William Hamilton's portrayals of the scenery, trees giving on to a rustic scene, the odd peasant going about his business, in the distance some interesting volcanic phenomenon in progress. This was the area of Campania described by the 2nd century historian Florus as the most beautiful region not only in Italy but also in the world. Nothing is sweeter than its climate. To say, everything, spring flowers twice there. Nothing is richer than its soil. Nothing is more hospitable than the sea. Times do change, of course, and the region has been swamped by undistinguished suburbs. But the Campi Flegrei is still the same collection of craters and calderas, separated by volcanic hills. As it was in Florus' time, only the flat bottoms of the former have often been filled in with army barracks or cheap industrial units. The reality of these evocatively named fields are sadly something of a disappointment. Lake Averno was considered to be one of the entrances to the underworld in classical times. In those days, birds roosting around it were wont to fall dead from the trees. From here, Dante was led by Virgil into the Purgatorio. If geology is a true underworld, then Lake Averno seemed to provide a kind of metaphorical entry point to the deep regions that form the subject of this book. Can you imagine anywhere with richer associations? It is an almost perfectly circular crater lake, 3/4 surrounded by steep walls of tuff. When I visited in early spring, it had a slightly sinister character. Plumes of smoke arose, not from volcanic exhalations, but from burning heaps of rubbish left over from the last summer season. A few mean reeds grew from the lake bottom, and bubbles of gas arose and broke the surface methane, I suppose, from the deoxygenated mud. Perhaps, after all, this is a postmodern underworld with existential gloom presiding. There is a geological explanation for this lethal lake. After volcanic eruptions have subsided, invisible eruptions of gas may continue. Carbon dioxide is one of them. It is odorless and heavy, much heavier than air, so it sits around invisibly or flows into pockets and depressions. It induces suffocation until, a century ago, a cave with these properties in another crater in the Campi Flegrei, Astroni, was shown to visitors as a tourist attraction. It was called Grotto del Cane, Cave of the Dog, for reasons which will become apparent. The playwright and jobbing writer Oliver Goldsmith reported in 1774 on this grisly natural phenomenon in an history of the earth and animated nature. This grotto, which has so much employed the attention of travelers, lies within 4 miles of Naples and is situated near a large lake of clear and wholesome water. Nothing can exceed the beauty of the landscape which this lake affords, being surrounded by hills covered with forests of the most beautiful verdure, and the whole bearing a kind of amphitheatrical appearance. However, this region, beautiful as it appears, is almost entirely uninhabited. The few peasants that necessity compels to reside there, looking quite consumptive and ghastly from the poisonous exhalations that arise from the earth. The famous grotto lies on the side of a hill near which place a peasant resides, who keeps a number of dogs for the purpose of showing the experiment to the curious. These poor animals always seem perfectly sensible of the approach of a stranger and endeavor to get out of the way. However, their attempts being perceived, they are taken and brought to the grotto. The noxious effects of which they have so frequently experienced. Upon entering this place, which is a little cave or hole rather, dug into the hill about 8 feet high and 12 feet long, the observer can see no visible mark of its pestilential vapor. Only to about a foot from the bottom, the wall seems to be tinged with a color resembling that which is given by stagnant waters. When the dog, this poor philosophical martyr, as some have called him, is held above this mark, he does not seem to feel the smallest inconvenience. But when his head is thrust down lower, he struggles to get free for a little, but in the space of 4 or 5 minutes, he seems to lose all sensation and is taken out seemingly without life. Being plunged into the neighboring lake, he quickly recovers and is permitted to run home, seemingly without the smallest injury. It is the recovery of the dogs from their ordeal that identifies the gas as carbon dioxide. Goldsmith goes on to say that the vapor is of the humid kind as it extinguishes a torch, an experiment still performed in school laboratories to this day. Had the gas been sulfur dioxide or hydrogen sulfide, the poor dogs would have suffered a rapid and painful death. In 1750, a statue of the god Serapis was excavated from a Roman site at the coastal town of Pozzuoli. Serapis was based ultimately upon the Egyptian god Osiris, but hybridized with Greco-Roman gods to become the basis of a widespread cult in the Mediterranean at the time of the Emperor Hadrian. For more than a century and a half, the impressive archaeological discoveries in Pozzuoli were known as the Temple of Serapis, or the Serapion, under the belief that the statue indicated a sacred function. This is the name that appears in the caption to the illustration that forms the frontispiece of Charles Lyell's Principles of Geology. The image is also engraved on the Lyell medal of the Geological Society of London, so it clearly mattered to his contemporaries. The current perception is that the temple is nothing of the sort, but was in truth a rather opulent marketplace, or macellum, but it is still a geological shrine, an emblem for the coming of age of geology as a science. It is something of a disappointment that it had to be deconsecrated. After all, the temple is a holy place for rationalists, if that is not an oxymoron. At first sight, the Serapion is curiously unimpressive. The old town of Pozzuoli lies on a hill and has been out of bounds since the earthquake crisis of 1982. The site lies near the harbor beyond the hill. A few yards seawards from the ancient mart there is still a market selling oranges and lemons and local fish. Then you see the old marketplace lying beyond a well-shaded square. It lies about 6 meters below the level of the present piazza. It is like looking down into a sports field or a football pitch, a resemblance increased at night when the area is floodlit. The large rectangle is dominated by 3 huge columns, which a notice tells us are 12.5 meters high and composed of a single piece of marble. They must have been expensive items, even at the time the market was built. In front of them there is a raised circle carrying a series of smaller columns that were probably reconstructed relatively recently, whereas the great columns were in place. The circle is constructed of the familiar tuff, underlain by courses of Roman bricks. There are planted palm trees whose trunks supply a kind of biological equivalent to the marble columns. All around the edge of the market square are remains of the stalls of the traders. The monument has none of Pompey's breathtaking qualities, tucked away as it is so matter-of-factly in the middle of Pozzuoli. The casual observer might wonder at its importance. To discover the reason requires closer examination of the great columns. About 4 meters above their pedestals there are what look from a distance to be zones of blackish discoloration, where the marble appears roughened or eroded. The lower parts of the columns are, as Lyell said, smooth and uninjured. Look more closely at the discolored parts of the columns. You can now see that the marble has been perforated and pierced. Identical borings are caused by the marine clams that Lyell knew as lithodomus. They can be found around the Bay of Naples today. The great Swedish biologist Linnaeus had originally named the destructive species Lithophaga, a name that tells you all you need to know. For Lithophaga means rock-eater in Greek, which is exactly what these clams do. They bore into rocks at the watermark, eventually reducing the host limestone to a kind of framework. The implication should be clear, just as it was to Charles Lyell. The columns were, of course, constructed above the sea, but the whole marketplace must then have been immersed beneath the sea sufficiently to drown the lower part of the columns. Not only that, the whole marketplace must have been raised again for the visiting archaeologist to inspect the borings. It was possible to infer further details. The rock-eaters operate only in clear water, so it seems that the lower parts of the columns must have been buried beneath sediment in order to remain so clean. The borings total almost 3 meters of the columns. Thus the immersion and subsequent elevation must have been greater than 6 meters and could well have been more. Lyell was tempted to associate the depression of the temple with an eruption at Solfatara nearby in 1198 and its subsequent elevation with the eruption of Europe's youngest mountain, the small volcano of Monte Nuovo, which appeared almost overnight on the outskirts of Pozzuoli in 1538. I went there, although so juvenile, it is already weathering away to rich soil. Thus the interpretation of these past events was made rationally by reference to what could still be observed at the present time. The clams had not changed their habits. The world had gone up and down, or rather down and up, but this was not catastrophic. The street markets still plied their many trades. The same physics that had operated in past years operated again today. This statement seems almost banal now, but it provides the basis for all modern geological reasoning. There has been much puffy stuff written about whether or not Lyell's uniformitarianism permitted variations in intensity of causes, or whether he applied his logic in a consistent way, and whether he assumed indefinite stretches of geological time. And there is a good case for making the Edinburgh geologist James Hutton, 1726 to 1797, the true father of the modern geological method. For most geologists, though, the important fact is that Lyell provided a clear way of thinking about the world. He substituted a rational system of investigation based upon present processes for a belief in a series of catastrophes, the latest of which was the biblical flood, according to some. A marvelous cartoon by Henry de Labeche first, director of the Geological Survey of Great Britain and Ireland, shows the light of science dispelling the darkness which covered the world. The light in question that dispels the clouds covering the globe is carried by a female figure who also bears in her right hand a geological hammer. For this was the particular discipline that was seen as attacking reactionary thinking by main force. The Lyellian method still lies behind everything described in this book. Look at volcanoes today to understand volcanoes in the past. Do experiments in the laboratory to understand what goes on at depth in the earth. Look at what plates do at the present time to understand how the world was made. Stephen Jay Gould has pointed out that the Temple of Serapis was a much more appropriate symbol for the Lyellian method than temperamental Mount Vesuvius. Gould remarks in Lyell's Pillars of Wisdom, 1986, that Lyell presented the 3 pillars of Pozzuoli as a triumphant icon for both key postulates of his uniformitarianism, the efficacy of modern causes, and the relative constancy of their magnitude through time. Scientists now tend to downplay the second part of this thesis because they know that the Earth has evolved and changed from its origins more than 4 billion years ago. Not every process has continued at exactly the same pace at All times there have, on occasion, even been catastrophes, but the principle of reconstructing the past by using present-day analogs has remained at the center of the process of turning geology from a pastime for dilettantes into a science. I could not have said what I have said about the ignimbrite of Sorrento or the limestones of Capri without Lyell's example. Put simply, Pozzuoli made a difference to science. Charles Babbage should be mentioned at this point in the story. Born in 1792, Babbage was a brilliant mathematician, known today as the originator of computing and the inventor of the calculating machine. He, too, visited the Serapeum in 1828, 2 years before the publication of the first part of Lyell's Principles. He presented a paper on his very detailed computations on the site at the Geological Society of London on March 12, 1834, and it is a model of Lyellian reasoning. It was not published until 1847 as a postponed paper in Volume 3 of the Quarterly Journal of the Geological Society of London. The editor included the intriguing note that the paper, by the request of author, was returned to him soon after it was read, and has been in his possession ever since. One wonders what sort of inhibition caused Babbage to delay nearly 20 years before printing observations that would have placed him at the start of uniformitarian reasoning. By 1847, the scientific zeitgeist had already changed. However, you cannot but admire Babbage's summary. In reflecting on the causes which produced the changes of level of the ground in the neighborhood of Pozzuoli, I was led to consider whether they might not be extended to other instances, and whether there are not other natural causes constantly exerting their influence which, concurring with the known properties of matter, must necessarily produce alterations of sea and land, those elevations of continents and mountains, and those vast cycles of which geology gives such incontrovertible proof. From Pozzuoli to the world. In this brief summary, Babbage encapsulated much of the research program undertaken by modern geology. This book is about explaining the character of the Earth. The ultimate controls on the personality of the planet are tectonic plates. They are the natural causes constantly exerting their influence, of which Babbage wrote. So my story will inevitably lead to an outline of plate tectonics. But I shall get there through special and particular places like the Bay of Naples where geology and history are interwoven. I shall explore the influence of geology on the character of landscape and the character of people. Far from being the driest of the sciences, geology informs almost everything on our planet and is rich with human entanglements. The rocks beneath us are like an unconscious mind beneath the face of the earth, determining its shifts in mood and physiognomy. The progress of our understanding is also inextricably linked with the virtues and failings of the investigators. Different eyes at different times looked at the same view across the Bay of Naples and saw different things. One perhaps saw the wrath of the gods, another relief of pressure from a magma chamber. Textbooks tend to fillet out the history and scenery in order to give the current scientific consensus, so this is a kind of anti-textbook. In truth, the same classical areas have seen a half-dozen different generations of scientists tapping the rocks or putting their instruments about, but I shall try my best to avoid what the historian James Secord terms the Whiggish view of history, by which you uncover the mistakes of your forebears and the progress towards present enlightenment. Understanding is always a journey, never a destination. If you try to comprehend how thought has changed over a century or more, there are a few books that can act as useful benchmarks. Since Lyell, there has been a handful of authors who have comprehensively summarized the knowledge of their time, who have tried to write down the world on paper. One of those was the Austrian geologist Eduard Suess, 1831 to 1914, whose Das Antlitz der Erde, published in 4 massive volumes between 1883 and 1904, is probably the most ambitious attempt ever to capture the entirety of everything. You feel that a fact foolish enough to escape Seuss' grasp probably was not worth his notice. Seuss sat in Vienna like an omnivorous spider with a web spread over the world, tugging in facts. Das Antlitzter, Eart was translated into English as The Face of the Earth by Hertha Salas, the wife of an eccentric Oxford professor of geology, and published in 1904. 9. If you want a view of what geological knowledge was like at the end of the 19th century, when geologists using the scientific method had already scanned much of the world, then Seuss is your best guide. He, too, wrote of the Bay of Naples and of the Temple of Serapis, noting that on Capri there are lithophaga borings as much as 200 meters above present sea level. He had insights that are still woven into the fabric of geological thought, and even where we now know he was mistaken, it is instructive to try to understand why he thought what he did. Yesterday's cast-iron inference is often today's discarded argument. As Mott Green has pointed out in Geology in the 19th Century, Seuss differed fundamentally from Lyell in believing that, far from operating in a kind of steady state, the history of the Earth was punctuated by periods of pronounced change revolutions, during which mountain belts were thrown up. For example, we shall see that this tension between continuity and sudden change was resolved only when the plate tectonic view was established. In 1944, 40 years after the last volume of Seuss' magnum opus was published, another widely influential work appeared, Principles of Physical Geology by Arthur Holmes, known to generations of students simply as Holmes. It was a tremendously successful textbook from the outset for two reasons. It was well and clearly written, and it was illustrated throughout with photographs. Holmes was a professor at the universities of Durham and Edinburgh, and in some ways a more radical figure than Seuss. Cherry Lewis has recently written the first biography of him. Holmes did not try to write out the whole world in longhand like Seuss, but sought to illustrate geological principles by selected examples, which could come from anywhere, appropriate around the globe. It was a successful formula and will do well as a record of mid-20th century views of how geology makes the world what it is. My own intention is much more modest, since I have no pretensions towards the omniscience of Seuss, nor to the didactic skills of Holmes. The few places I describe in detail, many of which I have visited, show what geology does to the landscape and its history, or the kinds of animals and plants that flourish there. The intention is selectively to illuminate rather than to be comprehensive. Arthur Holmes is relevant for another reason. At the point we have reached in the journey around the Bay of Naples, he was a pioneer in methods of radiometric dating of rocks. This is vital to the narrative of the Earth. Lyell may have provided the intellectual tools for understanding geological processes, but he did not provide a time scale. The span of geological time was a mystery, and contemporary estimates of the age of the Earth varied wildly from a few to many millions of years. There were even those who still adhered to the calculations of James Ussher, 1581 to 1656, Archbishop of Armagh, which placed the date of creation in the year 4004 C. However, most scientists agreed that the Earth had to be old to accommodate all the rocks in their various sequences, all those Lyellian events, but how old? Leading 20th century physicists, notably Sir Harold Jeffreys, made estimates based upon good physics, but false assumptions, such as the presumptive cooling rate of the Earth. Such estimates invariably proved too young, but were vigorously defended for decades. The development of radioactive clocks has served to put an objective date on remote antiquity. The method is based on the natural rate of decay of the radioactive isotopes of certain elements, such as uranium, carbon, and potassium. These rates can be determined experimentally. For example, 235 uranium decays very slowly, over hundreds of millions of years to 207 lead. Hence, if you measure the amount of decayed product, you have a measure of time elapsed. It's as simple as that, though many complexities arise along with accuracy of measurement. Holmes' working lifetime spanned an era of technical improvements which continue today, and estimates of the age of the Earth steadily increased and became more accurate as methods were refined and older rocks were discovered in the field. After Holmes' death, dating of moon rocks and solar system meteorites finally nailed the time of the origin of the Earth at 4.5 billion years ago. These refinements of dating techniques allowed for calculation of the rates of change of what Babbage had called the vast cycles of geology, the speed at which plates move, the time taken to erode a mountain range, the length of time of an eruptive phase, how long dinosaurs were in charge of the land. Because different radioactive elements decay at varying rates, techniques must be tailored to the problem at hand. Thus, 14 carbon decays very fast and can only be used to date comparatively recent events up to about 30,000 years ago. I have a scientific paper before me that uses radiocarbon dates extracted from the same kinds of clams that bored into the Serapian's columns to show that on the island of Ischia there has been 70 meters of uplift in 8,500 years. So there are clocks of the world, completing the task that Lyell started. It has become almost a cliché that we cannot grasp the immensity of geological time, what 5, 50, or 500 million years actually means. But around Pozzuoli, the changes we observe have taken place over thousands, rather, than millions of years. Luciano Bagnoli has been compelled to move the mooring of his fishing boat nearly a meter lower since his father's time. Such is the rate of uplift in Pozzuoli. You do not have to travel very far if you want to see evidence for the forces that are lifting the whole region from the sea. The Solfatara crater lies just on the edge of town. You smell it before you see it, a result of what Oliver Goldsmith would have called its noxious emanations and pestilential vapors. It is still hissing furiously. Courses of angular boulders line the rim of the volcano, the remains of its last explosive phase, resulting in a volcanic breccia. Half of the crater floor is devoid of vegetation and as active volcanically as you could wish. There are numerous fumaroles belching forth steam. Holmes calls these active vents solfataras. So evidently we are at the type locality for this kind of thing. The Bacca Grande is the largest of them all, a roaring vent that emits steam at a temperature of 160 degrees Celsius. It sounds like a perpetually boiling kettle of enormous size, or the gasping of some great steam engine. It has been carrying on like this for years and years. A volcanologist called Friedlander built a hut almost adjacent to it, the better to monitor its exhalations, such as scientific obsession. The ancients called the area around the Bacca Grande the Forum Volcani, and you do feel that the earth is manufacturing or forging something deep beneath your feet. What actually comes out are sulfides. The stink in the air is hydrogen sulfide, the smell of rotten eggs. There are smears of reddish-yellow color around the lips of the vents. These are condensed patches of rare minerals, compounds of arsenic and mercury with sulfur, with names like realgar, orpiment, and cinnabar that would have been familiar to alchemists 5 centuries ago. This is indeed where the alchemy of the earth distills precious elements upon the ground. Most of them are also very toxic. They were the preferred materials of 19th century poisoners. In 1700, a high tower was built to collect condensate from the steam, and particularly for alum, which is used as a mordant in the dyeing industry. It no longer stands. This steamy natural cauldron is a place where chemistry happens in the open air. Around some of the hot holes thrive heat-loving bacteria that have probably endured on Earth for as much as 4 billion years. How much more extraordinary still to contemplate the Earth wholly in motion. Nothing seems to be at rest. The surface of the Earth dilates and collapses. The seas rise and fall. Further, the very continents move. Suetonius would have dismissed me as a madman had I pointed out to him that Vesuvius is a consequence, ultimately, of Africa moving bodily northwards. But Africa really is on the move. The floor of the Mediterranean Sea is a collage of tectonic plates. Ultimately, that sea is doomed to obliteration when the main body of Africa plows into the European mainland in 30 million years or so. But now the sea exists in an awkward accommodation, as the saying has it, between a rock and a hard place. The northern edge of the African plate is plunging downwards beneath the southern tip of Italy, which allows the infinitely slow oceanic contraction to continue. Italy is twisted and swiveled in the process. The energy released deforms rocks to marble and uplifts the limestone hills. A whole series of Italian volcanoes are engaged in this congress of plates. Stromboli, with its continuous, grumbling eruptions. Etna on Sicily, which has erupted recently. And dramatically, Volcano, the home of Vulcan himself and the eponymous epitome of a volcano, and more than 20 others with less familiar names, spanning much of the length of Italy and scattered through the Aeolian waters. The story of how these volcanoes relate to the movement of tectonic plates is a complicated one, and geologists do not agree on the details. However, all specialists seem to concur that the region behind the African collision zone has rotated anti-clockwise. Rending of the Earth's crust produced the Tyrrhenian Basin here 8 million years ago. The volcanoes were related to fracture zones that accommodated this convulsion in the skin of the Earth. They are like sticky blood oozing from deep wounds where the Earth's crust thinned. The jostling of the plates results in fractures in the crust faults, movement along which caused earthquakes and tremors. The uplift and tilting of strata are the testimony to this activity. Ultimately, the energy needed to produce lava derives from the crunching drive of Africa northwards into Europe. As crust plunged downwards, it partly melted, creating the magma which ultimately fed volcanoes. Lavas rich in the element potassium still retain a signature that proves that a proportion of melted continental crust must have been mixed up with oceanic crust. This magma recipe also conditions the fluid properties of the lava during eruption. At some times it flows in an almost docile, if relentless, fashion. At others, mixed with gas and water, it explodes in a series of devastating pyroclastic flows. Everything around the Bay of Naples is controlled by the movements and interactions of tectonic plates kilometers below the surface. The scene is under the control of the unseen. The surface is at the behest of the underworld. Exploring such connections is the theme of this book. Even the most apparently ephemeral of Earth's memorials are a reflection of a deeper reality. What could be more superficial than man's concern with his appearance, with cosmetics the paint on the surface that attempt to plaster over his own mortality? What could be more trivial by comparison with geological reality? The town of Bea on the western side of the Bay of Naples was born out of hedonism and beauty treatments. The hot springs there fed Roman baths of unrivaled luxury. There are still ghosts of paintings on the ceilings of the rooms where the rich went to cool off or heat up and giggle at the latest gossip or discuss the hottest scandal of the first century. What modern-day Italians call the Bella Figura was just as important nearly 2,000 years ago. The baths were fed from springs that were plumbed down into a tectonic reality that cared nothing for the carnal scandals of a two-legged ape that only moved out of Africa a few thousand years ago. These springs were the exhalations of the magmatic unconscious. Yet Bea and the Pozzuoli Coase invented the concept of the holiday, time out in luxury to tickle the palate or the fancy. According to contemporary sources, the slopes of the bay were lined with marble palaces and walkways furnished with columns and with cool fountains for reflection and dalliances. Edouard Seuss was disapproving. It was in the flowery fields of Puteoli, Baiae, and Misenum that under the empire, at the expense of a subjugated world, the most sumptuous festivals were celebrated. This area was like Nice on the French Riviera in the days of the English aristocracy, or the Big Sur coast of California in the days of the Hollywood glamocracy, except that it was on a scale altogether more grandiose. You can still get some impression of the vanished splendor and luxury, for Baya remains, although the plaster has mostly fallen off the walls, and the paintings have often faded. The hillside, where the stylish Romans strolled after their bath, is still there, but it now has the atmosphere of a terraced provincial park gone to seed. The view across the Bay of Naples remains splendid, and with a little effort it is possible to imagine a continuous stretch of villas lining the bay. Close up, however, all is decay. Even the diamond pattern of the yellow tuff bricks, the opus reticulatum that built the walls, shows mortar standing proud of the weathered bricks it supports, for the rocks produced by a violent eruption do not necessarily make strong building stones. The earth movements in this area have submerged the ancient waterfront, so that it now lies more than 400 meters from the present shoreline. Part of the drowned city is still visible in the clear water. The thermal springs no longer bubble up in the ancient baths, since the island of Ischia, which lies off the northwestern edge of the Bay of Naples, and where the springs are alive and pumping. A doctor there will advise you on which particular elixir you need for your aches and pains, but fashion and geological plumbing have deserted Baya. The western end of the Bay of Naples is the Capo Messino. It is now a deserted spot, although it was once a great naval base for the empire, and housed perhaps 10,000 sailors. Only scattered foundations and remains of columns attest to its former greatness. From here, you can look back across the Bay of Naples towards Vesuvius, with the Sorrento coast beyond where this chapter began. It is a good place to reflect on historical and geological time and the forces that have shaped everything in prospect. The bay itself, the craters around the Campi Flegrei, even the distant hills. This was a spot where geology could be said to have begun when Pliny the Younger, as a youth of 18 in AD 79, observed from a safe distance the eruption of Vesuvius that obliterated Pompeii. His uncle, the elder Pliny, died in the eruption. The latter's natural history was a cornerstone of natural philosophy for more than 1,000 years, so it would not be too much of an exaggeration to say that the future of all science was engaged with the magma chamber of one temperamental mountain. The younger Pliny described a cloud that proved his uncle's nemesis as resembling one of the umbrella pines or Italian stone pines that still provide welcome shade around the villas dotted about the bay. The volcanic cloud shot up to a great height in the form of a very tall trunk, which spread itself out at the top into a manner of branches, occasioned either by a sudden gust of air that impelled it, the force of which decreased as it advanced upwards, or the cloud itself being pressed back again by its own weight, expanded in the manner described. It appeared sometimes bright and sometimes dark, according to whether it was more or less impregnated with earth and cinders. This type of volcanic event is still known as a Plinian eruption. The ash column can rise to 50 kilometers into the atmosphere, and then the ash can be spread for thousands of kilometers by winds. An eruption can alter weather patterns for months. The force behind the expulsion of the column is the result of gases expanding within the magma as it rises, as the overlying pressure is reduced. A kilometer below the surface, the rising mass loses all Coherence. The volcano violently boils over. As for the pyroclastic flow of Ad, 79 it, too, reached Pliny the Younger. It traveled across the Bay of Naples, shedding its lethal load and losing strength. By the time it reached the young man, it was little more than a miasma. It dropped the merest layer of fine ash over his sandals. Part 2. Island. Hawaii is evidently paradise. There are paradise restaurants, paradise realtors, paradise tours, paradise apartments. The Hawaii Star Bulletin modestly describes itself as the pulse of paradise, thereby grafting paradise onto the qualities of a living being. There is a lot of business hanging on Hawaii's paradisiac qualities. When you first approach Waikiki, the resort town on the developed island of Oahu, paradise is not the first comparison that comes to mind. One traffic jam is much like another, and vast hotels vaguely themed on ersatz. Polynesian mementos are no vision of life in the Garden of Eden. To be sure, the lawns in front of the hotels are immaculately trimmed. Palm trees lean out to greet you. There are even waterfalls tastefully constructed about the entrances, and there is a smile on the lips of every flunky. This is paradise. Designed for the determined shopper, Armani and Gucci and Tommy Hilfiger. Outlets line up along the sidewalk, doubtless two in the Paradise Mall, alongside 100 other familiar names to nudge the relaxed holidaymaker with bargains that will seduce them from their cash. The goods are mostly the same as can be bought in London or Rome or Tokyo, a kind of global cornucopia, deceptive in its promise of local idiosyncrasy. Most of the Aloha shirts are made in China. Perhaps the visitor should turn elsewhere to discover paradise. Not far behind Honolulu, mountains rise surprisingly quickly, and they are clothed in forest. There's an easy walk through it to the Manoa Falls north of Waikiki. The little path dodges this way and that through the trees, ever upwards, often muddy. This is more like the paradise of the movies. Vast trees soar way above you, and their huge trunks are decked with climbing plants, some of them with enormous leaves or heart-shaped foliage blotched with yellow patches. These vines seem vaguely familiar from florist shops, though here they grow on a giant scale. There is an intense and humid odor of prolific growth. You can almost hear the shoots squeezing upwards. Towards the sun, there are pale yellow spikes of fragrant ginger flowers on either side of the path. Within a few minutes, you are dripping with perspiration, for no breeze disturbs this extravaganza of unfettered growth. Piping noises echo somewhere in the canopy way above. Half-seen birds, such as these, are obligatory in Eden. When the waterfall is reached at last, some of your fellow walkers cannot resist the urge to wade out among the rounded boulders to catch a fickle spray that has plunged 200 feet down a lava flow. Bathing in a pool in the midst of a primeval jungle is a dream of paradise on the holiday brochure. But this, too, is a bogus paradise. Almost none of the plants that climb up the massive trees along the path are native to Oahu or the Hawaiian Islands. Indeed, neither are the trees themselves. They are interlopers brought to this remote place by humans. These plants settled in the tropics and thrived, displacing much of the native vegetation. The resemblance of the climbers decking the trees to pot plants is no coincidence. Some of them are the same species that can be bought in a supermarket in Norfolk, England, or Plains, Iowa, as commonplace in their way as tomato ketchup. Even the sweet-smelling ginger plant that looks so at home by the pathside is a Johnny-come-lately an aggressive colonizer. This place is not so much paradise lost as paradise replaced, a paradise of aliens dressed up to look as if they belong. The massive assurance of the trees is play acting. The Hawaiian Islands were once pristine, as remote from any major continent as anywhere in the world. They were originally colonized by a mere handful of hardy, far-traveled plants and animals, birds, insects, reptiles, that subsequently evolved prolifically in their new Eden. The species that appeared as a consequence were endemics. That is, they were found nowhere else in the world. The islands became a natural evolutionary laboratory. There were several hundred fruit flies found nowhere else, and an array of flightless birds pecked among the underscrub. This is where a caterpillar learned to be a meat eater. The land snail Acatinella evolved 1,000 or more species. The familiar plant Lobelia, blue-flowered mainstay of 1,000 hanging baskets, evolved fantastical tubular flowers that could only be pollinated by even more fantastical birds, scarlet or yellow honeycreepers with bills as narrowly curved as precision surgical tweezers. The Bishop Museum displays glorious, ceremonial capes of Hawaiian chiefs fabricated from the feathers of countless honeycreepers. They must once have been abundant. These wonderful birds are now, alas, mostly displaced by interlopers minor birds, and doves with more ordinary dietary requirements. They can feed on the crumbs and scraps left by tourists where the honeycreepers dine solely on nectar. Even the flightless birds had their part to play in the original ecosystem. They ate the fruits of the aboriginal trees, whose seeds could only germinate once they had passed through the avian digestive system. But then, the introduction of the mongoose saw to the extermination of the flightless birds. So, why introduce the mongoose? These aggressive little predators were brought in deliberately from India to catch rats, themselves another introduction. The rats escaped from ships, doubtless, as they have all over the world. They threatened the sugar-cane crop, which, of course, was yet another introduction, and one which transformed the Polynesian mixed economy of taro cultivation, supplemented by fruit and fish, into the specialized cosseting of a cash crop. But then, the Polynesians themselves had already introduced the breadfruit and several useful species of palms. You begin to wonder at what point paradise first became corrupted. Nowadays, mongooses skitter across the road in front of you when you least expect it. Cheekily self-confident, they must have made short work of endemic flightless rails and other birds. But the rats are still there. Mongooses are mostly diurnal, whereas rats are nocturnal. The extermination policy that introduced them was as pointless as proposing to introduce bats in order to eliminate wasps. Both mongooses and rats prospered while the birds disappeared. The few trees that remain from archaic times have no method of reproduction. They have outlived their propagators and have become sad remnants enduring from a vanished paradise. They are not entirely doomed, because attempts in the Lion Arboretum to regenerate them from culturing slivers of their living tissue have met with some success. The Arboretum, where this work goes on, is where you might get a hint of what might have been in the original islands but carefully cultivated, a kind of garden of Eden reconstituted. You begin to wonder whether you can go anywhere to see the real thing. Hawaii is actually a group of islands, all of them volcanic. The island of Oahu is the one that people tend to imagine represents the typical Hawaii. This is where the hotels and surfing beaches of Waikiki promise counterfeit paradise. Most of the islands, however, are completely different from this. Urban fantasy. The volcanic activity on Oahu is quiescent. The other main islands are Molokai, Kauai, Niihau, Maui, and the youngest, and by far the largest, known everywhere as the Big Island. Strictly speaking, this island is Hawaii, and it is still actively erupting. This is where you can go to see the world being made. On the rainy side of the Big Island, on one flank of the volcano's national park, there is a remnant of the original forest. This area is several thousand meters above sea level, and the rain is often heavy. In the mornings, a drenching mist can smother the landscape, only to be fried off by the sun. Before midday, The dominant canopy plant is the ohi, a grayish tree of medium height, often gnarled and dressed with lichens and carrying small, oval, dark green leaves that shine attractively in a certain light. Early in the day, there is a silvery brilliance in the ohi forest that cannot be matched anywhere else in the world. When in flower, the ohi is called ohi lihua. The flowers look like old-fashioned shaving brushes made of dense red stamens. Several of the remaining honey creepers earn their living from sipping the nectar of their blossoms, and there always do seem to be flowers. Somewhere in the ohi forest, around Volcano Village, the understory is composed prominently of tree ferns. The commonest species is the Hapiu sabodium, a majestic and graceful fern with all the elegance of a green fountain. There are so many of them it looks almost as if the earth has sprung a series of verdant, spouting leaks. Other herbs and small trees clamber among the ferns, bewildering botanists who try to place them with their more conventional relatives. In this forest, there is at least a chance that the piping you hear is from a native bird. The churring is almost certainly the native cicada, but along the path sides there are already plantains that you recall as weeds from Europe. The scourge of every lawn and the seductive ginger plant pokes out from the undergrowth. There is trouble already in this paradise. This jungle is simply structured, comprising only a canopy and understory. The ohi trees are not like the dominating and diverse monsters of the Amazonian rainforest, with layer upon layer of tiering beneath them. Yet, within these gray woodlands there are hundreds of species unique to the Hawaiian Islands. Then we must add the fact that each island has a windward and a leeward side. Most of the rain falls prolifically on the windward side. The other side is in a rain shadow. Clouds throw down what moisture they carry as they climb the mountains, but the further side remains dry. The animals and plants are different again on the dry flanks, tougher in several ways. Survivors in the face of hardship, they comprise an entirely distinct community from that of the rainforest, growing on nearly bare lava flows. The flora includes small relatives of the familiar cranberry. The ohelo carries a bright red, succulent berry that was once a staple item in the diet of the nene, the Hawaiian goose. The nene is a handsome bird that almost became extinct in the wild but was reintroduced successfully from ones bred in captivity. Ohelo berries are pleasantly tart, like watery cranberries, but scarcely the forbidden fruit of paradise. Ritual dictates that you must offer a berry or two to Pele, the fierce goddess of fire, before you eat them yourself. Many of the drought-tolerant species, like the ohelo, are rarities now, too. Because the volcanic mountains rise to great heights, there are some unique species adapted to alpine conditions. The most extraordinary of these is the silver sword, a huge bundle of silvery, blade-like leaves looking something like a crouching, bristling porcupine. It lives high on the bare volcanic slopes, at an altitude where little else will grow. It flowers and then dies. The flowering spike arises like some huge columnar firework from the center of the leaf rosette. Close examination reveals that each flower head is little more than a daisy. There are hundreds of these humble purple flowers on each spike. It takes the silver sword 20 years to screw up the energy for its final floral pyrotechnic. This is what Hawaiian isolation has done to one of our most familiar flowers. The remarkable forests with their remarkable animals, the rain shadow plants, the nene, and the hundreds of inconspicuous fruit flies all owe their existence to the geology of the Hawaiian Islands. This is a place where the geology announces itself in everything you see. Only in Honolulu and Waikiki do the works of mankind obscure the works of nature, save for the starfruit trees in the backyards, the neat suburban roads lined with well-tended villas. Surrounding these cities might be in almost any small town in Iowa or Michigan. North American domestic vernacular architecture has become the lingua franca of middle-class habitation. On the remoter shores you may see the open canopy dwellings of the Polynesians. There are very few purebred Hawaiians. On the windward shore of Oahu, these houses are often backed by steep cliffs of dark volcanic lavas. Scratch around almost anywhere and there will be similar volcanic rock beneath the dirt. The geology dictates the soil. Along the trail to Manoa Falls, this rock weathers to something with the color and consistency of gingerbread. It can be ground to crumbs in your hand. Constant tropical rain makes a mush of hard old lavas. The end product is a brick-red soil called laterite. Its color comes from all the iron in the oxidized or ferric state it contains, its other important element being aluminium. Laterite soil is not suited to growing many crops, but sugar likes it. The great cane fields of Hawaii used to occupy much of the lower ground, at least from the 19th century onwards. Feral canes are still everywhere. To a European, they look like hugely overgrown leeks. The bottom fell out of the market during the Reagan era, and now the great mills stand idle, and some of the fields are reverting to scrub. Others have been taken over by pineapple plantations. In the saddle or valley between the huge, extinct volcanoes on Oahu, the Dole plantations stretch for mile after mile. Along Route 99, the pineapple was once considered so exotic that it became a symbol of wealth to the aristocracy who alone could afford it. Pineapples, sculpted in limestone, often adorn the gates of stately homes in England. It comes as something of a disappointment to see huge pineapple fields so relentlessly uniform in ranks of green rosettes. You expect to see trees as exotic as the fruit itself. Isolation created the opportunities for the species to evolve that made the original paradise. The islands all grew as volcanoes from the sea floor over. The last 5 million years or so, the Big Island is still growing. 20 miles off the southeast coast of this island, there is an active volcano still hidden beneath the sea. The Loiaisi Mount is steadily erupting, and one day it, too, will break above the waves, and a new land will be born. Within a year or two, the first pioneer plant species will arrive to colonize the bare lava, their seeds perhaps being carried on the feet of a passing booby. The process of evolution will happen all over again. This insular birth is supposed to occur in 50,000 years or so, a geological tomorrow. The Hawaiian Islands provide an opportunity to see the birth, maturity, and death of a landscape. Creation is here, so, too, is massive erosion, and it has all happened in a time scale of just a few million years, a span that we can begin to understand. The Polynesian peoples arrived by boat for the first time about AD 500, but a second wave of immigration from Tahiti was more or less contemporaneous with the Norman conquest of England in 1066. The evolution of the web of interrelated island endemic species took thousands of times longer time enough for some species of birds to lose the capacity for flight and for others to develop long curved bills. Think of what has happened in the 1,000 years since the Norman conquest, all the advances and reverses and complexities of history, the technological revolutions, the rise and fall of empires. It then seems less astonishing that a complete and distinct biology should arise in a span of more than 50,000-fold again. The Big Island is the most southerly island of the group, and near its southern side you can witness the genesis of new crust. Lava has erupted from Kilauea for hundreds of years. Occasionally it blasts out in major eruptions, hurling volcanic bombs hundreds of feet into the air. Mostly, however, the eruption is comparatively benign by volcanic standards. The kind of basaltic lava that has built Hawaii is highly fluid and charged with gas. It flows rather than explodes. A new lava flow cannot be entirely stopped, but it can be outrun if your house is about to be engulfed. The flow of 1992 to 97 blocks the coastal road that used to run southwards from the town of Hilo. It simply truncates the paved surface at right angles, abruptly. From one side it looks as if a gigantic load of tar had been dumped by a disgruntled contractor. The road disappears beneath the flow, and sure enough, if you walk to the far side of the flow a few miles along the coast, the road emerges on the other side, apparently unscathed, but the surface of the flow is hard to walk over, being a mass of black and twisted lava. Sometimes it is only too clear that it has cooled from a sticky liquid. Braided curtains or wrinkled sheets of shiny, tarry lava heave and plunge under your feet. The texture of the surface is often described as ropey, and it is an apt description to anyone who has seen tangled masses of ropes on the side of a harbor. On steeper slopes, twisted clots of entrails come to mind. It is astonishing to stand in the midst of a huge lava field with the undulating masses of volcanic material stretching away as far as you can see, for this is a fresh-made world. You are permitted to inspect the current eruption from a safe distance. Parts of the old road have recently been revived, and you can drive very carefully and very slowly over graded parts of recent flows to get near to where the lava still debouches into the sea. Steam plumes, visible from miles away, rise continuously at the meeting between the new crust and the eternal waves, and there is a fierce hiss at the boiling junction. The stench of sulfur is everywhere, sharp in the back of your throat. If this is the breath of the deep earth, then it is poison. You must watch where you step over the recently cooled lava flows, for there are areas where the surfaces have heaved into cracked slabs, as if a vast tarmac atom airfield had been bombed almost to oblivion. It is easy to twist an ankle. On humid days, water vapor combines with the sulfurous emanations to produce an acrid mist known as VOG. As dusk falls, the brightness of the living lava becomes more evident. The warm, red glow at the sea's edge has a brilliant orange heart. Then you witness an explosion where the combination of violent boiling, sudden cooling, and expulsion of gas result in luminous chunks. One might be the size of a pumpkin rolling up into the miasma of steam. Fireworks almost, but more inexorable. For the moment the lava wins against the ocean, but one day the balance will be reversed. Now it is dark. You can see other brilliant lights along the flanks of the landward slope. They form a line. It is easy to deduce that this line marks the current course of the flow. It is not at the surface, but flows in a conduit, a lava tube, a short distance under the inky wasteland. You can trace the lights to the vent itself, at Pu on the flanks of the older Kilauea caldera. After the initial eruption from the new vent, the crust on top of the lava flow solidified, but the flow continued unabated beneath the skin covering over the tube. It is like an artery continuously bleeding the red blood of the earth. In places, the roof of the tube has crumbled away, and the lights on the hillside trace these windows, giving into the streaming inferno beneath, glowing bright orange. There is a lucrative local trade in lava photography, and many Hawaiian photographers like to crawl close to the windows and record the streams of magma and the fountains of fire that splatter up from time to time. But there are dangers. Where the lava hits the sea, it often builds out into an unstable platform. Only a few years ago, 2 overconfident visitors were killed when the platform broke away into the violent and boiling sea. The process of creation is not merely dramatic, it can be lethal. In the Volcanoes National Park, you can walk inside a lava tube which has long since voided its last molten load. The Thurston lava tube now lies in the rainforest, and tree ferns decorate its entrance. It had a curiously familiar feel to me. and it was some minutes before I realized that this was because it had the exact dimensions of that other tube the Piccadilly Line tunnel in London, on which I travel virtually every day. It is indeed almost perfectly tubular. The walls are curiously smooth. There is nothing here to produce the stalagmites that adorn caves in Kentucky or Cheddar. Part of the tube has been illuminated, but you are permitted to go on into the darkness at your own risk. It is a strange sensation to creep by flashlight into the guts of a former eruption, and just for a moment you might wonder if that rushing sound might be something other than the wind in the OHIA trees. But the dimensions of the tube do give you a very good idea of how much lava can be transported in an eruptive phase by measuring the velocity of a flow. It is easy to calculate the volume of an eruption. On the present eruption at Puyu, flow velocity is measured using radar through the skylights. Since 1983, 300,000 cubic meters per day have been flowing down towards the sea. Creation can be calibrated. The eruptions happening now are as nothing compared with those of the recent past. The Kilauea caldera remains as a testament to this activity. It is huge, for miles, 6.4 kilometers across. You come across it almost unawares. Driving through the lush OHIA forest, suddenly the colossal whole of Kilauea Iki is before you, and you have glimpsed a different world. It is as if some irresistible force had pulled an enormous bung or plug out of the earth. Far below, the congealed lava in the crater still smokes from cracks in its surface. The whole pit is so clear of vegetation and so regular that for a moment you wonder whether such a structure might be man-made. It has been cauterized, clean, and surely only human labor could carry out such an efficient scrubbing job. Then you can visualize that beneath the crusty surface there is still liquid rock lying low. It somehow looks as if it had only recently finished cooking. Kilauea Iki erupted as recently as 1959, and there was a major flow from elsewhere on Kilauea in September 1982. The whole place is not exactly sleeping, more pausing for a moment in the middle of a bad dream. When the Volcano House Hotel was opened in the 19th century, the visitor could look down at boiling magma pools from the balcony while sipping a scotch and soda. From time to time, spectacular lava fountains might create a pause in the conversation, but mostly the Hawaiian lava was benignly spectacular. Mark Twain entertained his readers in California with his graphic account of an eruption on June 3, 1886. A colossal column of cloud towered to a great height in the air immediately above the crater, and the outer swell of every one of its vast folds was dyed with a rich crimson luster, which was subdued to a pale rose tint in the depressions between. It glowed like a muffled torch and stretched upward to a dizzy height toward the zenith. I thought it possible that its like had not been seen since the children of Israel wandered on their long march through the desert so many centuries ago over a path illuminated by the mysterious pillar of fire. On occasion, eruptions can be much more dangerous, particularly when groundwater comes into contact with hot magma. Instantly, vast quantities of steam are generated, which punch out vents with colossal force, carrying rocks, volcanic bombs, and hot steam hundreds of meters into the air. A great roaring and hissing sound accompanies the drama. Such was the origin of Halimuyu, now an almost perfectly circular crater within sight of the Hawaiian Volcano Observatory. Its flanks show several former lava flows quite clearly, while stains of yellow smear its sides. The crater's eruption history has been closely studied. When it contained an active lava lake in the early years of the 20th century, the level of the lake went up and down by many meters. It overflowed onto the floor of the Kilauea caldera in 1919 and 1921. In 1920, for the lava withdrew, simply draining away via subterranean fissures. The unsupported sides of Rhône-Poulenc collapsed and created an obstruction until groundwater penetrated its underground plumbing. Violent explosions then showered the surrounding lava plains with rocks, which still lie scattered over the surface. During the explosive phase, the dimensions of the pit increased from 800 by 500 feet to 3,400 by 3,000 feet, 243 by 152 meters to 1036 by 914 meters. A trail takes you past a series of steam vents, from which the last gasps of this volcanic fury are exhaled. Superheated steam issues from inconspicuous holes fumaroles which are dotted over the ground. If you get too close, you get scalded very quickly. This kind of steam is colorless and undetectable, and only when it cools down does it make a wispy plume. In the early morning, when the humidity in volcanoes national park is high, the whole area looks as if a dozen or so kettles were boiling away, each with its own steamy signal. The yellow patches that commonly smear the ground around the fumaroles are composed of raw sulfur, and there are red patches on the flows where the steam has oxidized the iron in the basaltic rock. The bright-colored sulfur is brimstone, the fuel of hell itself. Brought up from the depths, it crystallizes at the cooler surface. It is easy enough to scrape a few crystals onto a knife. If you examine the crystals under a lens, you will see that they form tiny but perfect prisms. The fumaroles emit a gas which is also linked with sulfur dioxide, produced when oxygen and sulfur combine. This is the gas that once made London the perfect place for Jack the Ripper to vanish without trace after his crimes. More than half a century later, the smog was abolished. By banning open coal fires, you can still get the same hellish whiff in big industrial cities in China and Russia. Sulfur dioxide is distinctly bad for weak chests and is heavily implicated in acid rain, since it is readily transformed into sulfuric acid. But here on Hawaii, its occurrence is wholly natural, the exhalation that accompanies the birth of the crust. Rhône-Poulenc is the home of the goddess Pele. She is only one of a complex series of gods and goddesses that once influenced almost every aspect of life. In Hawaii, everything in nature had a god responsible for it, and the gods themselves were capable of embodiment in a variety of natural things. A dolphin or a turtle may be the embodiment of Kanaloa, god of ocean and winds. All natural phenomena are extensions of the gods, who were prolific in their varied ranks and stations. In this pantheon, perhaps even rocks had a kind of consciousness. The operation of taboos or kapu-kept society, ordered quite cruelly on occasion. Pele, as you might expect, has a volcanic temperament in keeping with her preferred habitation. She was wont to take a fancy to handsome young men and embodied the dry and fiery leeward side of the island. Pele's lover and opposite, Kamapua'e, was associated with rain and with the windward side. One of her tricks was to change herself into an ugly old woman, ready to reward those who offered her charity or launch an eruption on those who did not. After the hold of the other gods has faded, Madame Pele still seems to excite superstition. In the Volcano House Hotel, there are pieces of pumice returned from all over the world. Accompanying letters claim that after taking this or that small piece of Pele's volcanic property, the owners have had nothing but bad luck and so have dispatched the pieces of purloined rock back to their rightful place in the hope that Pele will lift the curse. The eruption of Rhône-Poulenc was naturally attributed to Pele's displeasure. Perhaps she would be pleased to know that there is a volcano named in her honor on Jupiter's satellite Io. If you riddle around among the more recent lava flows, you will find her tears and hair. Pele's tears are shiny, black, drop-shaped stones. They formed when hot lava sputtered or exploded into the air, As the tears fell to earth, they cooled suddenly, frozen in shape. Now, they can be found preserved in crevices in the top of lava flows. Pele's hair is spun from liquid lava, glassy, filaments drawn out as the gas is sped from the lava. It has something of the texture of spun sugar, but is rather brittle to candy floss of the earth. It has an almost golden sheen. So this conjures up a picture of Pele as flaxen-haired, but with black tears coursing down her cheeks. I also found an extraordinary, light material called reticulite, a kind of froth-frozen and spun glassy lava. It looks much like foam, such as might be blown up by a landward breeze on a beach, but then strangely solidified. It is very fragile, and almost as easy to damage as foam itself. Intense frothing of the magma threw up this delicate confection. Eruptions can have a light touch in the right circumstances. Lava flows can be well over 40 kilometers long before they reach the sea, like the Great Flow of 1859, which runs northwestwards from Mauna Loa. There are two principal types of lava readily distinguished in the field. The twisty, ropey kind that personifies flow-all congealed motion is called pahoehoe. This is the easy kind to walk over. It is like traversing an irregular road that has been partially melted, heaved, and distorted. The other kind is all blocky and lumpy, a jumble of sharp chunks and clinker, rough and impassable. This is known as a lava, and it is truly dreadful stuff to walk over. I overheard a geologist say that a good pair of boots can be rasped to bits on AA in a couple of months. The flows are initially as black as a Sunday hat, but as they weather, a crusty brown predominates. Looking down on the landscape from the side of Kilauea, fresh black flows overlie the older, brownish ones, as if some giant had carelessly spilled a great pot of black paint down the hillside, or it might be the shadow of a dark cloud cast upon the ground. Where the road has cut through the flows, you can easily see how one flow lies upon another. Often the surface of an individual flow is weathered brownish with an A topping, so that stacked flows have the appearance of a kind of volcanic club sandwich. The whole island is built of these flows, one on another. Perhaps a better image than a sandwich for the formation of the islands is a giant stack of pancakes, countless endless sheets of congealed lava piled up as if cooked for the fattest and most insatiable Polynesian god of gastronomy. My map tells me that the summit of Mauna Kea, the highest volcanic mountain on Hawaii, is 13,796 feet, 4,205 meters high. The other great volcano on the Big Island, Mauna Loa, is hardly less considerable at 13,679 feet, 4,169 meters. But this is only the part that projects above sea level. The average depth of the ocean floor in the Hawaiian region is 16,000 feet, 4,877 meters. A simple calculation reveals that, measured from the sea floor, their true base, these volcanoes are approaching 30,000 feet or 9,000 meters high. Taken together, they make up one of the greatest structures on Earth, higher than Mount Everest. Mauna Loa is estimated to occupy 19,000 cubic miles. When submersibles were used to examine submarine eruptions, those unseen events that even now are building up Loihi towards the sea's surface, the form of the lava flows discovered was different from anything on land. Cooled rapidly as it belched out under pressure, each lava pulse congealed into gobs and lobes. The globular masses piled up. Volcanic rocks of this kind are known as pillow lavas. Ancient pillow lavas are easily recognizable. I first saw them underneath a lighthouse on the coast near Fishguard, Western Wales, where they were nearly 500 million years old, but they did not look so different from some of those listed in Hazlitt and Hinman's Roadside Geology of Hawaii. There are different processes again when the stack of flows rises above sea level. When sea and lava engage in violent conflict, this is the battle that I had witnessed for myself in the foggy dusk. Explosive cooling and the sedimentation of glassy fragments results in a rock with a characteristic speckly texture known as hyaloclastite. So you can now envisage a succession of flow types that would follow one another to construct a volcanic island. Pillow lavas at first, then a mixture of pillows and hyaloclastites as the island wins the battle for emergence, and then pile of flowing Pahoehoe and its crusty companion Aa. All these stages are exhibited in one or another of the Hawaiian Islands. The first Western visitor to the islands was not slow to appreciate their mode of formation. Captain Cook recorded in 1778 the coast of the Cow District presents a prospect of the most horrid and dreary kind, the whole country appearing to have undergone a dreadful convulsion. The ground is covered with cinders and intersected with black streaks which mark the course of lava that has flowed not many ages back from the mountain to the sea. The southern promontory looks like the dregs of a volcano. James Cook was under no illusions about this place as a kind of paradise. To him, paradise would have been a much more orderly affair, a garden of organized orchards and well-tended herbs, perhaps with a passing resemblance to his home in Marton, Yorkshire. Cook was killed by the locals on his return to Hawaii the following year, allegedly in retaliation for a flogging administered to a native thief. If there was a moment that marked an end to the island's isolation, it would be Cook's visit, for afterwards they were located accurately on a map for others to find. The missionary William Ellis visited Kilauea in 1823, probably the first Westerner to enter Pele's domain. The perception of the place had changed utterly in 40 years. In his narrative of a tour through Hawaii, 1826, he enthused that, in appearance, the island of Hawaii is grand and sublime, filling the beholder's mind with wonder and delight. The poet Samuel Taylor Coleridge read and approved the modern version of the island as Eden was born. The best views of the great volcanoes of Mauna Loa and Mauna Kea are from the air. From the ground, it is difficult to appreciate their colossal scale, and they are often obscured by clouds. When the sky clears, they do not tower in quite the way that mountains are supposed to. Rather, they loom. It is only when you realize that all roads directed towards them go relentlessly upwards, apparently forever, that you begin to understand their height. It takes several days to hike to the cold top of Mauna Loa. The summit of Mauna Kea is considered the ideal place to mount an astronomical observatory, for above the clouds there is only the stars and the skies are ideally transparent. From an aeroplane, you can see why these giant Hawaiian volcanoes are known as shield volcanoes. They do indeed resemble upturned Roman shields, at least until they begin to be dissected by erosion. Their comparatively gentle slopes are no less than the natural angle engendered by the solidification of countless lava flows. The shield analogy fails in detail, for at the center of Mauna Loa and Kilauea lies not a boss, but rather a great depression. Such a caldera marks the collapse of the center of the cone as the lava, which once buoyed it up, drains away to the underworld. The ages of the volcanoes on the big island of Hawaii decrease from north to south. The youngest, Kilauea, is the most active and the most southerly. Mauna Loa is the next oldest, then Mauna Kea, then Hualalai near the western Kona coast, and finally the oldest, Kohala, at the north of the island, which last erupted about 100,000 years ago, and the main shield of which was probably built by 400,000 years ago. We shall see that this progression is a result of plate movements. The first phase of igneous development is the Great Shield Volcano. Later, volcanic vents open up wherever a tongue of magma can find an outlet to the surface. Many parts of the Big Island have experienced the sudden expression of Pele's anger, for the early phases are often the fiercest. Around the main volcanoes, the eruptive centers, are localized along rift zones. These zones are the traces on the ground of planes of weakness marked by faults, along which lava preferentially penetrates. The chain of craters Rhône and the volcanoes. National Park follows the eastern rift zone of Kilauea. As its name implies, there are craters all along it. Mauna Ulu erupted in 1969 to 74, and now its legacy is a vast field of black pahoehoe lava glistening in the sunshine, in some places smooth and undulating like mass kidneys, in other places twisted like intestines. A little searching will turn up more of Pele's hair, so this is a truly anatomical landscape. In little crevices in the lava there are ferns growing. It does not take long for life to reclaim the barrenness. Where the lava is broken, it is easy to see the bubble-shaped holes from which gas has been released during the eruption. In places, it seems as much bubble as rock clinker, you might say, or more correctly, scoria. Further down the chain of craters road, there is a pagoda at Ka'alakomo with a wonderful view of the side of Kilauea. The landscape is terraced into a series of grassy hillsides. Each scarp is 30 meters or so high and is the graphic expression of faults that prove that Kilauea is sliding into the sea, even as the volcanic pile heaves itself thousands of meters above the sea floor. Its edges begin to collapse like the flanks of an overambitious children's sandcastle. The 1969 74 lava flows tip over the terraces like so much spilled treacle and crawl all the way across the plains below to the sea. The cliffs are already more than 30 meters high, and constant erosion has forged natural arches. Eruptions are spawned from a magma chamber, a fiery stomach beneath the main volcano. As pressure builds up in the chamber, it is released in the spewing flaming fountains and vivid showers of lava that spill out from the crater. Tributaries of magma insinuate themselves through cracks and older flows, splits brought on by the relentless pressure from beneath. Once breached, a crack will spill forth lava until the source dries up. Occasionally, in a roadside cut, you will spot vertical feeder dikes that once fed liquid rock to the surface. They sit at odds with the general attitude of the rocks, a perpendicular injection through the layered skin of the volcano. As the magma builds up pressure within the chamber, the ground swells, as if the earth were taking a deep breath prior to strenuous activity. Sense the swelling, and we may have a way of anticipating an eruption and taking precautions against disaster. At the Volcano Observatory on Kilauea, the eruptive activity has been monitored continuously since 1912. Batteries of instruments scattered over the ground are able to measure even the subtlest changes. Originally, the data were gathered by intrepid and persistent geologists. Nowadays, much of this information can be relayed instantly and electronically back to the observatory, where computers do their usual job of totting it all up. Tilt meters on Mauna Loa and Kilauea monitor the heave on the ground. They work like sophisticated spirit levels to an accuracy of a tenth of a micro radian. That is a very small tilt indeed. Evacuation bottles take samples of the gases issuing from vents and fumaroles. Levels of sulfur dioxide and carbon dioxide can be measured precisely back in the laboratory. Elevated concentrations signal hot breath issuing from rising magma. It has been estimated that between 100 and 200 tons of carbon dioxide are exhaled every day at Kilauea. This is magnified tenfold at an active eruption site. The breath of an eruption is not only choking but stifling. A network of 60 seismometers records the pulse of the ground. Earthquakes precede eruptions as jitters do a first night. There are global positioning Satellites to record precise position and any changes by reference to satellite standards passing above in the skies. Even clever instruments can measure increase in pressure within the crust itself. A borehole dilatometer operates inside a borehole driven several hundred meters down into a lava pile. The instrument is essentially a bag of oil that senses changes in the squeeze on the sides of the borehole. This meter is so sensitive that one deployed on the flanks of Mauna Loa detected a rise in magma under Kilauea. 80 kilometers away and about 3 kilometers down, the crust must have tightened under the press of the filling subterranean reservoir and squeeze the bag. Other features of the physics of the Earth, such as changes in the gravity and the magnetic field, are measured periodically. Taken together, all these different measurements provide a diagnosis of Pele's temper, and when she finally gives vent to her fury, another arsenal of instruments measures the temperature of her collar. Some of them are thermocouple thermometers, which measure heat directly. Others are optical pyrometers, which convert the color of the erupting lava to a measure of its temperature. At about 1,200 degrees Celsius, lava is white hot. At 1,100 degrees Celsius, it is yellow. Then, it fades through orange 900 degrees Celsius to bright red at 700 degrees Celsius, while the dull red, reminiscent of glowing embers of the Christmas Yule log, is about 500 degrees Celsius. Any color at all would fry you soon enough. The observatory was founded by Dr. T. A. Jagar, who initiated the scrupulous series of observations that today still continue to provide the basis of our scientific understanding. He wanted to quantify the Hawaiian volcanic eruptions. At first, they had been more the subject of gasps of admiration or distressed hand-wringing. Then, through the 19th century, Hawaiian volcanoes came under the scrutiny of scientists who tried to deduce the role of the underworld in their formation. This was helped by the appearance of scientific journals, like the American Journal of Science, in which the results could be published, and the establishment of the U.S. Geological Survey, which could pay an occasional salary. C. E. Dutton published his account of Hawaii in 1884, in which he identified the process of collapse as essential to the formation of calderas. He also recognized the rift zones radiating from the principal shield volcanoes of Mauna Loa, he wrote, so extensive has each and every one eruption of them been that the greater portions of them always reach far beyond the limits of vision, and mingling together are lost in the confusion of multitude. This paints the right picture of the bewildering profusion of vast flows and how they overlap in such a complex and braided way to build a single great structure. Perhaps the giant stack of pancakes was not an entirely appropriate analogy after all, since the pile is built up from smeared dabs rather than sheets. For many years, the definitive account of Hawaii was based on field studies that mapped out individual flows, and that was based on an understanding of the relative ages of the main volcanoes. It was written by the great American geologist James Dwight Dana, who was 77 when his work was published in 1890. He himself had the stature of a Mauna Loa compared with most of his contemporaries, but the eruptions of 1912 and onwards allowed many more physical measurements around the craters themselves. Curiously, Dr. Jagar, for all his pioneering objectivity, was convinced that changes in volcanic behavior were related to an 11.1-year sunspot cycle. He looked to the sun rather than to igneous plumbing here on Earth. His statistics are not now taken seriously, but the observations on which they were based are still used. There is a pattern, but it has nothing to do with the sun. Most important, it is clear that the plumbing systems of the great volcanoes are all separate. They do not originate from a single magma chamber. If they had been intimately connected, movements in the lava fields of one should be obviously connected with events in another, just as a domestic heating system, requires central equilibrium. This patently was not the case. A drain out from Mauna Loa was not necessarily accompanied by a reaction from Halimumiu. With modern techniques, it is possible to distinguish the source magma for each of the volcanoes. Each bears a distinctive signature in the elements it contains, and these elements, especially the very rare ones, known as the rare earth elements, can be measured with precision of parts per billion. Thanks to modern technology, the main volcanoes then are separately connected to the deep underworld. Yet to the casual eye, the rock type making up the lavas looks extremely similar almost wherever you are on the Big Island. When fresh, it is black and fine-grained, occasionally glinting slightly if you turn it in the light. It frequently contains holes or vesicles, especially nearer the surface of a flow, where gas has escaped. Ultimately, it weathers to the gingerbread rock we saw near the waterfall on Oahu. It is called basalt asterisk and is one of the commonest rock types on Earth. There is nothing with which you can exactly compare its texture. Heavy German black bread comes closest, perhaps. The pottery manufacturer Wedgwood went to a lot of trouble to produce a black porcelain called basalt, which is now much sought after. It is certainly easier to collect examples of its natural namesake. You cannot often make much of basalt in the field. However, if you cut a slice from a fresh basalt deposit and then grind it thin enough to see through, you can examine it. Under a petrological microscope, you will then see that it is a mass of tiny crystals, many scarcely larger than sand grains. Basalt is evidently a composite rock. If you turn up the magnification further, you will soon recognize that the most obvious of these minerals is transparent, forming tiny, elongate crystals, shaped like the fine chaff you can make if you rub brittle straw stems between your hands. These crystals are of one of the most abundant minerals in nature, feldspar. Furthermore, they are of a particular kind of feldspar rich in the element calcium, termed plagioclase. A mineral displaying a pale green color makes up much of the space between these prismatic crystals. This second important component of basalt is the dark mineral pyroxene, a compound of predominantly silica, iron, and magnesium. Then there is a green mineral called olivine. The olivine crystals in most basalts are imperfect, lacking clear crystal faces. Gem-quality olivine is known as peridot, which has a subtle green light all its own. Chemists will recognize that the green is the color of the element iron in its ferrous state. When you have studied a few rocks in thin section, these minerals become old friends, and much of their chemistry can be identified just by studying their optical properties, such as their refractive index. But some little black grains between the crystals never become transparent, no matter how thin you cut the section. These are metallic sulfides, usually iron pyrites. In many basalts, the memory of flow is retained in the orientation of the longer feldspars. They seem to blow in one direction, pointing all one way like chaff in the wind. It is easy, then, to imagine this broth of crystals forming as the liquid magma cooled downwards progressively from white-hot, separating out into different minerals, which were then entrained in further flow. Cooling was rapid enough to ensure that the individual crystals had no time to grow large. All was flux. There is an urgency about this rock. When the flow cools even more quickly, there is no time to form visible crystals. A glass is the result. Pele's tears and hair are glassy, the product of the most ebullient phases of eruption, when Pele's irate lava was thrown skywards and froze in midair. Hawaiian natives had an eye for the subtlest differences in the rocks. The lavas on the summit of Mauna Kea are glassy and flinty. They make very good stone tools, since their edges can be knapped to keenness. all around the world, native wit has appreciated the technology implied by such stone. One of the craters near Kilauea is called Kinakakai, literally, the Cave of the Adze, which was another source of superior stone. 4 pestles and mortars, more massive basalt, pohaku, was required. There were also game, stones for rolling, a kind of Pacific bozulu mica, and stone has always been the recipient of carvings or petroglyphs, in Hawaii's case often, pleasantly rudimentary figures with arms and legs akimbo. The basalt was also piled to outline large squares in the ceremonial centers known as heiaus. They are forgotten now, but in the 18th century they would have been heavily populated and cultivated all around. Somewhat forlorn in decline, they are slowly becoming engulfed with scrub and secondary forest. Even the red pigment that results from prolonged weathering of basalt had its use as a dye, a feature that some imaginative entrepreneur has revived so that you can purchase red dirt shirts from many outlets. The Hawaiian Islands were Stone Age homelands at one time, and their cultural possibilities were circumscribed by the potential of basalt. Rock ultimately rules. The story of the volcano is not over when the great shields are complete and the calderas collapse around their summits. The magma reservoirs still have life in them. Late-stage volcanic eruptions are different. First, they are more violent, and they build steep-sided cinder cones, which resemble everyone's first notion of a volcano. Second, they are smaller by far. From high in the air, they look like boils or carbuncles on the flanks of their parent volcano. They are built from a different kind of lava, much gummier than that of the free, flowing tholeiitic basalt. This is the result of changes in the magma chamber, where the liquid mixture has had time to evolve and so produce a more viscous alkali-rich lava. Magma evolution proceeds little by little over several thousand years, as heavier minerals crystallize out and drop slowly to the bottom of the chamber, enriching and altering the composition of the magma that remains. It's a kind of underworld fractionation. The type of rock that results is often described as trachyte and contains abundant crystals of a different kind of alkali-rich feldspar, such as sonidine, rather than plagioclase. The spattered cones can maintain a steeper slope than the fluid flows. There are several cinder cones near Honolulu on the island of Oahu. The Punchbowl crater, standing high above the town, is home to a tasteful monument to the war dead of the Pacific War. The crater floor is now all lawns and plantings, and you would scarcely guess that it was born of a violence commensurate with the conflict it memorializes. Diamond Head, which bounds Waikiki's western edge, is wilder, making a feature against the sky, its steep side supporting rather miserable scrub. This is the drier side of the island, and displaying ranks of rough, brown volcanic rock beds, plunging obliquely towards the sea. Some spectacular surf gets up off Black Point. A few kilometers to the west, Hanuma Bay is a former cone breached by the Pacific, shaped like a deep bite into the coastline. It is one of the few places where the novice can swim over corals by a close and protected shoreline. It has become a favorite tourist stop as a result, and the corals have not benefited from the abrasion of 1,000 flip-flops. But you may still get a glimpse of Hawaii's famous incarnation of Lono, god of rain, peace, and agriculture, a little bluish fish called Lumahamaniknaquapue. On the way down to the bay, you pass much clinker-brown volcanic rock in the cliffs. I thought my eyes were deceiving me when I examined this rock closely, because it quite obviously contained chunks of white coral amongst its volcanic matrix. Bleached by time, the coral lumps seemed suspended like figs in a cake. Evidently, the explosive violence had been sufficient to punch a hole through a fossil reef, and the smashed coral got caught willy-nilly in the blast. There are 3 kinds of sand in Hawaii: black, white and green. The commonest kind is white sand, the staple feature of those brochures. Promising paradise. It creates the beaches on the older islands, always behind. The fringing coral reefs. It constitutes the seafront at Waikiki and at Kahana. On Maui, coconut palms really do tower over these ivory sands, making little puffs of shade. Visitors like myself are accustomed to white sand being, well, sand, that is, finely rounded quartz such as you find on the beaches of New England, New South Wales, or Nuki. Hawaiian sand is utterly different. It is comminuted coral and algae, the broken detritus of 100,000. Storms washed up against the land. It has been churned to fineness in the massive winter breakers upon which surfers perform their improbable feats. It sticks to you. Quartz sand brushes off as you dry, but coral sand seems determined to add itself to your skin. It is light stuff, startlingly white, not rock at all. It is curious to experience its opposite just a day's journey away. On the southern shore of the Big Island, Punaluu Beach is backed entirely by black sand. The beach seems to suck light in rather than reflect it. Take a handful of this sand and smear it out so that you can examine it under a hand lens, and it is easy to see that the sand is composed of tiny, smoothed out fragments of glassy basalt, which are quite shiny when they are moist. The grains have something of the luster of black pearls. This sand is from a geologically young beach, freshly ground from the newest part of the island. There are no coral fragments offshore to dilute its dark purity. On this particular beach, huge Hawaiian green turtles bask. Perhaps they appreciate the warmth that the black sand quickly picks up from the morning sun. The third sand color is a pale olive green, and it is much rarer. It occurs near Ka, La on the Big Island, a promontory that has the distinction of being the most southerly point in the United States. This bleak shore is where older flows, originating from Mauna Loa, confront the full force of the Pacific Ocean. It is a slightly spooky place. An oddly uninterested man in an information center, which contains very little information, offers to guard your vehicle for a small fee, from whom there is hardly anyone around. The only trees are stunted and pressed downwards, reaching away from the sea. Near the seas, edge little pockets of green sand are tucked among the rocks. If you scoop up some of this material, a hand lens will reveal that each grain is a transparent, crystal, rounded, green like bottle glass. These are olivine crystals. They have been concentrated from the eroding lavas in this special place by the particular combination of sea and wind winnowing away all other minerals. This variety of sand is the most superficial aspect of the aging of the islands. The greatest and newest island still lives and grows, with the red ichor of lava streaming through its arteries. The other islands are all about erosion and decay after the death of the volcanoes that gave them substance. Maui lies northwest of the Big Island and is the youngest of the other islands. Maui may perhaps be dead, but it feels as if the corpse is hardly cold. Erosion is still in its early stages. Charcoal recovered from soil beds buried by late lavas can be radiocarbon dated to show that there were large eruptions not much more than 1,000 years ago. In 1786, a Frenchman called La Palaus mapped a bay near the southwestern tip of the island, which had already been obscured by fresh lava when the navigator George Vancouver passed the same spot. 7 years later, this eruption originated from the end of a rift zone and could conceivably revive once more. Maui is an amalgamation of two volcanoes, West Maui to the northwest and Haleakala to the southeast, connected by a lowland known as the Isthmus, an area scattered with ancient dunes. The shield of West Maui was complete 1.3 million years ago, while the The main shield of Haleakala was built up layer by layer about 700,000 years ago. Later, explosive eruptive phases followed and pockmarked the landscape with cinder cones. Some of the original form of the volcanoes is preserved. On the wetter eastern side of Haleakala, there are thousands of cascades that are eroding deep valleys. But on the summit basin it can seem as if the acrid smoke faded away only yesterday. The scale is vast. The floor of the basin is more than 610 meters, 2,000 feet, below Kalahaku Overlook, and the highest cinder cone within it is 180 meters, 600 feet, high, but by a natural trompe l'oeil contrives to look much smaller. The cinder cones are arrayed in a range of red, some raw and startling, others like old blood, that were painted on the rocks as the result of alteration of the lavas by steam and volcanic gases after the main eruption. The cone is only the accumulation of the coarsest scraps of lava coughed up during the eruption, built up from tossed volcanic bombs and gobs of lava tumbling down the growing slopes. Larger bombs still lie around on the bluffs. They are often rounded by their passage through the air, and where they are broken, their glassy skins prove how quickly they cooled. Much of the finer stuff would have been carried away by the wind as ash. The last blast left craters in the top of the cones, like raw carbuncles. Oahu is older again. It grew above the sea nearly 4 million years ago. It, too, is an amalgamation of two volcanoes, but the dual mountainous spines of the island are the wreckage of the shields that once made it. The mountains are only minutes away from the urban anonymity of Honolulu. You can drive into them along the Interstate Highway 3, a road that Senator Inouye managed to get built to connect the two strategic bases of Pearl Harbor on the leeward and Kanaho on the windward shore of the island. Allegedly it was the most expensive road in the world. After emerging from a tunnel, you seem to fly alongside the most precipitous cliffs. Yet these mountainsides are carved and grooved with valleys, which are so steep they seem to be draped over the scenery. No matter how sheer the slope, everything is covered with a green blanket of ferns and trees. Within minutes the view is wrapped up in clouds and it begins to pour with rain. Mark Twain perfectly described this eroded volcanic panorama in April 1866. It was a novel sort of scenery, those mountain walls. Ahead the mountains looked portly swollen, if you please, and were marked all over, up and down, diagonally and crosswise, by sharp ribs that reminded one of the fantastic ridges which the wind builds. Of the drifting snow on APLAIN, the whole upper part of the mountain, looking something like a vast green veil thrown over some object that had a good many edges and corners to it. Twain was free with references to Eden and to paradise in his letters. But this island, like all the others, is doomed to return to the sea above which it once had the temerity to rise. Is paradise necessarily eternal? Twain was right to use the analogy of hidden struts propping up the improbably steep mountain slopes. They are actually partly bolstered by the vertical supports of basalt feeder dikes. These once supplied the great lava flows that built a shield volcano, long since ruined and dismantled by time. Just as reinforced concrete pillars sustain a soaring tower, dikes act as struts, supporting the beetling precipices. The steepest drop of all is at the Pali. Look out. You can drive there easily enough through forested slopes, but when you reach the top, the prospect westwards into the sheer drop of the Kolau caldera is enough to make your legs go peculiar. 1,000 tourists try and fail to capture the view on film. It was here in 1781 that king, Kamehameha I, known as the Great, drove 300 warriors of the king of Oahu over the cliff to their deaths, thereby uniting most of the islands under his rule. A highway named after him runs around the island. If you follow King Kamehameha's road close along the windward shore of Oahu, You see something of the island as it was before the appearance of the first tower block. In spite of the dominance of secondary vegetation, paradisical thoughts come easily. It is a lazy-feeling place, green and lush, with open verandas dotted along an almost continuous coral sand beach. There are delicious bananas and papaya and fresh coconut milk to drink. I thought of the medieval earthly paradise, an alleged island of perfection and immortality located far out to sea. It is actually marked on the Mappamundi. In Hereford Cathedral, located near India in that eccentric geography. Perhaps the memory of this ideal place does linger somewhere in our psyche, a remote island with coconut palms fringing it, like hair round a tonsure, and coral reef surf delineating a line no more than a swim away from shore. Seems to chime with an idea of escape from the worries of life into primordial calm. Hawaii was made this way, and the causes are wholly geological. Along the shore, cliffs of bedded lava of the Ko'olau caldera sometimes squeeze the road into a narrow belt beside the sea, without room even for a dwelling. At Kualoa, a marvelous vertical-sided valley almost reaches the sea. Offshore, there's a stack known locally and appropriately as the Chinaman's Hat. This side of Oahu, far from being the product of slow and peaceful weathering of the crust, was the result of a catastrophe. The steep topography was a consequence of an enormous collapse of the eastern half of the original Ko'olau volcano. It slid off the edge and into the Hawaiian, deep as if it had been amputated, creating a tidal wave of almost inconceivable power. This event is known as the Nuuanu Slide, nor is it unique. On the island of Molokai, the eastern volcano was virtually bisected. When its northern flank collapsed into the Pacific Ocean, the Great Slide left a scar that now makes the sea cliffs along the northern shore, and they are possibly the most spectacular cliffs in the world, 24 kilometers long and rising vertically to 11,000 meters. Molokai is but a sliver now. When their volcanoes die, islands perched in the midst of an ocean begin to founder. The most northwesterly, most eroded, and oldest island is Kauai. This is where you must go to see the maturity of a volcanic island. It is the gutted remnant of a single, huge volcano, which still sits at its center, 1,576 meters, 5,170 feet, high and almost always veiled in cloud. Although much of the island has been weathered down to soil and is heavily cultivated, the mountains remain extraordinarily rugged and remote. The Ilakai Swamp has the reputation of being the wettest place on Earth, and it is so isolated that relatively few interloper plants have yet established themselves there. It is one of the last havens for native birds. There are still twittering honey creepers among the lichen-clad branches of the ohichai trees. There were massive slides on Kauai, too, the largest of which left as its legacy the green-clad, inaccessible and mighty cliffs of the Na Pali coast. The movie Jurassic Park set its dinosaurs down here. The forbidding cliffs mean that no road can circumscribe the island, and part of it remains inviolate. From the viewpoint, at the top of Na Pali, you can look down on helicopters taking tourists along the cliffs. From this height, these machines look like mosquitoes skimming alongside the hide of a great, wrinkled elephant. It is hard to believe that, in former times, even the most remote valleys on this coast supported native Hawaiian villages. Kauai is dissected by huge, eroded valleys. They are ripping into the volcano's heart and will one day strip out its lava flows and dikes. The island will not be ground down so much as wasted away. You can get some idea of the rate at which this happens at Wailua Falls, where twin 25-meter waterfalls plunge over a massive lava flow. This resistant flow is underlain by a rubbly-looking flow that is clearly more susceptible to erosion than its overlying neighbor, thus becoming continually undermined. Pieces of it eventually break off and fall into the waters below, ensuring that the precipice remains sharp. Hence the falls fitfully retreat, and a gorge grows seaward of them. This gorge was excavated through some of the later, stickier lavas that are a couple of million years old. Since the gorge is between 3 and 5 kilometers long, very approximately, the lavas retreat in the gorge at 1.6 kilometers per million years. There are all kinds of complications possible. For example, the relative sea level has not been stable, but this is probably about the right order of magnitude. We can imagine that 20 million years or so would have to elapse for similar erosional processes to traverse the island. When the island finally reaches close to sea level, there will no longer be sufficient elevation to produce the rainfall that drives the erosional machine. The island will be ready to sink slowly beneath the waves. The most spectacular valley is Waimea Canyon, which has been described as the Grand Canyon of the Pacific, a description that is woefully inaccurate as far as the geology is concerned. However, the epithet grand is unquestionably apartment, for the Waimea gash has opened up into lavas that reflect only a geological instant compared with the billion years or more of strata that are on display along the Colorado River. But what a display this brief moment of geological history has given us. The Waimea River cuts into two series of lavas and their related volcanic rocks. The canyon is at least 22 kilometers long, 1.5 kilometers across, and up to 228 meters deep. A road runs up its western side, so that if you stop regularly on the way upwards, you are vouchsafed intermittent views across this vast dissection through a volcano, and every view you have is a surprise. The sides of the valley are striped with the flows that give them a spurious resemblance to the strata of Colorado. There are pinnacles and ridges, often wisped in cloud. You wonder that there could be so many shades of red, which change and change again, with the angle and intensity of the sun. The slopes are dappled with reflections of the clouds, which enhances the drama of it all. As you get higher, native vegetation takes over, so a prospect might be framed by the dangling leaves of the beautiful koa tree, each leaf a gently curved, trembling sickle. The course of the river is shown only by a thin line of green. Impossibly far away in the base of the valley, how could such an insignificant trickle grind away such a mountainside? Then you notice isolated buttresses of weathered lavas, some beginning to totter. Where there have been cliff falls and landslides, the evidence of debris lies before you. In your mind's eye, the whole process can be imagined as in a cartoon where the speed absurdly redoubles. You envisage the rise of the Shield volcano, catastrophic collapse of its sides, and initiation of the rift zones, then the blasting of late lava cones and the inroads of streams into the caldera, and finally the rotting of its lava by the elements and vegetation and its eventual erosion to a stump of its former mightiness. It is more challenging to imagine the sheer weight of these vast volcanic constructions on the ocean floor. Once they have ceased being built, they start to sink. This is because of the kind of isostatic adjustment that was explained above. Everything is against the survival of the islands. Once born, they struggle above the waves, only to be assaulted by the elements, but they are already sinking under their own mass of basalt. If this is paradise, it is a kamikaze paradise. There are messengers from the underworld preserved among the lavas. Occasionally, geologists have discovered places where the contents of the magma chamber itself survive. Because they cooled more slowly, these rocks are composed of large crystals, which catch the light on a fresh example. But they are similar minerals to those in the basalts: plagioclase, feldspar, and pyroxene, and some olivine. These lend the rock a comparable dark color. It's heavy and oppressive in a hand specimen, but lovely and lustrous black, and gray when polished. It is known as gabbro, and is thought to form the lower layer of the oceanic crust at about 4 kilometers depth and comprise a layer up to 6 kilometers thick, making it one of the most abundant, if least recognizable, materials on Earth. Then there are small boulders of other kinds of coarse-grained rocks, much rarer than gabbro, brought up from the innards of the Earth in the explosive events that accompanied later phases of eruptions. These are envoys from the most alien parts of the underworld. They are collectively known as xenoliths, Greek for foreign rocks, and they are indeed out of place on our green planet's surface. Their natural habitat is in the nethermost kingdom of Pluto, from which they have been abducted by the pull of eruption. They look like rocky chips or triangular to spherical bodies dotted within the main mass of basalt. They often weather to a different color, a leprous brown, as if distressed by their journey to an alien sphere. They rot readily. Most are varieties of peridotite, and it will be recalled that peridot is the more glamorous name for the green mineral olivine, so coarsely crystalline olivine is an important constituent of this rock type. Varieties of peridotite are distinguished by their mineral composition. For example, dunite is a peridotite, which is virtually all olivine and a dense, dark green in color. The most important variety is called lherzolite. Its list of constituent minerals includes a lot of olivine, but also feldspar and pyroxene, and often small quantities of 2 other minerals, garnet and spinel. These last give a clue to the conditions from which these strange fragments were recruited, for they form at high temperatures and pressures. These superficially unimpressive fragments of rock are incredibly important, for they provide us with just about the only direct evidence of what rocks are like deep, very deep down there. They have been hijacked from the mantle. The inner earth is green, too, but a rich green such as is seen on the leaves of climbing plants in the rainforest, the green of the forest floor. At Manoa Falls, incredible though it may seem, these little chips are what most of the earth is made of. The basalt lavas of Hawaii are derived from the selective melting of such mantle rocks. As a whole, rocks of this type are referred to as mafic because of the importance of magnesium and iron in their composition. Chemists appreciate the subtleties of differences between their various species, but to us the extraordinary thing is the differences that appear once the breaking and dissolving powers of rain and sun and plants have wrought their metamorphosis. So much variety wrung from a seemingly uniform raw material spewed from the depths is a wonder worthy of an earthly paradise. Putting the facts of the Hawaiian chain of islands together, what can be deduced? First, think about the age of the islands and the state of their decay. The youngest island is Hawaii itself, the Big Island, erupting steadily still, building itself from its deep magmatic wells. Shields still turned to the sky. Except to the southeast of it, a new island is growing beneath the sea and will one day take its place. Even within the Big Island, the younger volcanoes are to the southeast. Alas, the great shields afford no protection from geological inevitabilities. Maui to the northwest of the Big Island is extinct, but hardly cold. It may still have life in it. Its recent history is written all over the landscape. The small island of Lanai was once part of it. Following the same line to the northwest, Molokai and the Oahu are still older, more worn down, with major slices from their sides collapsed into the deeps, presaging their ultimate ruin. The edges of the old calderas are now fantastically fluted by erosion. A lot of the volcanic rock that was once black and tough is weathered soft as cake, and is much the same color. Thence, northwest again to verdant and rich Kauai, the oldest island of all, gouged by chasms of erosion digging towards its very heart. Geologists can see into the deeper layers of volcanoes thanks to this progressive erosion. As an aside, I should not forget to mention Niihau, west of Kauai. This is the island that nobody can visit. It is known locally as the Forbidden Island. Can this be where forbidden fruit still grows? Is this the real Garden of Eden? It is easy to see it from the Napali Heights on Kauai. It is a small island representing just one flank of an ancient and decayed volcano, the rest of which foundered into the ocean. It is privately owned by a family called Robinson, who forbid access to outsiders. Of course, there is nothing like the word forbidden to make you wish to go to it. It is now the last bastion of the Hawaiian language. McDonald's has no franchise there, and it is beyond the dominion of Colonel Sanders. Fish is still farmed in the traditional way. Its total privacy has guaranteed the survival of a culture which is blended with the American way elsewhere, to the point where the inquiring visitor begins to wonder what, if anything, is authentic. There is such a thing as an authentic hula dance, but it is not the one you see in the Hilton Hotel. And even grass skirts did not originate on Hawaii. The Robinsons have taken on the role of the traditional lord and thereby kept this island race alive, the honey creepers of Homo sapiens. The islands age on a line from southeast to northwest progressively and regularly. Each island was created by lava, but then the source died. One way to encompass these facts might be to propose that the heat source of the volcanoes migrated southeastwards, one by one. Such was an early explanation. But what if the tables were completely turned so that the fiery source of magma was fixed, and instead it was the volcanoes that moved? Or, to be more accurate, crust passed over a fixed heat source, so that its volcanic progeny erupted in sequence in harmony with this movement. As long as a favored volcano lurked above the source of magma, it would grow and grow above the sea, flow by flow, eventually forming a shield like Mauna Loa. This would be how islands were created. Life would colonize the new land, seeded from the next oldest island. Isolation from the neighbors might then engender another endemic species. Thus, even biological richness might be accounted a geological phenomenon. The effect can be simulated more in spirit than in truth by moving a sheet of thickish polystyrene foam a few inches over a lighted candle carefully. I should add, and outdoors to avoid any toxic fumes. When I tried this experiment at the right speed, the sheet did not simply melt in two, rather, it became corrupted with blobby, burn holes. In an approximate line, some large, some small. Islands in the negative, you might say. Then, as the tectonic conveyor moved the plate onwards, away from the heat, the island would begin to founder slowly under the intolerable load of its mass lava layers. The crust would adjust to the weight loaded upon it. Unstable slopes would break along faults, and once in a few dozen millenniums, huge slides would collapse and tumble to the same seafloor, above which the island so impertinently rose. Another of these catastrophes may happen even now, carrying a slice of paradise to oblivion. The moving crust is part of one of the great tectonic plates of which the Earth is composed, the Pacific Plate. Hawaii is almost in the middle of it. The fixity of the magmatic heat source supplies a wonderful test of the reality of plate movements, because it provides a fixed marker on this peripatetic Earth of ours. In a world that shifts, here is an igneous reference whose fidelity has been tested over millions of years. If the theory is right, it will be relatively easy to calculate the rate of movement of the Pacific Plate over the volcanic source. The first direct measurements using modern instruments were made on Maui at Science City on Haleakala. It seems that the Pacific Plate moves northwestwards at about 10 centimeters or 4 inches a year. Hair grows much faster cumulatively. This is all that is needed to throw up new crust, make an island, and move it onwards to begin its destruction. What are the heat source that has been so steadfast while invading species and, belatedly humankind, have settled upon its productions? The lumps of peridotite preserved as xenoliths, those strange rocks so far from home, give evidence that there is more or less direct plumbing down into the depths, way below the crust itself. The persistence of the site suggests a permanent flow of energy coming from far inside the underworld, from which strange emissaries with strange names like Herzlite bring news of alien spheres. They come from a high-pressure world, brought upwards by what has been called a mantle plume. Despite the name, a plume is not liquid. At great depth, solid rocks behave in a curious way. A plume is a high-energy, hot jet of solid rock that rises through the mantle. Many geologists believe that plumes originate at a depth of nearly 3,000 kilometers. Where the plume hits the crust, it is called a hot spot. The paradise of the Hawaiian Islands is thus the product of the most direct route to Hades we have on Earth. Heat is lost from the interior of our planet by means of these ducts, which maintain the same position for millions and millions of years. Not all the magma that erupts as lava on the surface, however, has streamed directly from unfathomable depths. Much of it is generated by heat melting of peridotite. Strictly speaking, its variety Herzlite at about 100 kilometers below the surface. The kind of magma that is produced is dependent on the exact conditions of temperature and pressure, which change with depth. This can be simulated by melting experiments carried out inside special pressurized apparatus in the laboratory, a kind of pressure cooking. The peridotite is partially melted to generate the most stable magma under the ambient conditions of pressure and temperature. Basalt magma is the result. The magma then seeks out weaknesses above, and once the ocean floor is breached, the growth of the shield is relentless. A magma reservoir forms within the growing volcano at 2 kilometers or so below the surface, which is where the density of the magma matches that of the surrounding rock. Magma is delivered into the chamber in pulses. Its upward passage has been monitored by measuring the small earthquakes generated during its movement. A newly cooked stew of magma can erupt just a month or so after. It starts to rise in the mantle. When the new batch arrives in the magma chamber, the ground draws its breath and the tiltmeters register. Then comes the exhalation of lava. Thus goes the respiration of the living earth as it generates new crust. The detailed structure of Mauna Kea on the Big Island is currently being investigated by means of a deep borehole in the old airfield at Hilo, which is scheduled to reach a depth of 6,000 meters. The lava at this level should be 700,000 years old. It is hoped that this deep probe will reveal some of the secrets of the mysterious mantle plumes. The time represented is long enough to record the shift of the volcano from off the center of the plume. There is a lot of clever science that can be carried out on the fresh, unweathered rocks recovered from the borehole. Very precise measurements of abundances of elements like barium show when the later alkali phases of eruption are reached. Other rare elements, like neodymium, exist in more than one isotopic form, the ratios of which can provide a measure of the depth from which the flow material may ultimately have been derived. These are like xenoliths, but at a molecular level. Hidden messages from the underworld that require the most sophisticated tools of modern science for their translation. So the increasing age of the islands towards the northwest is now readily explicable as the ancient track of the moving Pacific Plate. Modern studies suggest that the Hawaiian hotspots are probably paired. There may well be two of them side by side. In spite of their common cause, rare earth elements tell us that each volcano is in detail and individual. Every version of magmatic plumbing is unique. The logic of the plate tectonic explanation for islands demands that northwest again of Kauai, there must be further islands still, older expressions of the hot spots. So it proves to be. There's a whole chain of islands, their rock outcrops now effectively submerged, aligned along the Hawaiian Ridge. Northwards again there is a train of submerged volcanic cones known as the Emperor Sea Mounts that extend all the way to the Aleutian Trench at the edge of Asia. Once deep beneath the waves, sea mounts are protected from further major erosion. In total, this chain of volcanoes extends across more than 30 degrees of latitude. Drawn upon the sea floor is a line of geological time, burned into its very fabric. There were still dinosaurs alive at the time the first islands over the hot spot were erupting. It has taken more than 70 million years to build this memorial, recording the slow march of plates across the face of the Earth. For once the cliché is true, this trace is literally a graphic illustration of the span of geological time. Recall that everything I have described in the Hawaiian, CHAIN, FROM, the birth of an island, to its EROSION, HAS taken less than 10% of the time recorded by the complete chain of islands related to the same hot spot. Now, multiply the time taken for the formation of the entire chain of islands by 10, and this will still be only about 1/6 of the age of the oldest Archean rocks on Earth. To put it another way, imagine a plate spinning about 6 times around the whole world with a speed not much exceeding the rate at which our fingernails grow. This is a more realistic, more graphic way of signifying the sheer immensity of time involved in Earth history than the 24-hour clocks or running tracks or the other commonly used analogies that attempt to bring geological time down to a domestic scale. To collapse time by whatever analogy is to misunderstand it. You have to think hard in order to appreciate the geological scale. As John Keats said, time, that aged nurse, rocked me to patience, asterisk. The islands of the Hawaiian chain to the northwest of Kauai are mostly atoll circular reefs surrounding a warm lagoon. The volcanic islands themselves may have sunk below the waves, but the corals that are ultimately founded upon them continue to live close to sea level. Charles Darwin himself, when he was naturalist on the voyage of HMS Beagle in 1837, made observations that allowed him brilliantly to deduce an explanation for atolls, as in the reefs that form a clear white line along the shore of Oahu coral. Growth begins close to land in the early stages of the life of a volcano. Most reef-forming coral can only grow in shallow water, since the algae that live inside the tissues of massive corals need light. Without it they fade and eventually die. And, of course, the shield volcanoes are surrounded by deep water, so corals may only perch on their margins. As the islands sink, the corals grow upwards. They are as vigorous as forest trees, built on the firm base of their own dead skeletons. The coral animals comprise no more than a skin of living tissue. When the island eventually subsides below the waves, the corals keep abreast of sea level, and they continue to fringe their vanished host. Their waste fills the lagoon inside the reef, white sand that reflects the skies so perfectly as to produce the most aquamarine water in the world. It is astonishing how much debris a healthy coral reef can yield, for as much or more as ends up in the lagoon is tipped seawards to buttress the whole structure. Darwin's scenario remains definitive. In 1910, R.A. Daly added further observations about changing sea levels that would have inevitably been associated with the glacial epoch during the maximum extent of the glaciers in the northern hemisphere. So much water was locked up in ice that global sea level was greatly lowered. Then surf would have renewed its onslaught on some of the volcanic islands. So the actual history of the coral reefs on any given island or atoll might prove to be rather complicated, depending on the relative trade-off between sea level and subsidence rate. There will be places where the sea deepens so rapidly when ice sheets melted between glacial pulses that reef construction was perforce abandoned, as in the battle that happens on every sandy beach. In summer as the tide comes in, when small children vainly pile sand against implacable waves to protect their carefully constructed castles. In other sites, a coral reef may have grown when sea level was high, only to be stranded as a bleached fossil when the waters once more withdrew. These reefs are like ghosts of the real thing, wan, skeletal, and retaining no trace of the brilliance of marine life. But the intricate lattices of the corals are still unmistakable, even in petrifaction. There are several of these bleached reefs on the island of Molokai, which has probably stopped sinking. Eventually, however, steady and unstoppable plate motions carry any island beyond the tropics to a place where corals cannot grow. In higher latitudes, they are preserved only as fossils on the sea mounts where they once prospered, such as the end of Paradise. Plate motions provide a marvelous, yet simple explanation for a range of apparently disparate facts about the Earth, several of which have been the subject of speculation for more than 150 years. The march of erosion north, westwards through the Hawaiian Islands, and the ever-subtly birth of new volcanoes, the prolific endemic species on those islands, the line of sea, mounts and atolls and volcanoes, of which the Big Island forms the largest, and the latest, Pele's fury and her subsequent quiescence, even the colors of the beach sands, they are all explicable by a combination of hot spots asterisk and the movement of the Pacific Plate. Can there be a more gratifying example of how plate tectonics has transformed the way we look at the world? Part 3. Oceans and Continents. The Hawaiian Islands are remote. It is hard to appreciate quite how far away they are from any continent, when an aeroplane can whisk you there in a few hours from San Francisco. As you look through the cabin windows at endless blue water, time seems to collapse, hours blur, yet all the time you pass over the vast and apparently featureless Pacific, you are also traversing an incalculable stretch of basalt, down, far below the waves, into the dark abyss where no light reaches except the luminous flashes of deep-sea organisms. The sea floor is dressed in sediment, but this is only a thin blanket, atop 5 kilometers or so of basalt. If some terrible explosion in the sun were to vaporize the seas and blast clear its sedimentary top dressing, the Pacific hemisphere would be black, the dark, matte signature of basalt. The area, floored by varieties of this igneous rock, covers about 2/3 of the Earth's surface. It is invisible to a passing satellite because this is an area that coincides exactly with the major oceans. Basalt provides the lining of the basins that cradle the seas. There are 363 million square kilometers of sea floor. There is a lot of basalt in the world. The depth of much of the ocean floor lies at about 10,000 to 16,000 feet, approximately 3,000 to 5,000 meters. It has been observed that we know more about the topography of the moon than we do about some parts of the ocean floor. It is an extraordinarily difficult place to reach. Bathyscapes are designed to withstand the enormous pressures that come with depth. They are, like small, riveted coffins of steel, lowered for hours into the dark. Modern successors include the submersible vessel Alvin, operating off the research ship Atlantis. Few people have been privileged to make the journey to the deeps, and until a few years ago our knowledge of the ocean floor was negligible. Anything could hide there. One of my early cinematic memories is going to see Jules Verne's 20,000 Leagues Under the Sea with James Mason playing an obviously deranged Captain Nemo, Latin for nobody. What stays in the mind about this film is not so much the jerkily animated giant squid as the sheer mystery of the depths. When Edouard Seuss was writing not long after Verne, and a little more than a century ago it was Still possible to imagine whole continents founded upon the ocean floor. The lost land of Atlantis paradise, even. The dredging of samples was technically difficult. Maps made by soundings were hardly possible. The greatest single advance in the 19th century was the voyage of HMS Challenger, the first ship equipped for and dedicated completely to oceanographic research, which steamed out of Portsmouth in December 1872. Challenger made thousands of measurements and collected an equal number of samples. Most of what was brought up from the ocean floor was just mud. Soft sediment is the easiest thing to collect from a simple dredge. The chances of picking up a good rock sample are about the same as catching a fish with a pair of tweezers at the end of a long pole. The ubiquity of the basaltic underlay was not at first apparent, but the Challenger did discover something of the ocean's extremes. On March 23, 1875, near the island of Guam, more than 5 miles of sounding line were run out before the bottom was reached. The crew did not know what they found. We now know that. It was the first sounding of an ocean trench, part of the Mariana Trench that forms part of the marginal zone of the Pacific. Not far away is the deepest spot in the ocean, 11,034 meters, 36,200 feet, deep 6.85 miles. In January 1960, the famous Swiss physicist and daring doer Auguste Piccard descended, in a bathyscaphe of his own design, Trieste, to the bottom of the appropriately named Challenger Deep. It's worth remembering that it was only 9 years later that footprints were first left on the moon. Robert Kunzig, in his book, mapping the deep, points out that Mount Everest tipped upside downward, tucked comfortably into the Challenger Deep, leaving room for a minor Alp on top. Nonetheless, it is interesting that the tallest mountain and deepest depth are of the same order of magnitude, with mean sea level providing the zero calibration. This may not be a coincidence. Challenger also made the first reliable measurements on one of the other great features of the ocean. Near the middle of the Atlantic, the soundings unaccountably diminished. Depths of considerably less than 2,000 fathoms, 3,660 meters, were commonly encountered. The conclusion that there was a mid-oceanic shallowing seemed inescapable, if unexpected. To visualize this as a mountain range was more imaginative. We would now know these measurements were a consequence of peaks aligned along the mid-ocean ridges. But at first, images of foundered lands came to mind. Could these represent land bridges that had once connected the continents? In Das Antlitz, der Erde Edward Seuss had written, this contrast between the outlines of the ocean basins and the structure of the continents shows in the clearest manner that these ocean basins are areas of subsidence reproducing, but on a far larger scale, the subsidence with which we have become familiar in the interior of the continents. His italics, for Seuss, the ocean floors were but foundered continents. He reasoned that the processes that generations of geologists had so meticulously investigated on land should still apply even in the abyss. The realms of Neptune and Jupiter observed the same rules, at least according to one of the greatest geologists at the end of the 19th century. At the time that Seuss wrote, this uniformity of concept must have seemed what is now termed good science. The fundamentally different geological nature of the ocean basins was only slowly accepted, but it is always easy to be wise after the event. It does Seuss and his contemporaries more justice to realize that they were seeking to apply general principles in a general way, a reliable scientific practice in most circumstances. They would no doubt have answered any potential critics that they were observing good Lyellian principles to infer, from the secure basis of processes you understand to ones you wish to investigate. If we can observe subsidence in the Bay of Naples even in historic times, then is it not reasonable to anticipate the same processes elsewhere, even if it is difficult to make the necessary observations to confirm what you surmise. Lost continents were expected, and here they were. As for the composition of the ocean floor beneath its sedimentary covering, direct evidence from dredging was elusive. It was only samples from mid-ocean ridges that were relatively easy to gather, for the simple reason that sedimentary cover is thinner there. Currents sweep away a thin dusting of sediment in many places. What was retrieved, of course, was basalt. On occasion, other rock types were recovered from different ocean floor sites. That served to confuse the issue. More than 20 years ago, when I was a new boy at the Natural History Museum in London, I received a sample, dredged, I believe, from the deep Atlantic. The samples were black shale, and on the shales were some ancient fossils called graptolites. They were instantly identifiable as of Ordovician age. Had they been retrieved from the crust of the ocean, they might have caused a major problem for plate tectonic theory, since all the crust should have been much younger than Ordovician. Under the lens, however, the pieces of rock showed the remains of a crust of marine creatures. The blocks must have been lying around on the sea floor, just waiting, as it were, to be dredged up. A little more research work revealed the likely source of the shale as a smallish area of New York State. It is likely that the fragments were ballast, taken on board to wait and empty hold, a common practice in the days of sail. Jettisoning the ballast for whatever reason showered the sea floor with an alien load. There are other rocky strangers out there, granite boulders rafted by ice flows from the far north, foundered blocks slumped from the edge of the continental slope. It is not surprising that the basalt underlay was not immediately obvious. The development and application of seismic methods, especially in the 1950s, had an effect upon our knowledge of the Earth's anatomy comparable with that of the discovery of X-rays on the diagnosis of disease. Seismics provided a way of peering into regions where eyes were useless. Nature provides seismic information in the form of earthquakes, but these are not focused necessarily in the areas you might want to explore. For the investigation of the structure of the ocean floor, timed artificial explosions, often dynamite, were set off from a shooting ship, and the pulses so released probe the deep layers of the ocean floor. It is necessary to know the water depth fairly precisely for the method to work, but that can be obtained by sonar, where there are changes in the composition of the rock layers. These seismic waves should be reflected in different ways. A receiving ship some kilometers away from the shooting ship would then pick up all the consequent signals. The timing of return signals can reveal the thickness and characteristics of the rock layers traversed. Different kinds of rocks are able to transmit waves at diagnostic speeds. The calculations involved are not complicated as calculations go. However, it is important to know what type of waves are being recorded. The several kinds of waves are conveniently distinguished by mnemonic capital letters. P waves are the first to arrive. That is, they travel fastest. These are push-pull waves analogous to sound. Waves, in which each particle moves back and forth as the waves propagate. Then come S-waves, shear waves. In this kind of wave, every particle moves up and down. If you lay out a longish rope along the ground, holding one end, and then shake that end vigorously up and down, waves of this kind travel along the rope like shivers. P and S waves do different things. P waves can travel through liquids, for example, which is something that S waves cannot do. So this is like having more than one kind of X-ray at your disposal, capable of seeing more than one kind of internal organ. Later still, long period or L waves arrive at the receiving station. These are surface waves, confined in their movement to the crust. They have different characteristics again, notably that they travel further more strongly than either. P or S waves asterisk. The instrument that measures the arriving effects of an earthquake or explosion, natural or artificial, is a seismometer. The measurements are recorded on a seismograph, usually a continuous paper log of the intensity of seismic activity, scratched by a needle or a light beam onto a rotating drum. Early instruments often had to be tuned to receive a particular frequency, but modern broadband instruments can measure and record the whole gamut of amplitudes and frequencies within the same black box. They listen to the music of the earth. Amplification of the faintest signals is now routine, including those that have traveled through the innermost core of our planet. The statement that the main refracting layer beneath the sedimentary cover has the capacity to transmit P waves at 5 kilometers per second will now, I hope, make sense. This is a velocity figure appropriate to a dense, iron-rich igneous rock like basalt, and it is almost ubiquitous in the ocean basins. It is underlain by another layer with a velocity of 6.7 km/cc appropriate for gabbro. The seismic reflection profiles tell us also that the oceanic crust is thin, no more than 10 kilometers thick, and in places half that thickness. By contrast, the crust under the continents is up to 40 kilometers thick, around 24 miles, and always much thicker than under the ocean basins. This is, quite simply, the most important distinction on the face of the earth. Edouard Suisse did not know it, but Arthur Holmes did. The fundamental and invariable distinction between oceans and continents was essential to seeing the physiognomy of the world drawn in plates. The earth can be divided into basalt and the rest. Not that a ubiquitous basalt underlay is the only interesting thing about the ocean floors. As we shall see, its sedimentary cover has provided evidence crucial to several other important scientific advances. At the time of writing, the ocean floor has been core sampled at more than 1,000 sites by the Ocean Drilling Program. The technical problems and expense of this kind of research mean that it has to be funded internationally. Sea time is always one of the most expensive items on any project budget. Since January 1985, the Ocean Drilling Program has recovered almost 160,000 meters of drill core, much of it sedimentary, from the deep oceans. It is sobering to compare this with the scattered recovery of odd rocks from dredges at the time of the first Challenger. The Deep Sea Drilling Program ship was christened, appropriately enough, the Glomar Challenger in deference to its pioneering predecessor. The current state-of-the-art ship, the Joyd's Resolution, is able to collect samples from below a water depth of more than 8.2 kilometers and carries an onboard team of about 30 scientists. The technical problems of drilling literally miles away from the mother ship are now almost routine. The most challenging problem is that of maintaining position above the hole while being buffeted by waves and winds, and the ship is generously provided with stabilizers. Acoustic beacons near the drill site on the ocean floor ensure that the Resolution does not drift from where it should be. As for the drill itself, its housing is constructed in sections and extruded through the bottom of the ship. There is hardly any part of the ocean that can escape its probe. Even this paragon of a ship will be updated. A new vessel is under construction in Okayama, Japan, that will be able to drill holes in the ocean floor as much as 7 kilometers deep, 3 times more than the current ODP fleet. This will penetrate into the gabbro layer that underlies the basalt. There is still much to discover down there. It is one thing to take samples. It is quite another to make a map. Yet, understanding is often rooted in a map. Problems often need to be anatomized. First, before they can be tamed by explanation, the circulation of the blood was inferred in part from anatomical charts of veins and arteries. Elucidation of the principles of stratigraphy accompanied the publication of the first geological maps. So it was with the oceans. the map of the ocean floor that often adorns the walls of geography classrooms around the world was prepared by Bruce Zen and Marie Tharp and first published in National Geographic in 1967. It almost glows with reality. Here is the ocean drained. The sea floor is a mass of fissures and mountain ranges, and everything seems to be arranged in lines. The mid-ocean ridges are the most linear features on the Earth, one of them bisecting the entire length of the Atlantic Ocean. At its apex is a neatly marked rift. There is the Hawaiian chain and its extension northwards to the Aleutians. Sea mounts teeter. In places, the ridges are displaced by craggy lines, as for example opposite the Guinea coast. In other places, the tip of sediments from the great rivers Amazon and Mississippi is patent alongside the steeply sloping continental edge. It's all so exact. I remember wondering when I saw this map for the first time, how do they know that? It was clearly prepared by an artist well trained in the skills of suggesting 3 dimensions. In fact, much guesswork was involved. Since the days of HMS Challenger, depth soundings had been developed, using sonar equipment, more sophisticated versions of the kind of equipment that is now standard in modern ocean-going yachts. Even so, there were parts of the ocean across which there were remarkably few surveys. There was much need for imaginative extrapolation. Tharp constructed a long stretch of mid-ocean ridge, around 6,000 kilometers, between Australia and Antarctica on the basis of one line of soundings. This portrayal, as she said, was of necessity sketched in a very stylized manner. So it was, but the guesses were masterly. This was the map that made clear to the interested observer that there were natural seams in the oceanic crust. The world began to look like a kind of irregular sports ball, sewn together from disparate patches. The joins were apparently located at the mid-ocean ridges, those most persistent lines at once elevated above and graven into the surface of the ocean floor. Those who knew that the Great Wall of China could be seen from a space satellite orbiting the Earth would instinctively know that these basalt walls were more fundamental to the planet than anything humans could construct. The spot depths that the Challenger had discovered were now rationalized into ocean trenches, mysterious and profound dark blue arcs, skirting the edge of Asia. For all its imperfections, the Zen/Tharp map made the imaginative leap for the workaday scientist. However, it did exaggerate the vertical scale 20-fold. This had the effect of making the mountains and slopes look imposingly steep. This is a distortion of real nature. For example, the Hawaiian volcanoes do not rise so precipitously. If they had the proportions shown on the map, they would founder immediately. It is important to remember that the oceans are full of gentler slopes, generally of a magnitude that would not trouble the submarine version of an all-terrain vehicle. Modern multi-beam sonar can enormously increase the accuracy of portraying the ocean floor. Beam technology discriminated the giant landslips that had left Molokai looking a mere sliver of an island, while some of the hills on the sea floor proved to be enormous, foundered blocks over 300 meters, 1,000 feet high. Much of the island must have collapsed. Modern mapping techniques have discovered entire submarine mountain ranges that were not portrayed on the Zen/Tharp map. The foundation sea mounts in the South Pacific form a chain of submerged volcanoes 1,600 kilometers long and rising 3,000 meters above the seafloor. This is like omitting from the picture of the world a Great Wall of China, but 50-fold higher. Nor has discovery stopped. In 2001, a paper in the magazine Nature reported the occurrence of volcanoes, possibly nearly 900 meters high, on the Gackle Ridge under the Arctic Ocean. You can fly over this region a few hours from Heathrow Airport in London. Who would imagine that there were discoveries of such moments still to be made on one of the standard Great Circle routes? The ocean floor has certainly not yet been mapped in enough detail to be certain that there are no other surprises waiting down there. Perhaps it is as well to retain something of the awe once felt for the biblical monster. Leviathan, if not giant serpents, there could still be realms in the deep sea of which we have never dreamed. The standard basalt is known as MORB mid-ocean ridge basalt. Its chemistry is the bottom line for oceanic crust. Other kinds of rocks are often compared with MORB as being enriched in this particular element or depleted in another. The mid-ocean ridges are where new crust is added to the Earth. So MORB is the basic building material of our world. The extrusion of submarine basalt flows supplied by feeder dikes at the mid-ocean ridges may be less spectacular than the foaming lava fountains of Hawaii, but it is more important to the world, for this is how the ocean floor grows. It grows by stealth in the dark. Hidden in the gloom there are pillow lavas, such as those that make up the lower flows on the Hawaiian chain. There are tremors, accompanying eruptions, although they mostly pass unobserved except by the special instruments trained to spot them. World seismic maps show a thin line of weak earthquakes closely following the ridges. The ridge as a whole is buoyed up by the heat that comes from below. The rift at its apex is a seam. At the suture of creation, this is where plates are born and where they part. Company forever, despite being joined at birth. The new volcanic material, added at the apex, becomes part of one plate or another. In the simplest system, to read the Mid-Atlantic Ridge, the new crust is destined to move in the direction either of the Americas or of Europe and Africa. One analogy might be with paired conveyor belts, both tuned to run at the same speed and running back to back. The proper term for the process is seafloor spreading. Even so, the image is too active. The eruptions do not push the system. They are a consequence of it. The lavas insinuate themselves into the cracks along the rift system as the oceanic plates on either side spread apart. This is nature abhorring a vacuum rather than nature punching a hole in the crust by main force. The high heat flow is a measure of an upward movement of the convection cell below the ocean ridge, a movement that both drives the system and engenders the magma that in its turn gives rise to new ocean floor. Spreading rates vary. At some mid-ocean ridges they are slow, including the North Atlantic at 2.5 centimeters a year. This has been compared with the speed at which fingernails grow. The fastest rates are 15 centimeters a year as measured on the East Pacific Rise. The total length of all the ocean ridges added together is something like 60,000 kilometers. Water from the sea can seep into the spreading system. In some of the more active spreading ridges, it becomes superheated and charged with minerals in solution. This water then discharges through hydrothermal vents, the name being no more than classical science speak for hot water, sulfur and iron. We have met before on Maui and the Big Island, painting the rock rusty or bright yellow. But at depth, iron sulfate or pyrites builds fantastical chimneys. There are encrusted dark towers and crazily teetering tubes. The surrealist painter Max Ernst drew fantasy landscapes uncannily resembling this scenery, as if his untrammeled unconscious mind had had prescient access to another immersed store of weirdness. Or the ridges may remind you of the delirious castles designed by mad King Ludwig of Bavaria, piled masses of turrets and pinnacles, daring gravity to do its worst. In the depths of the ocean they can grow undisturbed, for no wind will topple their extravagance. Vents discharge iron-rich, superhot water, and the pyrite is deposited where this water meets the sea water. The chimneys grow progressively around the hot streams. Water does not boil under the pressures. At these depths, so temperatures of 300 degrees Celsius are common, the vents belch forth their sulfurous exhalations as dark miasmas. They have come to be called black smokers. This may seem slightly curious. In a world of blackness, how do you recognize a black fog? It was not until they were seen by the lights of the submersible Alvin that these factory chimneys of the deeps could be recognized and christened. Among biologists, they soon became famous for supporting a whole ecosystem not previously known on Earth. The sulfurous tube supported sulfur bacteria in profusion, and they in turn gave birth to a food chain comprising crustaceans and worms, and then predators upon these animals. Virtually all of these species, in the language of the taxonomist new to science, some of the tube worms that lived near the sulfurous springs were almost leviathans. That there is always something to be discovered in the deeps is proved by the recent recognition of a new kind of hydrothermal vent. In 2001, Deborah Kelly of the School of Oceanography at the University of Washington in Seattle reported masses of white pinnacles growing from the sea floor, building what was romantically called the Lost City. The chimneys can reach 60 meters in height. Fluted and branched, they look like the facade of Gaudi's famous Cathedral of La Sagrada Familia in Barcelona, or like vast quantities of candle wax partly melted and piled into columns by some megalomaniac sculptor. They are largely composed of the common mineral, calcite, and its relative aragonite, both plain old calcium carbonate, the stuff of chalk. Apparently, there are microbes aplenty there, too. Water emanating from the vents from which the columns sprout is much cooler than that associated with the black smokers, 75 degrees Celsius or less. The site, too, is different. The Lost City lies on that part of the mid-Atlantic ridge opposite northwest Africa and positioned a little further from the center of the ridge than in the case of its boiling hot relatives. This is a slow-spreading ridge, while most black smokers have been found on fast ones. The deposition of calcite is the result of warm vent waters high in calcium coming into contact with cold sea water. The ultimate origin of the fluids may relate to processes deep in the underworld, where the seepage of sea water reaches the top of the mantle. This results in alteration of peridotite rocks to serpentine, and the residual calcium-rich fluids migrate away towards the sea floor, ultimately to lay down their chemical burden 800 meters down from the surface of the Atlantic Ocean. The research vessel Atlantis carries the submersible Alvin for this kind of exploration. Photographs of the Lost City were taken by digital camera mounted in a remotely operated vehicle called Argol. The scientists aboard the Challenger certainly set something in motion when they pioneered the technology of undersea exploration. Will the sea floor ever become the ultimate tourist destination? There seems to be as much interest to go there as to the moon, and there is always a chance of coming face to face with some new species of deep-sea creature. For myself, I would prefer this last, inaccessible, wild place to remain in its dark security. The human touch has been so devastating elsewhere. This may be one place where we should satisfy our curiosity and then move on. The continents comprise only about 1/3 of the Earth, yet they also compose the greater fraction of all dry land. This is a self-evident fact, yet stating the obvious has one useful function. It makes one wonder why the obvious is also true. They make dry land because continents stand up. They extend outwards under the sea as continental shelves, which may be up to 100 kilometers wide but are frequently narrower. In geological terms, shelves are no more than drowned portions of the continents. The real division between the continents and the realm of basalt is the continental slope, the steep edge that bounds a shelf so as to appear almost sheer on the horizon, and Thart maps, but remember that vertical exaggeration. The edge of the shelf frequently parallels the coastlines of continents with which we are familiar, as in Africa, but in places such as to the west of the British Isles, There is no relation between the shape of adjacent shores and the outline of the European continental margin. The continents are geologically diverse, being stitched together masses of a myriad rock types, including granites, gneisses, sandstones, and shales. If this book were to list them all, it would be a litany of incomparable dullness. In this fundamental respect, continental crust contrasts with oceanic crust, which is 100 variations on a theme of basalt. This is the result of the manufacture of oceanic crust at the mid-ocean ridges. There is a hot umbilical cord connecting its birth with the pervasive mantle rocks beneath. Melting inexorably leads to basalt magma. By contrast, each continent has its own biography, its own genesis and evolution. Continents are complicated, but on the simplest level, the difference between oceanic crust and continental is one of weight, or rather, density. Continental crust on average is less dense, upper layer 2.7 gm/cc than oceanic crust greater than 3 gm/cc. You can just about feel the difference if you hold a piece of black gabbro in one hand and a comparably sized piece of gneiss in the other. Continental crust is also much thicker than oceanic crust, generally something like 30 to 40 kilometers, but maybe double again, underneath the great mountain ranges like the Himalayas. Oceanic crust, by contrast, does not exceed much more than 10 kilometers in thickness. Continental crust rides up as a consequence of its thickness of less dense rock. So where the light continents are thickest, e.g. Himalayas, Alps, there also is the greatest tendency for them to rise. Prod a chunk of floating wood down with your finger and see how it bobs up. But this is a misleading analogy, for the wood is too buoyant and the motion too fast. The asthenosphere that underlies the surface plates is not liquid in any vernacular sense, although it is relatively plastic. This means it deforms by flow rather than by fracture. Nevertheless, the flow is sufficient to accommodate the Himalayas rising, as erosion by ice and torrent continually wears down and removes some of the load from the summit of the range. The mountains are perpetually delivered into the teeth of storms and the vice of ice, and presented again continuously by uplift to the worst that the elements can do. There is an upper limit to such an uplift process, dictated by physical limits, related to the thickness of the crust, so that no mountain can rise much higher than Mount Everest. To put it as teleologically as possible, every mountain will eventually be ground down to the point where it wishes to rise no more. The stable, average continental thickness eventually attained in this way can endure for thousands of millions of years above mean sea level, or at least above the level as it stands today. We will return to mountains in more detail later. Within the oceans, there are few places where the crust breaks the seas. Surface. The abyssal deep is the stable position for cold oceanic crust. Even on the mid-ocean ridges, the volcanoes rise towards the surface, but rarely disturb it as islands. Had there been no continental crust, there would have been no evolution of land animals, no trees, and assuredly no thinking bipeds. Intelligence may have become the property of the squid, who communicate through color changes on their skin. In another world, this book might have been written in shimmering, swirling modifications of tens of thousands of chromatic cells. Hence the most important, but often unacknowledged, distinction on the face of the earth between continent and ocean is a consequence of the properties of basalt. In order to give habitation to penguins and Polynesians and bring about land, dense basaltic crust needs an extra push of heat. This brings us back to paradise. The hot spots provide such an additional boost. Hawaii is an exceptional place, as were its geological ancestors that bulged upwards over the same deep feature, and as its descendants will be in their turn pushed upwards into the atmosphere, beyond their natural height. When they lose touch with their private artery back into the middle of the earth, These islands will sink below the waves to remain as sea mounts unless a persistent coral reef grants them a stay of banishment from Neptune's kingdom. There are oceanic hotspots elsewhere. Most geologists consider that Iceland is one. It sits atop the mid-Atlantic ridge. We have seen that the ocean ridges are prominent features, but submarine ones. Iceland alone forms a substantial island, 480 kilometers long, with enough shallow waters around it to ensure that the sensible, conservationist Icelanders still have a deep-sea fishing industry. Like the Hawaiian Islanders, they, too, have a respectful, rather than a fearful, relationship with their volcanoes. The eruptions are mostly of the comparatively benign, basaltic kind. Like a northern hemisphere Hawaii, the island has been built up from countless flows piled on top of one another. However, Iceland is not part of a chain, since it is situated so closely on top of the mid-Atlantic ridge. Plates do not drift over the hot spot. Instead, Iceland sits almost still at the center of creation. The apical rift zone is produced by extension where the two plates are prized apart. It is normally accessible only to probing echo sounders far beneath the sea's surface, but in Iceland it runs right across the center of the island. The American plate lies on one side of the island, the Eurasian plate on the other. Uniquely on Iceland, the plates spread apart on land, so there may be a place on Iceland where you can stand with one foot on America and the other in Europe. Iceland is where geologists can go to study the mechanisms of plate birth. No, paradisiac luxuriance decorates the lavas here. Mosses and grasses and lichens are what ultimately soften the blackness. The volcanic centers are very much alive and usually clearly related to the fracture zone. Hekla in the south of the island erupted vigorously in 1947-48. Surtsey was a new island, born in the sea off the southern coast in 1963. As I write, the Grimsvatn volcano is erupting underneath an ice sheet. This combination of ice and fire is especially elemental. On September 29, 1996, there was a magnitude 5 earthquake associated with the eruption at Vatnajökull. Thus the Earth records its birth pangs. In Iceland, you can wash in water heated by the process of creation, making the island a world center for the use of geothermal energy. Hot water is piped into offices and private houses for central heating. It is used to heat greenhouses, too, so that you can eat fresh tomatoes and smell fresh roses. Even as glacier ice grows not so many kilometers away, water percolates towards a hot plume all the time, and there is an endless supply of heat. Iceland is the home of the original geyser, at a place called Geyser. The spout lies at the center of a bowl of geyserite, some 25 meters across. Geysers blow when the water that fountains up so spectacularly is released from overlying pressure, often rising in a single gush up to 60 meters in height. The water spouts out at 75 degrees to 90 degrees Celsius. At that temperature, it can retain silica in solution, but as it cools, the silica is deposited as a white lacquer, which builds the geyserite bowl layer by layer. This silicious center will outlast the geyser itself, and fossil geyser sites can be recognized by the stony remains of the warm ponds to which they once gave birth. Not far from Reykjavik, there is a geothermal lake where you can sit in hot water for the good of your health, or maybe because you like being simmered. The Blue Lagoon at Svartsengi is backed surrealistically by the silvered pipes of a hydrothermal station. When the sun is upon it, the lagoon is genuinely Carolean blue, colored with something like the intensity of the utterly different lagoons in Hawaii. The Icelandic bathers dip in the hot draft that rises from the underworld. You cannot help remembering the spring of eternal youth in Rider Haggard's She. If anything is going to have the properties of an elixir, surely it should be these special waters. Unfortunately, there is no sempiternal paradise here. either just as there was. None in Hawaii. Islands grow, islands fade, but there is something miraculous about such pinnacles of life in the vastness of the basaltic oceans. Miraculous and fragile, too. We shall discover that they are all islands large, and small doomed to obliteration. Part 4. ALPS. Every river in Switzerland has a companion highway, perched precariously above the white water below as it seethes and rushes downstream between giant boulders. In the canton of Glarus, the little road that runs to the village of Elm is no exception, closely dogging the course of the river Surmt and dotting back and forth from it like a persistent beggar. This is comparatively low alpine country, and the steep valley sides are densely clothed with trees. Winter drapes their crowns with brilliant clots of snow, imparting airiness to the landscape. But in summer, when the geologist does his field work, the trees are altogether denser and more serious. Glades of beech and conifers provide deep cover. When I visited the Surmt Valley, wisps of low cloud clung to its sides, as if smoke from some bonfire burning slowly deep within. The woods had drifted out heavily upon the humid air. There are cleared pastures among the woods, where the ground slopes less steeply. These are richly green and splashed with yellow daisies. Discreet wooden hay stores poke out of the hillsides as if they were entrances to underground tunnels. Larger chalets are scattered apparently almost randomly over the slopes, with white rendered foundations and dark brown planking above, each with shutters as neat as can be, and no casement without a window box planted out, with bright scarlet geraniums or extravagant petunias. In the summer there are hardly any tourists, so the inhabitants appear to deck out their houses for their own pleasure. It is hard to believe that these primly picturesque dwellings not so long ago housed peasant farmers whose lives were relentlessly hard, irrevocably linked to the rocky terrain and the imperatives of transhumance. You do not have to look hard for evidence of the geology that controlled their lives, for crags break out from verdant surfaces of the fields, and higher up on the peaks there is little else but rock all the way up to the glacier's edge. The Alps, particularly that part that lies within Switzerland, are the type, example of a mountain range. Many great geologists have spent their lives trying to unravel the mysteries of alpine structure, for this region of the Earth's crust is where everything is topsy-turvy, where great slabs of rock may be flipped over like badly tossed pancakes, and where a mountain of height to challenge the most experienced alpinist may be no more than the tip of a vast geological fold. It is a place where nature has apparently relished stirring up the strata on such a scale as to make wriggling rock conundra to torment the minds of scientists. The Alpine orogeny, Greek oris, a mountain, plus Genesis, took place over more than 60 million years, continuing into the Pliocene period. These highest parts of Europe are also among the most disturbed, as complex in their way as the Hawaiian chain is simple. Hence, you cannot just describe the Alps in lifelike detail, for there is no end to their complications. Instead, I shall take one small piece to represent the whole, a selected microcosm to illuminate the macrocosm. I shall start in the Glarus area of the eastern Alps, where some of the secrets of the range were first decoded from the rocks. It is classical terrain. This simplification is rather like taking one of Shakespeare's sonnets to represent his whole oeuvre. It will not do justice to it, of course, but it is enough to suggest the outline of greater things. Loch Sighton in the Surmt Valley is one of geology's holy places. It does not look much when you arrive, just a wood by a minor road. To find rock, you have to scrabble up a steep bank covered in leaves derived from the dense canopy above. It is rather dim under the trees on an overcast, damp day, and hard to keep your foothold on the slippery bank. The path is underlain by a rock termed the Flish, meaning something like slippery slope in the local patois. After a few minutes of scrabbling along a path through the wood, you reach an overhanging cliff a few meters high. A projecting rock ledge provides shelter from the rain. This is where a famous contact between rock formations is exposed. The lower part of the rock section over which you have just climbed is the flysch, dark gray slaty rocks that come out in small shards if you pick at them with your fingers. These rocks were once soft muds beneath the sea, hardened now by time and pressure. The cliff above is made of a completely different type of rock. It is a massive stone, and if you scrape off bits of moss and lichen, a rich red color is exposed, the same ripe berry tones can be seen in the old red sandstone of the Welsh borderland. Look closer, and you notice that the red rock is a mass of pebbles of various sizes and colors. Some as large as your fist. The red is mostly concentrated in the matrix that encloses them. It is a conglomerate nature's approximation to concrete, such as might be formed from the cobbles on an ancient beach or from the pebbles accumulated on a lake bed after storms. The pebbles themselves were the product of weathering of still more ancient rocks. Limestones here, a lump of sandstone there, perhaps some resistant volcanic rocks, in fact, something of a potpourri, all cemented together by the red matrix. We have all had a comparable experience when picking out the differently colored cobbles on a beach. This distinctive rock is known as the Veracano. Look closer again, and you notice something else. The pebbles in the conglomerate are all elongated. They have been turned into parallel sausages, telling you that the whole outcrop of rock must have been extended, stretched plastically on some kind of tectonic rack. This is something that only happens at depth in the Earth's crust, where pressure makes rocks flow rather than fracture. So now you can tell that there was once a great thickness of rock above you, where only brooding clouds now float thick and gray, which erosion has removed to expose the rock seen today. You are looking into the interior of the Earth and back in time. So far, so much deduction, but there is more. At the contact between the Veracano above and the flysch below, there is a thin interval of limestone. You might call it a bed, but it undulates in thickness. Limestone, of course, is calcium carbonate, and thus chemically utterly different in composition from the clay rocks below and the hard, pebbly ones above. It is known as the Lochsitan limestone, named after the type locality. At this spot under the trees, it is about 30 centimeters thick. At other localities, it can be 2 meters thick, but never much more. It forms a recessive notch in the cliff's profile, the eaten-away softness of this stratum explains why the overlying and much tougher Veracano forms the overhanging cliff. The limestone is a creamy color. In several places under the overhang, it projects downwards into the flysch below as a kind of lobe. A closer look reveals that the Lochsitan limestone is all ground up and contorted. It has been pulverized, mangled, and mashed. In the middle of the limestone, there is what appears to be a horizontal crack that extends straight as a die along the length of the outcrop. At first glance, you might assume that what you were looking at is a normal sedimentary rock succession. Oldest rocks below and progressively younger ones above flysch, limestone, and Veracano respectively. This is the kind of sequence you can see in cliffs of undisturbed strata by the seaside all over the world. Rocks that were originally laid down under the sea as sediments and then elevated above sea level stack up this way. It is as easy to read as a diary of geological time as the sequence of basalt lava flows on Oahu. After all, the succession of names for the intervals of geological time shown on the end papers of this book was worked out by placing one set of strata on top of another in their proper sequence: Jurassic before Cretaceous, Cambrian before Ordovician, and so on, eventually building up the narrative of geological time. Clearly, we need to ask what evidence of age is there for the rock sequence in the Surrey Valley. A few kilometers up the river, there is an old slate quarry in the Flysh at the hamlet of Engie, today little more than a scattering of houses and a sawmill. The valley is wider here, floored by a few luscious fields in which pretty, gray and tan Swiss cows munch contentedly. In the 19th century it rise, of the dinosaurs, the reverse of the normal sedimentary succession. For while this caused consternation, could all the edifice of geological time built up so carefully by dozens of paleontologists around the world be an error? Could geological time itself be as insubstantially founded as a house of cards? Or, if the ages were correct, what convulsions of the earth must have happened to stack the strata in their current order? Closer inspection of the Lochsitan limestone proved crucial. The contortions within it made sense only if it marked the location of enormous earth movements. Could it have acted as a kind of lubricant as the vast mass of the Veracano slid over the Flysh beneath? Towards the end of the 19th century, the crushed rock, known as myelinite, had been recognized, a rocky paste that was ground when one mighty rock mass was pushed bodily or thrust over another. Very often, younger rock was forced over older. The older Veracano must have traveled to its present position as it slid and ground its way on the back of the oppressed Lochsitan limestone, which buckled and churned under the superincumbent load. This explained why the limestone fluctuated in thickness according to the local pressure and, on occasion, pushed its way down into the softer Flysh, but never upwards into the harder Veracano. If this scenario were true, another inference is now obvious. This mighty earth movement had to have occurred after the last sediments of the Flysh were accumulated, that is, in the Oligocene or later. The sliding motion cut short the history of the Flysh like an assassination, providing one way to date the formation of a mountain range. The next question is, how far did this massive horizontal movement extend? And what was the great push that caused the movement? To answer the first question, one very basic piece of research is required. A geological map. Strata can be plotted out upon the ground plane or mountain alike, then colored in on the map to make their distribution clear, so that the extent of the movements that transported Veracano over Flysh can be traced. Mapping geological strata, or formations as they are usually known, is a skilled business. A good appreciation of subtle changes in rocks and an accurate grasp of three-dimensional space are de rigueur in Switzerland. It also requires stamina and persistence. My guide over this ground was Jeff Milnes, formerly at the renowned Technical University in Zurich, who had tramped many kilometers in the area with topo map and notebook in his rucksack, hammer in hand, marking out this boundary or that. In order to try and understand how the Alps were put together, there was an heroic age of rock mapping in Switzerland. In the earlier part of the 19th century, there were pioneers like Arnold Escher von der Lind. Escher had acquired the last part of his name from his father, an engineer who had built the Lind Canal and drained malarial marshes in the process, so his son had reason to feel proud. Eduard Suess was an admirer of Escher the Younger, whom he had met in 1854. In the preface to his own great work, Das Antlitz der Erde, he remarked, Escher, with all his simplicity, was a remarkable man. He was one of those possessed of the penetrating eye, which is able to distinguish with precision, amidst all the variety of a mountain landscape, the main lines of its structure. He went on, Escher and Studer's map of Switzerland may serve as monuments of the subject. Geological insight, thought Suess, was all about seeing a deeper geological reality beneath the complex, folded rocks that presented themselves to the observer, a special eye. This remains as true today as it ever was. Albert Heim was Escher's student and intellectual successor, and his Geologie der Schweiz in 3VOLUMES remains the biggest single-handed contribution to understanding the Alps. Professor Heim did not just make maps, he made mountains. In his old department in Zurich, they sit in glass cases, models too. The life of the peaks he had studied, with the strata painted beautifully and accurately, passing over Eart and valley alike. They induced the same feeling of wonder that is experienced on seeing one of those model towns in which a sparrow hardly bigger than a pinhead perches upon the town hall clock. Almost every piece of snow, almost every tree was modeled on Heim's replication of Saintes on the northern edge of the Alps. No detail was too small to be beneath recording. Heim's modeler, Carl Maley, deserves much of the credit for these marvelous miniaturizations. Heim used his meticulous scale models as teaching aids for his students to tame the mountains, to cut them down to size. There was nothing so vast that it could not be conquered by the geologist. See, a whole wild landscape has been caged for your instruction. You could regard Heim's models as embodying in concrete fashion a century's change in attitudes towards great mountains, a change in aesthetics as much as science. Mountainous terrain had once been thought of as terrifying and untamable, a place belonging to wolves and unquiet spirits. An 18th century observer wrote of those places where mountains deform the face of nature, where they pour down cataracts or give fury to tempests, rather than exemplifying nature at her most untrammeled. The mountains were a deformity, having little to do with true beauty, which might rather be found in farmed and orderly lowlands or, perhaps, in a productive garden. A wise man might well prefer to keep away from them. A grand switch in perception had already happened by the time Ralph Waldo Emerson could write, in The Conduct of Life, 1860, the influence of fine scenery, the presence of mountains, appeases our irritations and elevates our friendships. Mountains had become the object of romantic sensibility, where emotions seemed to be concentrated in direct proportion to the thinning of the air. They became sublime. Mountains were now places for the sensitive soul to visit in order to experience exaltation and grandeur, wild places that revealed deeper truths. Geological elevation was first cousin to spiritual. The hikers that stride off along mountain paths today, equipped with the latest boots and binoculars, probably subscribe to a less passionate version of the same attitudes. But whether they realize it or not, these modern explorers are following the footsteps of Johann Wolfgang von Goethe and Lord Byron. I live not in myself, but I become portion of that around me. And to me, high mountains are a feeling, but the hum of human cities torture asterisk. Understanding followed upon the removal of terror from the heights. On a mundane level, the heights simply became more accessible as better roads made the mountains negotiable. Spectacular railways followed within a few decades and are still the arteries of Switzerland. Paradoxically better engineering helped foster an aesthetic of wildness. Geologists turned their attention to scientific explanations of the action of glaciers and the genesis of high-altitude landforms, the great Louis Agassiz first among them. For other pioneers, the carefully plotted geological map was a primary tool in understanding alpine structure. Heim's model succeeded the early maps, and then the consideration of deep causes followed in due course, right down to the plate movements we know today. Filleted of fear, even mountains could be encompassed by the powers of deductive reasoning. We can now return to the structure underlying the Veracano, mapped by Albert Heim. Jeff Milne showed me that the notch produced by the erosion of the Lochsitan limestone could be traced quite readily, rising gradually from the top of one peak to the next above the quiet little village of Elm. The package of thin, pale limestone and overlying Veracano could be Seen through good binoculars, the line of contact of the limestone with what lay below seemed to be as straight as a die for several kilometers. Above, elm, far above the tree line, there's a natural hole in that outcrop of Veracano that forms the jagged crest at the culmination of the mountain. This is called St. Martin's Hole, Martin's Lock, and it is said that the sun shines through it directly onto the village church every St. Martin's Day 11 November. To get a closer look at this part of the Glarus thrust, we need to make a detour, moving slowly southwards towards Italy. Just to get to the other side of the mountain, you have to drive for several hours round three sides of a very large rectangle and cross over into another canton. There are no shortcuts over the Hostock, 3,158 meters, without a helicopter. The town of Flims is much more the classic ski resort town than Little Elm, retaining a well-groomed charm in the summer that must be the legacy of the many euros, dollars, and pounds spent when the snow lies crisp upon the piste. Even out of season, ski lifts are still available to carry you up the mountain, 2 chair lifts in succession, and a cable car to get you to the very top. The lifts soar above the summer chalets until there is a fine view across the valley of the western branch of the Upper Rhine-Vorderrhein to the mountains to the south. The car continues higher above the last stunted conifers, past a magnificent cliff exposure of the Malm of Jurassic age, a massive, thick-bedded, yellow-creamy limestone that gives rise to features in many parts of the Alps and which was once laid down under a shallow, warm sea. You feel insignificant measured against the great crags. Upwards and upwards you climb aboard your dangling craft until you debark at the summit of Flimserstein Cassins. There is a trail leading out over the gentle slope. The close alpine sward has splashes of the most intense blue in nature. The flowers of the gentian, deeper than cornflower, brighter than human artifice can achieve, except for Raphael's drapery perhaps. D. H. Lawrence described them darkening the daytime torchlight with the smoking blueness of Pluto's gloom. On either side of the path there are other plants to get the botanist excited. Creamy milk vetch, rough-leaved lungwort, humble creeping, polygonum, delightful little pinks. Here, saxifrages grow so close within cracks that they really do seem to live up to their Latin name for rock breaker. It is a special community of flowers, enthrall both to altitude and geology. A little further along the path, the profile of the reverse side of the mountain tops that towered above Elm is outlined against the sky. There is a line of jagged peaklets, like an array of dog's teeth, called at Skingelhorner, and beyond them, St. Martin's Hole. On a closer, dumpy peak named Ofen, you can see the famous contact very clearly. It is so straight that it looks as if the top of the mountain has been sliced clean through just off the horizontal and then placed back again along the line of severance. The Lochsiden limestone is a pale band, and it undulates in thickness along the length of the outcrop. There is even the same sharp line or cut within the limestone that was observed in the roadside section. Below the contact, a flysch, here called Sardona flysch, South Helvetic flysch, forms soft-looking grayish scree slopes. A small glacier creeps down from the heights. It is a wonderful view, and one that attracted attention from geologists from the early days. Sir Roderick Murchison's party sketched the same scene in the 1840s. Murchison was an English aristocrat, imperious and brilliant author of the Silurian System, 1839, the great attempt to systematize rocks belonging to what we would now call the Lower Paleozoic era, 545 to 417 million years ago. Thus the pragmatic geologist followed hard on the heels of the Romantic poets, and the Flimserstein became an obligatory stop for alpine geotourists. Arnold Escher von der Lindt made a painting of St. Martin's Hole from near the same spot on which we stood. famous eyes had taken it all in before us. Looking further afield, the same geological contact could be clearly seen towards the top of several other adjacent peaks. On Piz, Dolph, 3,028 meters, and Piz de Sturles, 3,114 meters. The temptation to draw a kind of dotted line through the air to connect the separate elements of the contact together was overwhelming. It must surely be a single vast plain. The story of the development of understanding of the Glarus structure encapsulates that of the Alps. We have traced it from the lower part of the Surf Valley, Alabama, the way to the Flimserstein and beyond. Older rocks above, younger. Clearly, there is a vast perturbation of the earth to be considered. There are several ways to bring older strata on top of younger. Thrusting has been mentioned previously. The other way is to fold and overturn the strata, much as one turns back the underlying sheets and blankets at the head of a bed. It was clear from the early days of geology that parts of the Alps were intensely folded. Whole mountainsides could evidently be twisted as the heights were built up. There's a drawing dating from the earlier part of the 18th century showing one shore of the Erner Sea, the easterly lobe of Lake Luzerne. It was reproduced in Vallisnieri's Lesion aux origines del Fontaine in 1715, one of the earliest systematic accounts of mountains. I stood on the very spot from which the drawing had been composed by J.J. Stutcher. The same lakeside had other resonances, too, for Telskapelle was where Wilhelm Tell escaped to freedom from the boat that was to take him to Kusnacht Castle and a grim death. Goethe's friend Schiller retold the story in incomparable fashion in 1804. It seems that geological and romantic locations have a tendency to get tangled together. On the far side of the lake, disturbed Cretaceous limestone strata are splendidly displayed. Stutcher clearly portrayed folds in several of the mountains and, overall, made a passably accurate sketch. What he did not do was connect any one series of strata from one mountain to the next. Each outcrop was its own self-sufficient story. Stutcher is one of those unfortunate men who is chiefly remembered for an error. In 1776 he published in the Transactions of the Royal Society of London a fossil find from the famous Miocene deposits of Eningen as proof of the biblical flood. He called the fossil Homo deluvii testis, which speaks for itself. It is a kind of spread-eagled object with obvious legs. Sadly for Stutcher, 100 years later the fossil was shown, beyond dispute, to be that of a large salamander. Diluvial man was but an amphibian, and Stutcher joined a select few like King Alfred unfairly immortalized for a gaffe. That this was unjust is shown by his competent drawings of strata. 100 years later, and the strata were joined up. Geological maps showed that one limb of a massive fold might connect the base of one mountain with the top of the next. Interconnecting strata had been eroded away in cross sections. The air became full of dotted lines showing where strata had once passed, only to be removed grain by grain as a result of the operation over millennia of frost and water and wind. Ghosts of vanished mountains could be inferred, faint specters of topography past imagined. Stutcher's outcrops were linked together by the outline of folds. Writing of the same area, Edouard Seuss said, "Those who have seen the cliffs of the Axenberg on the Lake of Lucerne will have viewed with astonishment the inextricable entanglement of the limestone beds." It became a familiar observation that massive rock beds might be turned on their sides and crumpled like the bellows of a concertina. Overfolding did indeed turn whole piles of strata upside down. Mapping distinctive rock beds helped prove the structural suffering of strata beyond doubt. The thin, iron-rich Jurassic rock bed known as the Dogger is but one example. Near the little village of Brisson, Jeff Milne showed me how its distinctive signature could be traced from one hillside to another, bucking and twisting like some demented fairground. Roller coaster. You could see how the earth buckled and how such complex. Pleatings shortened its crust by folding straight up onto themselves. I am reminded of unpicking the bud of a poppy, so much gaudy petal crimped and folded, into so small a volume. For many years the careful mappers mapped, and folding became quite the thing to explain virtually all geological problems in the Alps. Following the zeitgeist, Arnold Escher interpreted the Glarus structure entirely in terms of folding, and Albert Heim, model maker extraordinaire, apparently followed suit. Heim was a patriarchal figure, authoritarian and sure of himself. He would not be an easy man to cross. Escher and Heim explained the Glarus structure as a double fold, two mighty overturned and recumbent folds that face one another across the Sernf Valley. The Veracano was brought back over the younger Flysch in two folds. Imagine turning back both the head and foot of the bed, so folding back two swathes of the underlying sheets to oppose one another. One fold came from the north, the other from the south. It was certainly a striking concept which implied a lateral movement of the Veracano of at least 15 kilometers. When Escher first proposed the double fold, it seemed a radical, even revolutionary idea to have so much crustal movement. In his tectonic essays, Sir Edward Bailey quoted Escher's caution at the time, "No one would believe me if I published my sections. They would put me in an asylum." Edouard Suisse later summarized the Glarus story as a magnificent conception, unheard of in the views of that time, of a double folding of certain parts of the Alps. Albert Heim defended the idea of the Doppelfold for many years, and who would have dared to disagree to his face? It would be wrong to pooh-pooh these great geologists with the wisdom of hindsight, for what they saw was an honest interpretation of the high ground they knew so well. The only alternative scheme seemed even more radical: to join the dots, as it were, to unite the soul of the structure marked by the thin sliver of Loxodon limestone as one stupendous line of movement, skipping from one summit to the next like a tectonic ibex. I had experienced the temptation to draw such a line atop the Flimserstein. Everything from the Vorderrhein to Glarus would belong to a single structure. You would have to more than double the distance traveled by the great mass of the Veracano to some 35 kilometers. A mighty heave, indeed. Perhaps Escher shrunk from the sheer magnitude of the crustal movements implied. Could the earth shrug its skin so momentously? We know that rocks could crumple and fold, but could huge chunks of crust slither laterally for such great distances? And if they did, what forces could propel them? The proposer of the single Glarus, Thrust, the man who attempted to rub out the double fold in 1884 in a seminal paper published in the Bulletin de la Société Géologique de France, was Marcel Bertrand, professor of geology at the University of Neuchâtel in the French-speaking part of Switzerland. What may have galled the meticulous mapper Albert Heim is that fact that Bertrand never actually visited Glarus. Bertrand admitted he had utilized less descriptions to Heim do, double ply, to draw his new lines and his new conclusions. How dare he be so presumptuous? Even today, there are hardened field men working, geologists on the rough end of a hammer, who feel that the laboratory, or computer-based scientist, is something of a softy, a spinner of hypotheses, away from the coalface of real observations, and who might have more than a sneaking sympathy for Albert Heim, worsted though he was in the end. Further geological mapping in the greater Alps, much of it magnificent, work by Heim and his colleagues, revealed that nearly all the structures in the rocks faced northwards. Thrusts were directed there. Major overfolds bulged outwards towards the north. This was familiar to Edouard Suisse, for whom the Alps were home ground. He pointed out that the whole mountain system was bowed outwards in a convex arc to the north. Here the mountains encountered what he termed a rigid foreland, whatever it was that caused all the rucks and dislocations. It seemed to be pushing from the south. Yet, the double fold of Glarus required quite as strong a shove from the north to produce its massive, south-facing overfold, and this force apparently must have operated at exactly the same time as that on the north-facing fold and exacted the same geological effects. After all, the rock sequences seen in the field in Glarus were similar wherever they occurred. This was all too much to ask. Besides, if Bertrand's single thrust were accepted, it was accountable once again to movement from the south towards the north, and no need to make an exception for a small area in eastern Switzerland. The double fold, it seemed, was doomed. Albert Heim, with some generosity of spirit, finally acknowledged as much in 1901 in an open letter published in a memoir by Maurice Lugion, 1870 to 1953, on the structure of the Western Alps. By now, it was apparent that in mountain belts great masses of the earth could move long distances at low angles. This was the key that unlocked the mystery of the Alps from Glarus to the world. By a repetition of the same process, mountain chains could be understood as collections of slices piled high on one another. This was how the Earth's crust both shortened and thickened. The name given to a slice was nappe, in French the word for a tablecloth. It is not clear who first used this word, which has now become the accepted term. Using an analogy appropriate to the name, the historian Mott Green described the Alpine strata before their elevation as a richly patterned tablecloth on a polished table. If you should place your hand flat on the table and push forward, the cloth will begin to rise into folds. Push more and the folds will flop over forward, and the rearmost fold will progressively override those before it, producing a stack of folds. The generation of an alpine mountain range is a matter of piling on the nappes. The early nappes pile up and are then carried piggyback as a new active zone develops. Pile is heaped upon pile. In the Alps, 3 great packages of nappes moved in succession. Of course, today you very rarely see the whole pile, for erosion has deeply dissected away the landscape, removing some of the uppermost series of nappes. Even at the top of the Flimserstein, we have to imagine several kilometers of rock above our heads. Time has sent it packing. Continuing with Green's tablecloth analogy, take a pair of scissors and cut away at the stack from various angles, removing whole sections of the pile of folds. Having done so, push the pile again so that the segments become jumbled against each other. In other words, you add chaos to confusion by adding erosion and later earth movements to the recipe, and that is why you stare at a cliff face in Switzerland and wonder at the spun complexity of its strata. But the recognition of nappes set out the research project. You need not simply throw up your hands in despair at perverse plications and ceaseless crenulations in the Alps. The idea now was to map the nappes, work out their sequence, and identify the rocks of which they were composed. There were many feats of heroic fieldwork. Pierre Termier, Rudolf Staub-Rudolf, Trumpy. These geologists will be forever associated with the mountain ranges. They unscrambled, as surely as if their names had been etched upon some mighty cliff face. Nappes were named so that hitherto intractable mountains might now be recognized as comprising several slices stacked one above the other. In science, naming is often taming. The Glarus nappe it became, and remains, to say nothing of the Scientist nappe, the Merchant nappe, and all the rest thousands by now each named for a locality where it was well developed. The deformation of the rocks was often ductile. They were stretched, not broken. Albert Heim himself had collected distorted ammonite, fossils that had been deformed along with the rocks that contained them. I examined a few of them in Zurich. They looked somehow hunchbacked, squeezed out of shape, lopsided, their original regular spirals twisted and wonky. In some places, fossils were stretched up to 10 times their original length. Mathematical calculations can be made to compute the distortion. These rocks have endured. They tell us how the Earth behaves in extremis. Forget tablecloths for a moment. An image of pasta dough stretched and spun back and forth seems more appropriate. Alpine mountains might be seen as badly made lasagna, crudely layered and buckled in the cooking. Perhaps the last of the Alpine heroes is Rudolf Trumpy, scion of the line of field men going back to Arnold Escher von der Lindt. I saw him receive the Wollaston Medal, page 220, of the Geological Society of London in 2002. Wilhelm Tell himself could scarcely be more legendary. In the urbane meeting rooms on Piccadilly, the grand old man seemed somehow as craggy as one of the mountains he had unscrambled. You just knew that his natural habitat was with a party of geologists bellowing at them through a megaphone on a small cruise ship in the middle of Lake Lucerne. For another important advance to which Trumpy contributed was the naming and mapping of the 3 main packages of naps. They were e'en placed in bundles, tectonic messages on sheets delivered one after another. Each of these packages was a record of a separate mountain-building event. The chronology of the Alps became calibrated by very careful geological mapping, later augmented by radiometric dating. The main events saw the arrival of what were termed Helvetic, Pennine, and Austro-Alpine naps, respectively. These packages would eventually make sense in the context of plate tectonics, since naps preserve chunks of the scrunched-up Earth's crust all out of place. You could find different bits of ancient geography as you moved across Switzerland. You have to imagine taking a map of the past, cutting it up, and then moving chunks around hither and yon. It was all most confusing. You begin to understand how a scientist might spend a lifetime working on no more than a few mountains. Sometimes the effort entailed in reconstructing the original disposition of the rocks seems like that, involved in unscrambling an omelet. Further south again, we follow the valley of the other branch of the Rhine, the Hinterrhine. All the routes dog the rushing river, the old road alongside, the impeccable new autoroute, and the railway to Thusis, all dodging in and out of sight of one another. The modern road misses no excuse to shoot into a tunnel. The Swiss are masters of such engineering, and now the new roads enter and leave tunnels with abandon, apparently ignoring folds and thrusts, and naps in their eagerness to arrive. Older roads tend to wind up precipitous slopes in a series of hairpin bends. 5 kilometers south of Thusis, the old road takes you into a dreadful chasm, the Via Mala literally, the bad way. It appears to be as much an irregular crack in the earth as a gorge. In places it is only a few meters wide, but as much as 300 meters high. The sun does not reach into it, so it is always gloomy, like a grotesquely narrow, unlit passageway. It provokes awe. A small party of schoolgirls we were with even stopped giggling and jostling as they craned their necks to get a view of the torrent. The river has gathered urgency in its confinement, the white water swishing past, and over rounded boulders far below. A few spindly trees cling to the sides of the gorge, but their root hold on the tiny patches of soil gathered in cracks is precarious. It is a place to make you shiver and pull up your collar even on a warm day. A bad way indeed it must have been in the Middle Ages, when a precarious path allowed for the passage of just one traveler at a time. Traces of the old path can still be made out. In places, chains hammered into the rock help the traveler retain his foothold. 70 meters above the river bed, there is a remnant of one of the subsequent roads, a single-span stone bridge built in 1739, crossing from one side to the other. From below, it looks absurdly as if it were actually propping the two walls of the chasm apart, like a buttress in a cathedral. The Via Mala owes its eldritch, claustrophobic atmosphere to the geology. The Hinterrhein has cut through the limy schists known as the Bühnerschiefer, which are part of the Pennine nappes. Their remarkably uniform character has ensured the narrowness of the gorge. As the mountains have been uplifted, again and again, it is as if the river acted in the manner of a circular saw. Cutting into a particularly dense log of teak, the gorge maintained its vertiginous integrity as the mountains were delivered into the jaws of erosion. So the character of the rocks determines the character of the land. The Bühnerschiefer are known to be the time equivalents of the massive limestone cliffs of Malm that we passed in the cable car above Flims. They are an utterly different rock type, originally deposited, some geologists believe, as lime-rich muds in a deep-water basin, rather like the Gulf of California, sorted, squeezed, and reshuffled by tectonics. The nappes dictate the lie of the land. It is something of a relief to emerge on the other side of the Via Mala into the Rainwald, where the well-wooded valley broadens and comfortable-looking farmhouses reappear. Even so, perched on almost every rocky promontory, along the valley there is a castle, or at least the ruins of one. In the latter case, you have to look hard to recognize them for what they are, because they are roughly built of local stone and merge naturally into the crags. In the past, they must have protected the important Rhine trade route. The old towns along the route are as solidly built from the gneiss of the region as you might expect. The roofing slates are actually thin slices of gneiss. They must weigh heavily on the massive beams beneath, as so often when natural stones are used for this purpose. These slates have an attractive irregularity, a dappled richness, especially when lichens paint them. The Post Hotel Bodenhaus in Splugen, where I stayed overnight, has stone walls as thick as those of a fortress. It was somehow comforting. When pile upon pile of nappes are superimposed, the Earth's crust thickens. Not just the Alps, but virtually all mountain belts are zones of shortening and thickening. The opposite, if you will, of the thinning of the crust over the mid-ocean ridges mentioned previously. When the crust clots together sufficiently, something else happens. The rocks themselves transform. This is because dramatic thickening also entails burial, and burial means that the ambient pressure on the rock increases as does the temperature. This encourages metamorphism. Minerals change from one to another. The very fabric of the rock is altered. The original rock becomes disguised and eventually unrecognizable. If the rocks were once sedimentary, any fossils they may have formerly contained become obliterated. Schists and gneisses are the most abundant products of metamorphism in mountain belts. Nature's metamorphism is not like the magical change that happens to Gregor and Franz. Kafka's famous tale Metamorphosis, who wakes up transformed wholesale into a monstrous insect. Natural metamorphism can only work with the chemistry of the original rock. All the mineral changes that occur are expressible in equations and can be experimented upon in laboratories. These rocks are, to return to the pasta analogy, the result of a kind of cookery, or, more correctly, pressure cookery. The dish is utterly transformed in the oven, which, however, cannot produce anything that is not in the ingredients. This topic will appear several times in this book. For now, I have said sufficient to take us further southwards to the Passo del San Bernardino. The old pass of San Bernardino, not to be confused with the great St. Bernard Pass, at 2,065 meters, 6,775 feet, forms the watershed between the Italian part of Switzerland and the German part to the north. Nowadays, the main road passes scornfully beneath it through one of those tunnels, but not. So long ago, all the heavy traffic had to grind up and then down its relentless hairpin bends. Today you can have the summit to yourself. There are wispy clouds below you and rank upon rank of mountains in the distance, just the place for Emerson's irritations to be appeased and his friendships elevated. The gray rocks emerge from the ground in low hummocks, like a school of whales breaking the water. Some are obviously Roche's Moutonnaise polished, and shaped by the ice sheet that covered this whole landscape during the last million years of the Pleistocene Ice Age, a geological yesterday compared with the formation of the Alpine chain itself. Major remnants of this great ice cover remain on parts of the Alps, although the recent retreat of the glaciers is one of the causes célèbres in the debate over the effects of global warming. Elevation of the mountain chain to the altitudes at which ice sheets can grow is itself a consequence of the tectonic thickening of the light crust as nap piles on nap relative to the dense mantle layer below. As the folding and thrusting doubles the thickness of the light crust, compensation is inevitable, and the mountain chain rises. It is bounce back. If you look for ultimate causes, then very deep forces sculpted the features of the face of the earth. The rocks of the San Bernardino are part of the Agila Nap. To use the geological language unadorned, they comprise coarse gneisses which have been deeply buried and metamorphosed within the alpine pile, and subsequently exhumed by erosion. Crudely shaped blocks of similar rocks were employed in the thick walls at the Post Hotel at Splugen. They are pallid, banded with grayish to creamy layers of the minerals feldspar and quartz, alternating with dark wisps and stripes composed of several different minerals. Shiny plates that catch the light are black biotite mica. In some parts of the outcrop, the layers are distinctly striped, like the fabric in old-fashioned pajamas. In other places, the layers undulate and curl in folds that often just peter out. You can almost visualize the squeezing that produced these writhing graffiti. Or there are dark curlicues, resembling Arabic writing. It is all massive, uncompromising, and highly impermeable. As a result, hollows are occupied by mossy little bogs, fringed with cotton grass looking like so many miniature white sticks of candy floss. Tough, coarse grass and the tiny, creeping dwarf willow grow on the slopes and in wandering cracks and fissures. Animals tend to scream at you up here. Alpine swift screech shrilly. Dark crows croak cries of cork, and Jeff Milnes assured me that a curious, persistent, piping angry squeak was the call of the marmot, a comical-looking mammal that gets as fat as it can during the short summer season before hunkering down for the long winter. There's a thick vein of milky quartz cutting through the gneiss. It looks as if it might be a precious seam, but it is actually the commonest of minerals. Nonetheless, I could not resist picking up a white morsel of it to take home. The vein must have been a response to some later event when gashes open up in the obdurate mass. Quartz is always ready to fill up cracks created by tension. What struck me was how similar this place was to other nice terrains I had visited. No matter what their geological age, bare hills in the highlands of Scotland, barren boggy wastes in the middle of Newfoundland, ancient areas of Sweden, all obeying the bidding of their geological foundations. Assiduous field workers have discovered little pods of a rock called eclogite in the rocks around San Bernardino. This rock has nothing at all to do with Virgil's pastoral verses, the eclogues. Good though it would be to imagine an earth scientist taking inspiration from a Roman poet, but it is a stone that makes geologists as lyrical as they ever get, because it is composed of special minerals, including one type of garnet that only form very far down in the crust. Rather like the xenoliths we met in Chapter 2, eclogites tell of deep things. The area now populated by crows and marmots was once buried deeper than we can imagine, to exceed 70 miles, thought Arthur Holmes, and modern estimates are not so different. What revolutions of the earth have been played out on this bleak mountain pass, and what work time still has to put into where these peaks low again. When I asked Jeff Milnes what age, the rocks were before they were turned into uncompromising gneisses by the alpine orogeny, he made a rueful face. As with the landscapes they produce, gneisses are much of a muchness and have lost their original personality. Gneisses can start out as shales or granites, or even another, older gneiss. Heat and pressure is the great leveler. Radioactive clocks can be reset. In the case of the San Bernardino rocks, the last option is probably the right one. In the profound tectonic scraping through the crust, older rocks, dating from still earlier revolutions of the Earth, asterisks were caught up in the new vice of alpine, mountain building, having already endured what the Earth could inflict upon them once. They were subjected to it all over again. But where did all these naps come from? They have moved northwards in pick-a-back piles, and as Edouard Suisse noticed even before nap theory had been fully worked out, as a rule the highest lying sheet has been carried. Furthest, we have already worked our way steadily southwards into the heated heart of the pile. When the mappers had completed their monumental surveys, it became clear that the sheets were tucked downwards towards the south. Maurice Lugion called such regions root zones. If the naps were sheets or recumbent masses, they lie at a low angle, but in the root zones, everything is tipped to the vertical. It was as if the mountain belt had been squeezed out progressively from these narrow belts. Cross-sections prepared by modern geologists show the geology arising from these zones like huge cartoon genii whipped up out of the spout of an Aladdin's lamp. A fat series of naps will taper down to little more than a will-o'-the-wisp at its root zone. It must be time to move further southwards to look at this place where mountains apparently arise in the fashion of gigantic fungi from a small crack in a log. Off to Africa, my guide exclaims. It is impossible not to respond enthusiastically. The road winds and rewinds upon itself downwards, apparently forever. At some point trees make their reappearance, and there is the plangent dong of cowbells, so the zigzag route must really be shedding altitude. When buildings appear by the roadside, you realize that you have crossed into another country. As the bad-tempered crow flies, it is less than 20 kilometers from Splügen, but you have effectively entered Italy, though. You're actually in Italian Switzerland. All the signs are in Italian, and the ristorante offers superlative coffee at last. It is easy to understand how effective a cultural barrier the mountains must have been in the past. Geology, separating languages. It is harder for a stranger to comprehend the glue that has retained this canton for so long as part of Switzerland. The road follows the Val Mezzosina towards Bellinzona, downwards all the way, but gently. Now, all the nice roofing slates have vanished, to be replaced by pantiles, painting patchworks of all possible orange hues, broad-leaved trees, chestnuts, limes, beeches, have replaced the conifers. Neat vineyards make green stripes on the south-facing slopes. We are heading for the main route, zone of the Alps, which is marked by a major fault, the Inselberg line. It is one of the most important geological lines in Europe. Somehow, you expect to see it drawn out in black on the ground, as it is on geological maps. But of course it is more subtle than that. The San Andreas Fault in California has the same modesty, as we shall see. We stop in the village of Pianazzo in the Val Morabia. The river valley follows the famous line here. Streams have a way of seeking out major junctions in the Earth's surface, picking out old weaknesses. An ancient and somewhat decayed path leads down to the river. Its walls have been carefully constructed from the local geology, so it must have been important once. It was probably the path that was used by the villagers to conduct their flocks to the summer pastures on the high ground beyond the river, but there is little sign of that ancient peasant life today. It is a pleasant walk downwards, underneath the sweet chestnut trees. The ground is moist enough for apricot colored chanterelle mushrooms to sprout among the leaf litter, and there is a smell of damp in the air almost like walking through jungle. When you see the rocks poking out at the sides of the path, you are within earshot of the tumbling waters below. You notice at once that the grain of the rock is vertical. Ribs of rock flank the hillside like dense palings. There's a lot of the mineral mica, which glints in the sunlight. Every flat little plate of this mineral is also orientated vertically. The grain of the rock is its foliation, the way it splits in response to the massive tectonic forces that have squeezed its every particle. Here, you realize the rocks have been compressed and mangled in a way that has oppressed their very atoms. Seeking to accommodate unbearable pressure, they have realigned themselves at right angles to the lateral forces generated within the earth. A strange-looking, lumpy rock is all that remains of a granite, its feldspar crystals reduced to little knobs. Evidently, even the most obdurate of stones has succumbed to relentless pressure. There are creamy-looking rocks, too, which are reminiscent of the Lochsitan limestone. These are myelinites, the paste that results when rock grinds against rock in tectonic torture. All these highly metamorphosed rocks are the roots of the Austroalpine nappes, those that overlie everything else, the roof of the Alps. This is where great sheets of strata come to ground. Here is the aperture that spun out those gobs of tectonic pasta that extend 100 kilometers to the north. It is a wonder how so much can arise from so little. It is known exactly when it happened, too. The dark, lustrous mica called biotite grew in response to the mighty squeeze. It contains a radioactive clock that was set at the time of the tectonic events, so we know it all happened 20 million years ago. The mountains were made high, and since then the action of eons of erosion has allowed us to see into their guts, as we did at the San Bernardino Pass. This story cannot but seem dramatic to the imaginative observer, but the drama, of course, is in our minds. We inevitably anthropomorphize. Even the words we are obliged to use come with our own human baggage. Squeeze, pressure, grind. I have tried to avoid using the word Titanic throughout this book, although it could be strictly applied, since the ancient Greek explanation was that mountains were thrown up by the Titans. As science has advanced, the Titans have been sent packing. The rocks are indifferent to humankind. They move to the slow beat of geological time, but our language inevitably still entrains them with our lives. The Scottish poet Hugh MacDiarmid put it well. On a raised beach, we must be humble. We are so easily baffled by appearances, and do not realize that these stones are one with the stars. It makes no difference to them whether they are high or low, mountain peak or ocean floor, palace or pigsty. There are plenty of ruined buildings in the world, but no ruined stones. Onwards to Africa, close to the swirling river, there is a little rustic bridge that carries the old track across to the other side of the valley before it snakes upwards again through yet more woods to reach the pastures above. When you lean over the bridge, you can see rocks in the riverbed. What is immediately obvious is that they are directed at right angles to those we examined by the descending path. They are something quite different. They look completely distinct from the crushed and shiny rocks, too greenish. Schist for the most part. On the mountain slopes beyond they are in turn overlain by Triassic-age limestones, which have no counterpart in the Alps to the north at all. The conclusion is obvious, yet it is hard to believe. The little bridge spans two worlds. South of the bridge there is a strange continent. It meets the main body of the Alps along the Inselberg line. The fact that the rock sequence to the south is neither squeezed nor deeply metamorphosed, like those north of the bridge, tells us something else. There must have been something like 20 kilometers of vertical movement along the line. Squeezed and heated rocks that have been deep inside the earth now lie alongside others that have not. Looking over the bridge at the stream making its way along the ancient junction, you expect to observe something more profound. But no, all that movement has long since sunk into quiescence, and only the waters recognize convulsions that once shook the earth. For this is the place where Europe meets Africa to the south. The bridge spans the two continents. The collision between the masses pushed up the Alps, which is grossly to oversimplify, as you must at first. When we had a closer look, we found that Africa actually extended to just the other side of the bridge, so it was possible to take a photograph of my daughter with one leg in Europe and the other in Africa. I can imagine the photograph, by then fading slightly, puzzling one of our descendants why the legs akimbo on a leafy path, somewhere that seems without particular distinction. What would they say if they realized that the curious posture straddled a significant fraction of the world? Now we come to what, to use a happy pun, is the crunch. For now the confrontation of tectonic plates comes into the argument. In our mind's eye, we have to draw backwards from the particular spot where my daughter stood, on the surface of our kaleidoscopically complex world, or rather upwards, as if we were carried on a rocket into the ionosphere. Distance lends its own clarity. We see that our footpath terminates at one point in the southeastern part of the Alps, further upwards, and we can see the Mediterranean Sea with its pattern of islands, and the great boot of Italy hanging downwards. We might even make out a plume of smoke from one of the classic volcanoes, with which this book began, marking a current engagement of the plates. We can now appreciate the whole sweep of the Alps and its continuation, eastwards into the great arc of the Carpathian Mountains, and beyond that, into Turkey, where we know the ground still shakes disastrously when the earth shrugs. We can comprehend that this is all one interconnected system, and that our path through Switzerland was no more than an amble through one tiny piece of a great mountain chain, which in turn links other ranges all the way eastwards to the Himalayas. Then we see Africa, a vast continent, and an ancient one. We can appreciate its presence, its mass, its unyielding solidity. Africa's sheer extent dwarfs that of the Mediterranean Sea. From this height, mountain ranges begin to seem more like wrinkles. Naps might be no more than ticks on a spasm of the crust. If Africa is moving northwards, and it suddenly seems plausible that all those monstrous rucks and buckled limestones and squeezed gneisses, over which are insignificant bodies clambered in the Alps, might be no more than the desperate scrambling of the earth away from the encroachment of the inescapable giant. The naps fled northwards. The whole Carpathian chain curves away from the oppressor. The ancient mass of northern Europe at Wardsus. Forland braced itself against the onslaught, and the effects are felt far beyond the Alps themselves. The basement rocks of Europe shivered, and the rocks that covered them were flexed. Even the shape of southeast England is influenced today by the approach of the distant giant. Everything scales to the great event. The intimate history links with the grander design. You cannot look on too large a scale to help you understand a solitary footstep through the landscape, a single crystal on a cliff. The mountains grew as ancient oceans vanished. The oceanic lithosphere was consumed until continent collided with continent, Europe with Africa. This whole process was the motor of mountain building. There were other Mediterraneans before the present one, seas that came and went in the area between Africa and the European foreland. Sediments that accumulated around their continental shelves became the limestones, sandstones, and shales that subsequently fed the naps. The greatest of these seas was what Edward Seuss called the Tethys, named for a Greek sea goddess, which largely predated the growth of the mountains. Much of the Tethys was shallow and warm during the Mesozoic and full of life, a marine paradise of sorts. ammonites and sharks thrived and are now preserved as fossils that date the rocks. Seuss had inferred greater depths in some parts of the tethys, because calcium carbonate shells had apparently dissolved, something which only happens at depth. The fact that the calcareous base of the shark's teeth has been dissolved and removed proves that the tethys, where it extended over many places now occupied by the Alps, can hardly have been less than 4,000 meters depth. Some scientists may dispute Seuss' exact figure now, but nobody doubts that the tethys span everything from the shallows to the deeps. But what of the darkflish, over which we had slithered by the roadside where this chapter began? As the mountains rose above the sea in their early stages, they were immediately set about by the forces of erosion. The waste derived from the growing chains fed into adjacent marine basins, especially sags lying to the north of the growing chain, as masses of dark sediment. These sediments, the debris of tectonics, comprised the flysch. As the mountain belt continued to evolve and the crust shortened further between the opposing jaws of the tectonic vise, the flysch itself became entrained with the folding and thrusting. In places it became deformed. Hence, the squash flysch fish. The Glarus napped and slid over it, trapping it forever. By bringing in the movement of plates, the explanation of mountain chains becomes simpler than the recondite geometry of folds and naps, and all the twisted extravagance of strata might have suggested to those patient mappers. Except it isn't so simple. Nothing in nature is so obligingly straightforward. The principle of the Alps being squeezed out inexorably between the moving mass of Africa and obdurate Europe is correct enough. However, the margins of both sides were not one single piece of continent, like the jaws of a woodworker's vise. Rather, both the African and European edges comprised several smaller pieces that behaved with considerable independence. A better analogy than a vise is to think instead of two huge ice sheets jostling in the sea, with pieces fragmented from either edge grinding together or free, floating by turn as the gulf between the larger sheets waxes and wanes. The plate that lay on the far side of the bridge in the Val Morabius should correctly be called Adria of African origin, surely, but with a tectonic history only loosely tied to its great parent. So it was the collision of Adria, not Africa in the strict sense, with the adjacent part of Europe that was responsible for the heave of the alpine naps. By the same token, the margin of Europe actually comprised several blocks massives of old rocks. The field mappers had in fact recognized these masses of ancient Hercynian rocks underlying nap complexes within the Alps. This was a triumph of deduction, considering that this basement could look much like some of the baked younger rocks. Most of the massive igneous rocks, like granite, within the Alps actually belong to these ancient massifs, including mighty Mont Blanc itself, 15,782 feet, 4,810 meters. As we have seen in the San Bernardino Pass, the older rocks could also be remobilized in the alpine movements, just to add perplexity to complexity. These ancient blocks provide an explanation of the separate packages of naps. A single crunch, Africa, even Adria, on Europe could not by itself explain the complexity of tectonic events that built the great piles. Instead, there was a long evolution of the mountain chain, event piled on event, which through one series of naps above its predecessor, there must have been several closures, block to block, not just a single great one, when the opposing continents came into direct confrontation. When one massif collided with its neighbor, this produced earlier phases of deformation, the earlier packages of naps. There was even a pattern to it, a southerly migration of collision events as the African blocks progressively approached the European. There must therefore be more than one root zone, for each of the major events should connect to the line of its own genesis. There was, in short, squeeze following upon squeeze. The last, and arguably the greatest, was the one that left behind the tortured rock along the Insilbrick Line. So great, in fact, that morsels of Africa were carried bodily northwards over Europe. Each of these events was profoundly important in shaping mountains, and yet, viewed from the high vantage point of a passing comet, none was more than another pulse in the slow and inexorable progress of the plates. Lubrication was important. Several of the naps glided on salt, deposited after one of the ancient seaways dried out. During the Triassic, this was the oil that smoothed the passage of mighty segments of the earth, such as the molding of mountains, each one explicable in terms of tectonic principles, yet each stamped with its own individuality. To this extent, mountains are like people, cast from common genetic rules, yet every one having a personality of its own. Mountains are often the personification of strata, and indeed they are often named for their fanciful resemblance to white teeth or a virgin's breasts. Alpinists struggling with difficult peaks always seem to address their adversaries in human terms rather than as examples of tectonics in action. The Matterhorn, on the border between Valais, Switzerland, and Piedmont, Italy, is celebrated for its precipitate sides and for the fact that Colonel Whymper lost 4 men in its conquest in 1865. Less well known is the far more astonishing fact that its upper portion is actually a part of Africa thrust bodily northwards over Europe. The character of the mountain and the face it presents to the climber is as surely a product of its geology and the subsequent effects of weathering, as our own character is a consequence of our genetic makeup acted upon and modified by the vicissitudes of our upbringing. It is time to leave Africa and head northwards again, back into the Alps to look at one of the ancient massifs. From Bellinzona, this means following the Ticino Valley upwards, to the west of our path down from the San Bernardino Pass. The climb on the old road to the St. Gothard Pass proved to be a reverse replay of a descent. My visit there was obscured by low cloud. What should have been a splendid panorama was reminiscent of a late Turner painting, a kind of dramatic but milky obscurity. But it was still possible to inspect up close the rock of the Gothard Massif. This is the heaviest kind of gray granitic gneiss, a rock of ancient and implacable solidity, grim and giving no quarter. It is easy to imagine it as one side of a tectonic vise, or as some kind of bulwark against which naps are no more than pliable mash. The sparse vegetation clearly has a tough time extracting the most meager rations from its impoverished soil. It is the Scrooge of rocks. Time to move. O.N. The next massif northwards is the A.R. Massif. More grim gneiss is forming intimidating cliffs, sandwiched between the Gothard and the A.R. like a thin slice of Parma ham between 2 halves of a loaf, is the root zone of another of the great nap packages, the Helvetic naps. At the foot of the St. Gothard Pass, the town of Andernach is nearby, one of those places with a kind of storybook Swissness. On the edge of town, near the railway, and in a much less picturesque quarter, is a large, dull gray barracks, behind which the root zone crops out on the hillside. The cliff displays a series of yellowish crushed limestones as along the Isubbrick LIN, they are vertical, with a squeeze mean. We have come full circle, for this is also the root zone of the Glarus Nap, where this journey began. This is the time to envisage the mighty piles above you, how erosion of the higher naps has opened windows, giving on to the earlier tectonic events, how the mountains are still rising, while frost and rivers incessantly seek to render them low, and how all this is accountable to the movement of plates. Modern research is focused particularly on deep processes and structures in the lower crust and upper mantle, as revealed by seismic reflections. Here you can see how the opposing continental masses really meet. For example, it is likely that a wedge of Adria impinged into the guts of Europe. Such was the northward heave of the greater continent to the south. This, the most studied range in the world, still has secrets to reveal. There is one rock type to mention as a postscript: molasse. The typical locality is the mountain known as the Rigi, west of Lucerne, but the whole area on this shore of the Weirwald is made of it, an old-fashioned plum pudding kind of rock, a pebbly potpourri, including rounded cobbles of all manner of other rock types. I saw many pale limestone pebbles, some sandstones, even some pieces of what I took to be nice, and all dusted with a kind of pinkish skin. It is a massive rock formation, underlying whole mountainsides. The molasse provides a record of the wearing down of the alpine range at a late stage. Unlike the flysch, it is largely non-marine. The cobbles and pebbles had their edges knocked off in raging torrents, and they were rounded further in their inexorable progress downhill. Every cobble in the molasse represents a bit broken off a mountain. They were collected together indiscriminately in the deposit. A mountain side of this conglomerate is a mountain destroyed elsewhere. The rivers of 10 million years or so ago drained northwards into a basin that now occupies the Swiss plain, and so molasse underlies the serious business side of the country, even commerce, bows to geology. By the time they had reached this point, much of the energy of the waters had abated and was insufficient to move pebbles, so sandy and silty rocks predominate under the plain. Around Lake Lucerne, though, there are coarse rocks laid down in ancient channels or spread out by floods. Down by the lake the molasse slopes are gentle, and the soil is a reddish color that I do not recall seeing elsewhere on our journey. There are old orchards everywhere, but the most profitable crop these days is tourism. Down at Weggies, the Seehof Hotel du Lac is the very picture of luxury, with a waterfront having Venetian pretensions and wrought iron balconies and blue shutters. It was fashionable when built a century ago, and is now quietly dignified and expensive in maturity. The foreigner's vision of Swiss elegance, perhaps, but I like to think first of the apple orchards on the hillside above, growing on red soil that has been derived from the weathering of peaks long since vanished. The revolution wrought by tectonics has been finally converted into fruit. We have been on a journey through a small part of a great range, and that range is itself connected to others that extend as far as the Himalayas and further through the Malayan Peninsula to Indonesia. Although it is a classic area, it would be foolish to expect the Alps to be a surrogate for all mountain belts everywhere. The world is too rich and complex for that. The Alps are, for example, poor in granites, those most implacable of mountain makers, and most of those that do occur are ancient rocks caught up in the later earth. Movements, asterisk no matter. We shall meet them elsewhere, nor are naps as important in some other mountain belts. The Alps were the product of a particularly hard docking of one continental mass against another. Push invariably came to shove, but it does not have to be so violent, and we will encounter in other places fragments of ocean floor caught up in tectonic mayhem. Actually, these do occur in the Alps, for the mappers had accurately recorded serpentines in their accounts. It just took a very long time for their significance to be appreciated. According to Rudolf Trumpy, if they had been recognized for what they were, the whole theoretical edifice of plate tectonics might have been deduced from the Alps. But this is to anticipate things to come. What can be said without blushing is that the elements that we met in our journey round Glarus are common to mountain belts through much of geological time and in most orogenic belts. There is flysch and molasse associated with many folded ranges. I have labored long hours trying to find fossils in flysch nearly 500 million years old. No fishes to gape at me then, just the little hacksaw blades of graptolites. Then, too, the Earth's crust has buckled and shortened in every mountain chain, and where it has thickened, metamorphism has produced gneisses not so different from those we saw on the San Bernardino Pass. Strata from ancient seas have been thrust up to cap high peaks. There are fossil shells at the top of Mount Everest. Virtually all ranges, too, are composite like the Alps, with one event following another as the mountains evolved over several tens of millions of years. Convolution and concatenation, folding and refolding, buckling and cracking or heating, and bending. Squeezing followed by collapse when the pressure is off. It is about as complicated as geology gets. Sometimes rocks are so perturbed and disguised that it is hard to say what they once were. Mountains demand an explanation beyond the fury of the Titans. After all, the thoughtful travelers soon realized that many mountains came in linear ranges. There had to be a design to the earth beyond the pettish whims of the gods. The 17th century Jesuit Athanasius Kirchner saw mountains as an internal skeleton, the bones of the earth. When you view the Alps from a distance, perhaps this does not seem quite so absurd, especially since hard and resistant rocks often take the high ground. Rocky bones indeed. Kirchner's Mundus Subterraneus of 1664 continued to be quoted until well into the 18th century and was, at the least, a stimulant for thinking about mountains in the context of a global explanation. The search for a theory of mountains was to occupy many more able geological minds for the next 300 years. The Alps were always central to the arguments. With their gift for abstraction, it is perhaps not surprising that the French played a prominent part in the process. Since Descartes had freed the wondering mind from theological baggage, the world had become their philosophical oyster. Léonce Elie de Beaumont, 1798 to 1874, was the director of the carte géologique, a mighty undertaking to map the rocks of France completely for the first time. He was by training a mathematician and inclined to view the world as deducible from mathematical principles. He was gifted enough to become the top graduate from the École Polytechnique in Paris, forcing ground for the elite, and became a distinguished field geologist. His achievements probably induced in him a certain arrogance, and Elie de Beaumont did indeed become a monolithic authority. For 30 years, between the 1820s and 1850s, he published influential works on the causes of mountain building. Recall that this period coincided with the acquisition of basic data from the rocks themselves, the heroic efforts of those who climbed the Alps with pencil and paper in their knapsacks, as well as a hunk of bread and cheese for lunch. So Elie de Beaumont was theorizing in tandem with new and hard-won discoveries in the field. The same period also saw the rise to prominence of the scientific methods advocated by Charles Lyell, with which this book began. Lyell himself had considered mountain formation in some detail, in line with his uniformitarian notions. He had conceived of grand elevations by the continuous accretion of existing effects, particularly the uplifts in topography that were known to be produced by earthquakes and volcanoes. It was a case of excelsior little by little. By contrast, Elie de Beaumont saw violent revolutions narrowly, confined to zones of weakness in the earth, and limited to special periods of global unease. He was aware of the growing evidence for powerful folding in the Alps. No mere nudging could produce such contortions. He was also attracted to measuring the lie of the mountains and plotted their linear trends, with an eye to their systematization. Elie de Beaumont was in little doubt that the folding and thrusting he and others had observed in the Alps resulted in an overall piling up of the strata, what we would now recognize as crustal shortening. Some of his results were published in the Philosophical Magazine in 1831 as researches on some of the revolutions of the surface of the globe, presenting various examples of the coincidence between the elevations of beds in certain systems of mountains and the sudden changes which have produced the lines of demarcation observable in certain stages of the sedimentary deposits, Philosophical Magazine, Volume 10. If an author were to submit such a title today, the editor would faint with shock, but it does save me the trouble of explaining what it is about. It is tempting to seize upon the revolution in the title. After all, revolution was likely to figure high in the consciousness of a Frenchman, and Lyell's modest changes, which affect much in small steps, provide the model for accomplishing reform through continuous parliamentary democracy. Lyell's ideas were also crucial to the young Charles Darwin. Evolution, not revolution, has been claimed as the mantra of democracy. The clash of opinion on the origin of the Alps is often presented as a test case for the great 19th century debate on uniformitarianism versus catastrophism, but it is not as simple as that. Many geologists of fundamentally Lyellian persuasion were impressed by Elie de Beaumont's results. His political equivalent as the head of the British Geological Survey, Henry de la Beche, was one of them. Other processes might be involved in mountain building than mere up and down. But what he viewed with favor Elie de Beaumont's idea that the Earth was contracting as a result of its slow cooling, mountains being thrown up as periodic adjustments of the crust to accommodate a diminishing circumference. If we suppose with Elie de Beaumont, he wrote in 1834 that the state of our globe is such that, in a given time, the temperature of the interior is lowered by much greater quantity than on its surface, the solid crust would break up to accommodate itself to the internal mass, almost imperceptibly when time and the mass of the Earth are taken into account, but by considerable dislocations. That, almost imperceptibly, combined with considerable dislocations, is suggestive of revolution by stealth, of having his Lyellian cake and eating it, too. Elie de Beaumont is commemorated by the mountain that carries his name in the Alps, the New Zealand Alps, not the Swiss. By geologists he is remembered, if at all, for the aberrations of his maturity rather than for the brilliance of his youth. Obsessed with finding a mathematical design in the arrangement of mountain belts, he developed what he termed the raison pentagonal. He ascribed the directions of mountain belts to regular pentagons, drawn on the surface of the globe, the pentagons themselves being derived from the intersection of 15 great circles. His lines were zones of weakness along which mountain belts preferentially aligned. This, he believed, was where the subterranean controls on folding were expressed on the ground. It was a total global system, a theory of almost everything. It was also an idée fixe for Elie de Beaumont, and he defended it to the last, and with his by then considerable authority. When anomalies in his system were discovered, he simply made it more complex to cope with them until his intersecting lines drawn on the Earth resembled a spider's web. To historians of science, the situation is a classic one. It is reminiscent of the epicycles that had to be introduced to retain an Earth-centered astronomy. To account for awkward facts, the system of orbiting planets was tinkered with until it collapsed under the weight of its own modifications. Similarly, the raison pentagonal died with the great geologist. Of course, with the wisdom of hindsight, we might say that Elie de Beaumont was half right, as we shall see. There are zones of weakness where tectonics reawaken. He was more accurate in his reading of the Alps than was Lyell, and one day a great Earth system would indeed be discovered. His ambitions had exceeded what was known of the Earth at the time, and his grand mistake obscured his grander virtues. History sometimes cheats reputations. Edouard Suess had more of the geology of the Alps at his command than any of his predecessors. After all, it was home territory for him. He was as averse as Elie de Beaumont to the notion of mountains as areas accountable to uplift alone. Everywhere he saw evidence of lateral movement of rock formations, piled on one another. He was familiar with much of the country we have, explored, and he read it well. Seuss never thought other than globally. Like Marcel Bertrand, he made connections between mountain chains joining one to another like a cordon drawn across the continents, and he knew that such a global phenomenon required a general explanation. The Andes and the Rockies were all grist to his tectonic mill. By the end of the 19th century, it was accepted that there were many ancient mountain belts and that the history of the planet had been punctuated by mountain-building events, or orogenes. We shall be visiting some of these old scars on the face of the earth later in this book. Whatever the cause of mountain ranges, then it must be one that could stretch back through geological time. Exactly how much time that involved was far from clear when Seuss wrote Das Antlitz der Erde, but it was certain that many millions of years were necessary to lay down the rocks of seas long vanished, elevate them into mountain chains by whatever means, only to have them worn down to contribute to the next cycle of sediments. When Seuss compiled his synthesis of the world, the geological scale of time periods based upon the succession of stratigraphy and fossils, Cambrian, Cretaceous, and the like was essentially in its modern form. But much finer subdivisions of geological time had also been introduced. As an example, Seuss went to great lengths to show that one small part of the Cretaceous, termed the Cenomanian stage, was a time when the seas advanced widely over the surface of the globe. What was not known was how, many millions of years ago, this event happened. A radiometric scale that could measure it was still to be developed. Still, the scientific basis for correlation of rocks was sufficient to make generalizations about when and how the past upheavals of the earth had happened. In Europe, three main mountain-building events, Caledonian, Variscan, and Alpine, respectively, served to divide the history of the continent. They were times when the earth convulsed, when Lyell's slow ticking of the geological clock was speeded up. Between times, the earth was calmer. For Seuss, summing up folding and thrusting in a dozen mountain chains, orogenic events happened when the earth shrugged violently and pulled itself together. After all, he maintained, the earth was contracting in volume. When the strain became too much, mountain ranges were the planet's way of coping. Edouard Seuss was a thoroughly political animal. He was a member of the Austrian parliament for 20 years. He knew how to make a case. Das Antlitz der Erde is more than a brilliant summary of how the world was made. It is also a disguised polemic for Seuss' view of it. He first set out to establish geology's omniscience. An early chapter deals with the biblical flood, the discovery in Mesopotamia of the clay tablets known today as the Epic of Gilgamesh, and to Seuss as the Azubar epic, allowed for a new interpretation of the biblical event. The tablets in the Akkadian language describe the flood as history and in some detail. The decipherment of the tablets was a state-of-the-art discovery. Seuss took the account on point by point to show that the flood was a geological event, a tidal wave or tsunami approaching from the sea rather than the result of exceptional rainstorms coming from the mountains. It was the first attempt to demystify the flood asterisk. Geology was a great rationalizing force, and throughout his huge compilation, Seuss could not resist providing a rational explanation for legends. Here he is entertainingly slaying a dragon. Trionyx aegypticus lives in the neighborhood of Beirut, and it is a remarkable fact that the crocodile of the Nile still exists in the nearby estuary of the Nar-e-Zirka, or Crocodile River, 3 kilometers to the north of Caesarea. Pliny knew of a town, Crocodilian, in this neighborhood. These facts also throw unexpected light on the numerous and circumstantial accounts of the slaughter of a scaly monster by the knight Dietrich von Gosen on the island of Rhodes in the first half of the 14th century. Curiously, Schiller, whose Wilhelm Tell was linked above with one of the classical geological sites of Switzerland, also wrote a poem about this dragon, based on an account by one J. Bosio, published in 1594. Seuss was equally concerned about promoting his view of tectonics. A complete revolution of opinion has taken place as regards the formation of mountain chains, he wrote, and it was his own ideas to which he was referring. When he wished to underscore a point, he resorted to italics, so the reader is infallibly guided to the nub of the matter. The dislocations visible in the rocky crust of the earth are the result of movements which are produced by a decrease in the volume of our planet. Nothing ambiguous about that. The shortening of the earth's crust observed in mountain ranges was inescapable, since it was also clear that such linear chains had a long history, perhaps extending back in time for hundreds of millions of years. There had to be a way to explain the inevitable telescoping of all those strata. A decrease in the Earth's volume would provide it, but Seuss regarded ocean basins as areas of subsidence, so there was no opportunity to reduce the area of the Earth's surface there. It would take ocean floors spreading to balance an apparently impossible equation, as we shall see. The ancient cores of continents seemed to be inviolable forelands onto which the mountain structures spilled, as would a wad of clay squeezed between two bricks. It had to be the mountain chains that took the strain and initiated the next geological cycle of erosion and sedimentation in the long, slow dance of the earth. As for the Alps, the details of a single outcrop confirmed the larger scheme. Here is Seuss' description of the kind of country we have explored. In this chapter, the flysch has been driven like a plastic mass, and the great advancing sheet of Cretaceous limestone rears itself up, creeps upwards over the flysch, assumes a vertical position, and finally turns over backwards. Heim has termed this a turnover clip. It is precisely these ends of the sheets which have directed attention anew to the diminution of the Earth's circumference. Home territory is always the most persuasive, for it is the number of sheets lying upon one another as seen in the Swiss Alps which most impresses us with the magnitude of the phenomenon, i.e., shortening from Glarus to the world. Indeed, the image that was often used to illustrate Seuss' idea was a drying and therefore shrinking apple, whose wizened countenance and ridges and furrows seemed appropriate for the visage of the earth crossed by mountain ranges. The metaphor was taken so seriously that pictures of old apples actually appeared in textbooks. Perhaps it was secretly hoped that this apple would be to tectonics what Newton's was to physics. As recently as 1952, the presidential address to the Geological Society of London was on the topic of a contracting Earth. I like to think of a succession of observers contemplating a mountainside, perhaps the one across the lake from the hotel balcony by the Erner See where Wilhelm Tell jumped to freedom. Old Kirchner would have seen a kind of girder reaching from the innards of the earth. Charles Lyell might have seen the consequences of 10,000 tremors. Elie de Beaumont might well have seen the same strata as a mere grace note on the réseau pentagonal. He might have smiled briefly to himself, recalling the beauty and completeness of his system, then frowned momentarily while recalling some critic or other, and Edouard Seuss would have seen folding as yet more incontrovertible evidence of the incessant, slow shrinking of the earth. The image hitting the retina would be the same for all of them, but what is actually seen depends on the secret workings of the brain. Seeing is not believing. Rather, it is belief that governs seeing. The modern observer, he might see little squirming strata on the back of the collision of Adria and Europe. No doubt the present-day viewer is closer to the truth than any of his predecessors, and the advances in understanding in the last half-century have been enormous and permanent. But it would be foolish to suppose that an observer a century hence will see nothing differently. Autres temps, autres yeux. By the time Arthur Holmes wrote his textbook, the structure of naps was well understood. Heim and his successors' magisterial maps had been published and digested. In the 50 years after Seuss, physicists had been to work on the idea of the secular contraction of the Earth, which was originally based on the concept that the Earth was a cooling body. The discovery of radioactive heating upset all the calculations. It just wouldn't work. We shall soon meet those who thought, on the contrary, that the Earth was expanding. The poor old Earth could apparently be pumped up and down like a balloon. The global pattern of mountain belts was well known, and Edouard Seuss deserved much credit for outlining them. But as Holmes remarked, the assemblage of mountain systems combines into a world pattern of apparent simplicity, which nevertheless masks a variety of details that remain perplexing and unexplained. There had to be a mechanism for the emplacement of naps that did not depend on the contraction hypothesis. It must be a force capable of moving large chunks of strata laterally at low angles. Newton's pristine and unshriveled apple might have its place in the argument after all, for gravity is such a force. The higher naps in the alpine pile might, in this theory, have slid into place on a lubricated sole of salt or some other tectonic oil. As they moved, they also folded progressively. You can get some impression of how it works if you lay well-puddled clay in a thin sheet upon a board and tip it upwards. If the consistency of the clay is correct, it will eventually slither and fold under the influence of gravity. In the 1950s, several serious academics, especially Hans Ramberg of Uppsala University in Sweden, spent a lot of time on clay models and sometimes produced good simulacra of nature. Analog models have developed considerably since those days and are now used extensively in the oil industry. Curiously, the gravity sliding theory was, in essence, a revival in sophisticated dress of Charles Lyell's notions of uplift as the essential control on mountain building. For you also need to elevate some region along the growing mountain belt to produce a height from which the naps could slide. Such a line of elevation became known as a geanocline, an upward swell running along the axis of the mountain chain. As the geanocline rose upwards, naps glided off like slicks from the back of an emerging whale. This might satisfactorily explain the higher naps. But then you also need an explanation for the kind of naps which we saw at the San Bernardino, past those that involve deeper and older rocks, metamorphosed under high temperature and pressure. How do you get them to rise up from the depths? It is a slightly difficult concept to grasp. Arthur Holmes explained it like this. The deeper and hotter parts of the infrastructure were where these burial effects are most intense, as in the core of an orogenic belt, and hence the zone rises to higher levels and may pass high into the superstructure. Deep, hot rocks flow upwards, deforming and creeping like a contrary glacier of the underworld. There was a model for this process in the salt domes of the Middle East. Deeply buried, deposits of sea salt dome upwards and pass through overlying strata as a kind of intrusive lobe. Eventually emerging at the surface, the rising tongue is called a diapier. I examined one of these salt domes in the Oman desert. It makes an improbable hump hundreds of meters across in the middle of a stony, flat wasteland. You can see it from miles away. A partly flowing, partly crusty, hilly mass of salt is a curious thing to see in the fiery heat. Even odder is to find all sorts of blocks of rocks lying around that have been carried up with the salt as it cut through strata overlying it, including limestone blocks. With fossils, some of these salt domes have acquired commercial importance as oil traps. The heyday of gravity tectonics came and went as the contracting Earth had done before it. Once more, detailed fieldwork provided critical evidence. In the first place, when naps were very carefully reconstructed back to their original disposition, Imagine refolding those sheets back on the bed. The evidence for any kind of downhill slope was very tenuous. It began to seem as if a push were needed after all. Gravity alone would not do the work. Secondly, as the history of the various parts of the alpine chain was unscrambled, it became clear that the emplacement of naps coincided with the closure of ocean basins, precisely the circumstances when such a push might result from natural causes. The timing of the emplacement of the packages of naps could be related to the history of the massifs and the sediments that accumulated upon and between them. Further research discovered microcontinents like the Bryan-Canese parts of Europe that, like Adria in relation to Africa, had a semi-detached history. It seemed a logical inference that the Alpine mountains were the consequence of the jugglings of all these major pieces of lithosphere, and not just a question of up and down. That uplift was going on was undeniable. Recall the Via Mala, that slit carved steeply into the earth, but this was as much a feature of the present history of the chain as an element in its early evolution. The time was ripe for the Alps to be integrated into the story of the plates, and that of the confrontation of old Africa and old Europe. When that happened, the green Serpentinites and the Pennine naps would suddenly make sense. But this is to anticipate. We leave Switzerland by way of the Jura Mountains. The name of the mountains is famous in geology. It is the type area for the Jurassic system, 205 to 137 million years ago, which, as every child now knows, was when dinosaurs ruled the earth. Rocks of this age are beautifully developed in the area, as you would expect of a type locality, although the ones I saw were all sedimentary rocks that had been laid down under the sea and would therefore yield to the hammer the fossils of humble invertebrates like ammonites, brachiopods, snails, and clams rather than the bones of huge terrestrial monsters. The mountains run in a great swathe northwest of Neuchâtel, where Marcel Bertrand was a professor following the direction of the lac. The Neuchâtel, all along the northern edge of the lake, the southerly facing, hillsides rise in vineyard after vineyard. Beyond the vineyards a wooded ridge reaches to the skyline. The Jura Mountains comprise a series of great ridges like this one, running in parallel east-southeast-west-northwest. They are like the wrinkles on the forehead of a very old man. The high points of the ridges often exceed 1,300 meters, so they are not negligible, even if they are dwarfed by the alpine peaks south of the Lac de Neuchâtel. Between the ridges there are valleys with the same trend, so the whole countryside is one of densely wooded, rising ridges separated by intensively farmed depressions. Corn, beet, and wheat in this pattern extends well beyond the border. Into France, cows have changed from the cute gray Swiss ones to a more everyday red and white breed. Most of the rivers faithfully follow the valley floors, but a few of them turn to cut directly through the ridges in steep-sided gorges. We follow one of these north of Neuchâtel, which traverses the Chaumont. Rocks are well exposed in the sides of the gorge. One difference from the Alps is immediately obvious. No longer are the strata thrown into elaborate contortions. They are tipped perhaps 30 degrees from the horizontal, but one stratum succeeds its predecessor in orderly fashion, younger upon older, as well-behaved stratigraphic sections should. An occasional small twitch in the bedding reminds us that these rocks, too, have not escaped tectonic influence, but clearly we are beyond the reach of the most violent of the alpine convulsions. The little town of Valingen guards the entrance to the gorge. It, too, is a famous name in geology, for the Valentinian is the label attached to the second earliest time division of the Cretaceous. Following on from the Jurassic, the strata in the area record the passage of time from one period to another without a break. Old Valingen is built from the local limestones, which yield deliciously creamy yellow blocks. That the chateau was defensive in origin is obvious, for its massive walls boast round towers on the corners, and its entrance is heavily fortified. The block-like big house tucked away safely inside is functional first, luxurious second. This place was evidently built to protect the route running through the gorge. In Valingen, you are reminded how appropriately villages that have been built from the local geology seem to lie in the landscape. They appear to grow from the hillsides. France, with its abundance of limestones, has hundreds of such towns and villages, from Provence in the south to Caen in the north. No matter if the buildings lack distinction, though they rarely lack individuality, for the harmonious whole is more than the sum of its parts. England, too, has dozens of villages in the Cotswolds with the same charm. Elsewhere, where natural building stone is unavailable, local bricks and tiles still grow out of the land and add their character to the regional architecture. In Provence, I visited the source of ochre, which is a sandstone formation cutting across the vineyards near apartment. How suitable this color wash now seems, rendering walls in the Midi like sunflowers, and much the same shade ochre revels in the rich heat. The structure of the Jura is comparatively simple. The great waves of hill and vale passing over the landscape reflect similar waves in the strata. The ground undulates in harmony with the folding of the Jurassic and Cretaceous limestones. The ridges are anticlines, meaning that the rocks are bowed upwards. The valleys between them are synclines, where the strata are bent downwards in the fashion of a cupped hand. The topography follows the bidding of the underlying structure almost slavishly. Everything else is a consequence of the geological underlay. The cultivated valleys, the wild, wooded hillsides, the courses of the streams, where vines will ripen grapes. Look carefully when crossing over a ridge, and you will see the switch in the general dip of the limestone beds as you traverse the axis of the anticline. On the southern side of the ridge, most of the limestone beds tilt to the south. Northwards, they are inclined to the north, a simple scheme only complicated by the inevitable minor undulations. The Jura is a geological switchback, a sine curve graven into the earth. The form of the ridges was generated as part of the alpine movements. Looking at the map of Europe, it is easy to see the Jura as an outrider to the great wheel of the Alps, flanking all that confusing disturbance, that most unruly and stirred-up pile. Imagine scrabbling up a rug into a mass of folds at one end, while at the other the material is thrown into a series of diminishing undulations. The connection between the Alps and the Jura was not always recognized. It was only with the growth of geology as a globally interconnected science that the marriage of the two regions was established. Here is Edouard Seuss writing in the second volume of Das Antlitz der Erde. There was a time when every single anticline of the Jura was regarded as an independent axis of elevation. Then it became clear that such a collection of parallel anticlines must have a common origin. Next, it was seen that there is a certain dependence between the Alps and the Jura. Finally, the influence of the obstacle presented by the Black Forest was recognized. Seuss saw the Black Forest as part of the foreland against which the Alps were constrained. The Jura Mountains were the relatively minor folds produced as the alpine movements lost their momentum against the immovable block to the north, a series of shrugs of exhaustion. The modern view is perhaps not so different in outcome, except that the cause is at the deep root of things, the northward movement of Africa. The Jura is part of the marginal effects of the convergence between the European plate and its great neighbor to the south. The folding is now considered to be the reaction of a thin skin of sedimentary rocks to the kick of continued alpine movements, lubricated by a detachment in the thick Triassic salt deposits at depth. It is as if the folds in the rug were generated by changing the relief on the especially slippery floor on which it lay rather than by shaking the rug from one side Seismic profiles made through this part of Europe suggest that the deep detachment extends southwards all the way to the Eart Massif. The vines and forest trees on the flanks of the Jura owe their particular habitat to events that happened several kilometers beneath their roots. Thus it is that the intimate details of natural history link downwards into unseen worlds. Everything connects. At the top of one of the ridges, there is a view to Alpes, lying beyond the far shore of the Lac de Neuchâtel. The array of white peaks takes up the horizon, like ranks of shark's teeth. Distance scrambles them together, so it is hard for a foreigner to place them in order. They seem to erect an impenetrable barrier. Yet we know that even in the late Stone Age there were skin-clad men who would brave the remote passes. One of them fell into a crevasse and was yielded up from his natural deep freeze only a few years ago. Forensic paleontologists have determined that he had ibex for lunch and that he may have been shot in the shoulder by a rival. Can it really be true that the Carthaginian general Hannibal Barca drove elephants over the passes 2,200 years ago? We have the word of the Greek historian Polybius that it was indeed so. But before the era of the written word, whether the words we read are true or not, everything has to be established by inference. History envelopes the past in uncertainty, like the mist obscuring the beech trees in the valley below me. The deeper the history, the more the outlines blur, the more inferences about the past are subject to change. In this chapter we have seen how different eyes contemplating the Alps each saw their own version of history. We have a vision for our time, but we can be certain that it will not be the last. Modern heroes have followed in Hannibal's tracks, but this time with map and pencil in hand, unscrambling the secrets of the Alps written in a code of writhing rock. We know that it is not fate that moves mountains. It is tectonics. Geophysicists today poke beneath the great pile with their seismic probes. We now know a great deal about the Alps, their structure, the role of plates in their genesis. There's been a revolution in our understanding over the last 40 years, and the gains in knowledge are permanent. But we will never know everything, and that is as it should be. From the obscuring mist of the past, science has ensured that some of the mountains have emerged into clear view, but as soon as that happens, the misty shadows of further peaks are glimpsed in the distance, rank upon rank. So many other heights to climb, so many mysteries to investigate. Part 5. Plates. There are lands of the imagination that cannot exist but seem real, and there are lands that once existed that somehow seem remote and hard to credit. Perhaps their comparative solidity depends on the hand of a skilled writer. Who can doubt the reality of the countries beyond the sea that Jonathan Swift peopled so skillfully for his hero Lemuel Gulliver to visit, not merely to stimulate the imagination, but as a ruse to illustrate human frailties, puffed up and monstrous in Brobdingnag, or shrunk in Lilliput to petty proportions to match the triviality of their concerns? Yet to travel back in time to the land of the Gondwana, or to try to grasp the reality of Pangaea 250 million years ago seems to require a greater leap of imagination. But these places existed as solid as Africa is today. Somewhere in a middling category is Atlantis, a familiar enough name, but one which is either myth or myth ultimately rooted in reality. Determined, researchers strive to place it on the map with the certainty of New York or Vladivostok. Plato described the kingdom in his Timaeus, locating it in the Atlantic Ocean, or at least beyond the Pillars of Hercules, but theories abound that prefer to place it within the Mediterranean Sea, near the cradle of the classical world. Whichever the preferred location, it's catastrophic. Elimination as a punishment for the dubious ways of its inhabitants was a tectonic one, for Plato describes earthquakes and floods. A cursory search on The internet will show the curious observer how many outre theories exist. About the drowned kingdom, there are claims made for it being in the south, China Sea, and for all I know, on the moon, probably the most plausible. Scenario relates the destruction of Atlantis to the eruption of Thera, now known as Santorini, 70 kilometers north of Crete. This was the biggest eruption that Homo sapiens has ever witnessed, at least in Europe. It has been estimated that 30 cubic kilometers of material was erupted, that is 15 times more than in the famous eruption of Vesuvius in AD 79 that eliminated Pompeii. The eruption of 1700 at sea also coincided approximately with the decline of Minoan civilization and is therefore one of the crucial phases of Western history. The Bronze Age could have had no better source for its subsequent legends. It must have been a most catastrophic blast, for it left a caldera 6 kilometers in diameter. It surely generated a vast tsunami, which would have drowned the vibrant coastal towns of Crete. On Thera itself, direct evidence of burial by pumice is preserved in the town of Akrotiri, where colorful frescoes and wine jars testify to the good life before the fall. The sky would have darkened with sheer volume of ash. The grapes would have withered upon the vine. Misfortune would have fallen with the inexorability of volcanic tephra upon rich and poor alike. The plain dwellers would have been punished with the mountain folk. That Thera was Atlantis is given some credence by Plato's description of the place pre-eruption as comprising several concentric belts of land and lagoons, or rather, characteristic volcanic configuration. According to Robert Scandon, a volcanologist at Rome University, the eruption of Thera may have inspired at least one passage in the story of Jason and the Argonauts. When they returned to Greece with the Golden Fleece, they passed by roads to the eastern part of Crete. Here they experienced a pall of darkness, as indeed they would have done if they were under a cloud of volcanic ash. When they fled northwards, a bronze giant called Talos pelted them with fragments of rock. This hardly requires further explanation. The eastern Mediterranean is replete with flood legends, which are not unreasonably linked with tsunamis in the aftermath of major eruptions. Today, what remains of Thera is the precipitous and sun-bleached port of Santorini and its flooded caldera, which shelters a small fishing fleet engaged in satisfying the demand for fresh grilled sardines in tavernas catering for tourist cruise liners. It is a prosaic way for the Argonauts to be shadowed. An observant passenger on one of these liners might spot Nea Kameni, a small island gradually growing from lava extruded out of sight. Who knows if the volcano might once again wreak destruction? For now, we know that all that destruction was caused by Africa moving northwards into and onto Europe, for Santorini lies at the edge of the Aegean plate. What we see at the surface, of course, is all down to the influence of the geological foundations. But how did this understanding arise? For Edouard Seuss, the idea of foundered lands was meat and drink. Some Atlantis of the mind enchanted him. Before the fundamental difference between ocean crust and continental crust was appreciated, it was possible, preferable even, to think of the oceans as places where continents had foundered. It would be wrong to think of that generation of geologists a century ago as reluctant to admit all change. Rather, they would admit the kind of change they wanted and deny other processes. They appreciated some of the evidence for what we would now call plate tectonics. Gondwana * should be taken as the prime example, because it was the acceptance of the existence of this vanished land that set the seal on modern geology. Seuss coined the word. The Gonds were an ancient Indian tribe. He saw very well connections between the geology of Africa, South America, and peninsular India, and appreciated that they were bound together by more than coincidence. Like finding fragments of an old treasure map, He saw that broken lines must connect to make a picture, and that the picture was a key to fundamental truths about the Earth. When I set out to read through Seuss' dense prose, I had not realized how intelligently he appreciated the evidence of the rocks. Rocks do not lie. They do, however, dissemble as to their true meaning. The most straightforward example is probably provided by tillites. In the 19th century, most geology in remote regions was of no more than reconnaissance standard. Exploring geologists were probing the innards of Africa for the first time, and the dark continent yielded its secrets reluctantly. Reports were sent home to whatever European country had the appropriate colonial interests, there to be published in the Journal of the National Geological Society. Seuss hoarded the insights dispatched by these trail blazers. A rock formation from South Africa was christened the Dwika conglomerate and reported by one pioneer, J. Sutherland, in the Quarterly Journal of the Geological Society of London for 1870, under the title Notes of an ancient boulder clay of Natal. This insouciant title embodies an extraordinary idea. A boulder clay is a deposit left behind as a glacier retreats. You can see deposits broadly of this kind dumped at the foot of alpine glaciers, shuffling backwards in their valleys away from the warm breath of global climate change. The boulder clay is a mucky kind of thing. Dumped boulders of various sizes all mixed together and sealed by a sticky brown clay gum. This is debris dumped unceremoniously by the melting glacier, its dirt alongside its cargo of rocks, unsorted, chaotic. It is like the contents of a badly made, old-fashioned bag pudding. Look closely and you will see characteristic scratches on some of the bigger pebbles where they were scraped along at the base of the glacier. When such a clay becomes hardened and annealed by time, it is called a tillite. Glacial till is the proper term for the deposits of ice, and the suffix "ite," as usual, designates a rock. But the scratches on the boulders are preserved, and so is the potpourri of different kinds of rock types, all jumbled up just as they were picked up and carried promiscuously on the back of the original glacier. So, here in South Africa, in the Great Karoo, was a rock identified as being of glacial origin in a countryside where succulent plants now abound. It was an original idea, to say the least. Nonetheless, the signature of the fossil action of ice is easily read. There had evidently been an ancient ice age in South Africa. These boulder rocks were followed by what Seuss called the Upper Karoo, sandstone. When some of these rocks were split, they were found to contain fossil leaves having something of the shape of bay leaves, but more tongue-like, which is why they were called glossopteris, from the Greek for tongue. Then, in peninsular India, very similar conglomerate rocks were discovered. In what Seuss called the Talcher stage of these beds of boulders, he remarks, the resemblance to the Dwika is very striking. Evidently, the ancient glaciation extended beyond South Africa. As if to confirm this judgment, leaves of the fossil tree Glossopteris and its associate gang, Amopteris, were found in overlying strata in India, just as they had been in Africa. Seuss goes on to describe many Indian basins bounded by fractures in which the lower Gondwana coal derived from these fossil trees can be exploited. Glossopteris is unknown in Europe or North America. It was a peculiarly Gondwanan tree. Nowadays, we could enumerate dozens of plant and animal fossils with a similar Gondwana signature. We can put a Permian, about 275 million years, age on many of the Glossopteris fossils, and we know them well from Australia. Evidence for glaciation is everywhere on Gondwana. I walked along a wadi in Oman in 1995, in the midst of the Arabian Peninsula and in a bone-dry desert, where the sides of the valley were lined with glacial boulder beds as blatant as any I have seen in the Arctic. The floor of the wadi looked as if some gigantic dragon had been sharpening its claws there. The grooves were gouges left in the rock floor by an ice sheet. Thus evidence is piled on evidence until the signature of Gondwana. Its Permian life, its Ice Age seems as graphic as the artifacts that define ancient Egypt, but the outline of it all, the facts that lay at the fawns, E.T. Origo, were available to Edouard Seuss. As he said, an undeniable resemblance exists between the structure of South Africa and that of the Indian Peninsula. He surmised that the former continuity of Gondwana was the appropriate explanation, * the Indian Ocean only subsequently separating the fossil tongues that spoke to him so eloquently. Then came collapse. A new ocean was created, and the continents assumed other forms. Out of the abyss of the ocean arises the great island of Madagascar, presenting all the characters of a Horst as to adducing evidence from other sources. Seuss remarks, eminent zoologists have been led to imagine the existence of an ancient continent on the site of the western half of the Indian Ocean to which the name Lemuria has been given. There are indeed similarities between the animals of Africa and India that were accounted for by the existence of a bridge of land joining the two areas, or by a foundered continent. In either case, Africa and India as we know them were in the past, exactly where we see them today. So the world apparently all makes sense with the facts, tucked away into a neat bag of theory. But of course the description was all wrong. It is worth reflecting upon what we would now see as an obvious mistake. Most theories are of their time, and Seuss was no exception. More facts are acquired, and in the end, a mistaken theory is jettisoned and then forgotten. The discovery of what made the ocean floors basalt, and more basalt, is one obvious fact that falsified the subsidence theory. No foundered tillites there, nor Glossopteris fossils. However, that the foundering idea was capable of such falsification still qualifies as a scientific theory, at least if one accepts the criterion of science that Sir Karl Popper has explained in Conjectures and Refutations. The scientist has a license to be wrong. The theories that cause much more trouble are those that can twist and turn in a breeze of new facts without ever fracturing completely. In fact, fixity of continents was already being challenged not long after Seuss' magnum opus was translated into English. It is one of the famous stories in science how a German meteorologist, Alfred Wegener, proposed continental drift many years before it was widely accepted that the continents were neither fixed nor the residues of a swathe of Atlantises. Wegener's first account was published in German in 1915 and was largely dismissed. It was translated into English in 1922 and probably only came to be on the serious scientific agenda by the time of the French edition of 1936, La Genèse des continents et des oceans, although even then it was regarded by most Earth scientists as distinctly wacky. Wegener pointed out, and he was not the first, the fit of the continental profiles, the western coast of Africa and South America, Madagascar, far from showing all the characters of a Horst, seemed instead to wish to snuggle back against the East African coast into an indentation that closely matched its western outline, and India and Africa were once joined. Gondwana was a united entity over which an ice sheet might move, or a forest might spread. The continents must have moved to their present positions. You could shuffle them back into their original contiguity by solving the jigsaw puzzle of their coastlines. Drift South America back towards Africa and sea. They locked together in a happy marriage. The ancient glacial deposits made sense that there had been an ice sheet centered upon this Gondwana, but it must have occupied a different latitude at that time, nearer the pole, to support such frigidity. Glossopteris and its allies spread over the cooler parts of this united world, and there were early reptiles that could stroll unencumbered throughout the same ancient glades. The idea of continent fusion was taken still further by Wegener. Perhaps all the continents were once fused together into one supercontinent. At this distant time, all dry land was annealed. Terra firma and sea were most perfectly parted one from another, for a single vast ocean counterbalanced one huge continent. North America and Europe/Asia were conjoined in the same way as South America and Africa. The North Atlantic Ocean had yet to appear, according to Wegener, in late Carboniferous times as huge. Northerly continent was bound to Gondwana as well. The current geography of the Earth was claimed to be a legacy of a marriage of all continents, consummated more than 250 million years ago. The current continents resulted from the breakup of this continental behemoth. They had moved, apart drifted, to their present positions over many millions of years. This was, by any standards, a profound reorganization of knowledge. Gondwana was the name applied to the United India, South America, Australia, Antarctic portion of the supercontinent. Laurasia usually refers to the northerly part, the marriage across the North Atlantic. The whole is known as Pangaea, from the Greek for universal world. I shall concentrate on the Gondwana portion, if only because the evidence for or against it figured so prominently in the history of the debate about the origin of the shape of the world. Originality may be the capacity to look at the same facts and see new explanations. Much of the same evidence that Seuss had adduced was paraded again by Wegener to draw an utterly different map and to make predictions as different from drowned continents as could be imagined. And just as Seuss' theory died by its predictions, so the notion of Gondwana and of Pangaea finally lived by virtue of facts that were still to be uncovered. The drift hypothesis explained to Wegener the crumpling up of mountain chains. The movement apart of the continents entailed the elevation and folding of ranges at their further edges. The rucked western edge of South America, the huge arc of the Himalayas, pushed upwards as India collided with Asia. To see the world as it should be seen, he implied the world must be looked at as a totality. The fate of mountains was bound up with the fate of oceans. Perhaps if Wegener had had the eloquence of Dean Swift or John Bunyan, then Pangaea or even Gondwanaland might have rapidly achieved the cultural currency of fictional Lilliput or the Slough of Despond. Instead, the concept lurked on the fringes of respectable science, like some eccentric location for Atlantis. More than 40 years elapsed before a version of Wegener's surmise hardened into something like a fact. But there were champions who kept the idea alive. Through the 1920s and 1930s, these were primarily field geologists who worked particularly in the southern hemisphere, where the evidence was most striking. The South African Alex Du Toit summarized a mass of information in Our Wandering Continents. 1937. He went far further than Wegener in identifying strong connections between the Gondwana fragments. There were South American rock formations that trended towards the eastern coast of that continent, where they were more or less abruptly truncated at the Atlantic Ocean. He claimed that their natural continuation could be found in southern Africa and beyond, into Australia, close the Atlantic and Indian Oceans, place the continents back together, and the match was perfect. No shattered Minoan urn from Santorini could be repaired with greater confidence. Wegener himself had described the logic behind such observations. It is just as if we were to refit the torn pieces of a newspaper by matching their edges and then check whether the lines of print run smoothly across. If they do, there is nothing left but to conclude that the pieces were in fact joined this way. Most geologists today would accept such evidence without demur, but it was still fringe science when Du Toit was publishing. Geologists didn't travel as easily then as they do today, so skeptics would not go to the trouble of taking a steamer halfway around the world just to disprove some crackpot idea that was bound to crumble under scrutiny. Geologists met at the International Geological Congress in some capital city every 4 years or so, as they still do. But not everyone could afford to attend, and the best funded, and therefore the most numerous, attendees were mostly Americans, who included the most convinced anti-drifters. "What's all this nonsense, you?" can almost hear them ask. "How can a continent motor across an ocean?" We all know that the resistant forces of rocks could not accommodate any such motion. The opponents included some of the intellectual heavyweights of the day. Harold Jeffreys was a brilliant geophysicist who wrote the standard textbook, published in 1926. He summarized Wegener's theory as an impossible hypothesis and concluded that the assumption that the Earth can be deformed indefinitely by small forces, provided only that they act long enough, is therefore a very dangerous one and liable to lead to serious error. In a word, there was no mechanism for continental movement. That same year, the American Association of Petroleum Geologists Symposium in New York was the first convened to discuss the subject of drift. Virtually everyone was against it. I wish I could report that those of my own persuasion paleontologists were more positive, but it was not generally so. Charles Scutchard of the Smithsonian Institution in Washington favored land bridges across the Indian Ocean and elsewhere as the conduits of biological similarity. Where had they gone? Why, they had foundered in Suessian fashion. It may be significant that Scutchard had made his name studying fossil brachiopods, an important group of seashells unrelated to mollusks of an era much older than Pangaea. The world was differently arranged again 500 million years ago, and Scutchard's prejudices may have been forged by an even earlier world in which, indeed, continents were once more separated. The credit of the paleontologist is somewhat restored by one of my own former colleagues in the Natural History Museum in London, the paleobotanist A.C. Seward. After he had studied the distinctive flora associated with Glossopteris, he found the assumption of the existence of Gondwana more probable than any of the alternatives. He said as much in several papers published in the 1920s and 1930s. Those who studied the fossils of the Indian subcontinent in the field followed suit, notably the remarkable Birbal Sahni, who founded a botanical institute in Lucknow that still carries his name. Other paleontologists on the anti-side invoked drifting logs and seeds. The distinguished mammal expert George Gaylor Simpson called them sweepstake routes to explain far-flung similarities between species. Reports of lizards clinging to floating stumps in the mid-Pacific were eagerly garnered in support. What a lizard could do, Glossopteris could do better. Many tectonicists were on the opposition side, too, and those with thunderous reputations carried their less extrovert colleagues and students with them. Hans Still was a formidable advocate of the importance of vertical movements in tectonics. Not for him the slithering, sideways movements of drifting continents where all was push and thrust. No, he was a stabilist. German professors of that time were like God, only more frightening. There were, besides, other things pressing on the German national psyche at the time. Perhaps the fate of mountains was low on the agenda. In the United States, there were other stabilists almost as formidable, but they did not have it wholly their own way. Emile Argand's nap theory of the Alps saw mobility of the crust everywhere, and evidence that rocks could indeed flow was accumulating. But in spite of the efforts of the few, the consensus carried the day. For more than 30 years, the idea of mobile continents lurked out of sight of a scientific establishment predominantly certain it was untrue. Continental drift was an appealing distraction, a siren song that needed to be resisted by those grounded in the certainties of physics. If it can't move then, it didn't move. To acknowledge the reality of Gondwana would have had the effect of changing just too many things in the geological status quo. One is reminded of the lines O.F. Hilaire Belloc on the fate of Jim. Always keep a hold of nurse, for fear of finding something worse. But what of Arthur Holmes? Holmes was, in fact, one of the early pro-drifters. It is clear from his correspondence that he appreciated the explanatory power of the new theory. He was an Africa hand as well. His first geological employment had been on a mineralogical survey there in 1911. This was pioneering exploration in Mozambique, in the most remote country imaginable. His diaries reveal a buoyant enthusiast whose powers of expression did not yet quite match his powers of observation. He was a young geologist in love with his trade, and any scientist will recognize his intemperate zeal to be up and doing, out and discovering. Academic instruction is like fitness training. Its point is only revealed when racing over the ground. What Holmes saw in Mozambique was not immediately concerned with the problems of Gondwana, but exposure to field conditions could help, but prime his mind to the scale of things. Some years later, Holmes had a position in the University of Durham. He had tenured employment, and his work on the age of the Earth had earned him respect in the geological community, even if he had made a few enemies, as well as many friends. In December 1927, he read a paper to the Edinburgh Geological Society where he revealed his pro-drift colors. It was an extraordinary presentation and anticipated so much of what was to come. Not only did he accept that drift had occurred, but he also suggested its elusive mechanism. Holmes' work with radioactive elements had made him aware of the possibility that they could be a source of heat. He proposed that the differential effects of such heating created convection currents in a deep substratum. Solid, yes, but sluggishly flowing over millions of years in an analogous way to the proverbially slow creep of glaciers. The upward limbs of the convection cells reached the lithosphere and then parted in opposite directions, much as the surface of simmering pea soup develops a pleat between boiling vortices. The drag of the convection cell provided the motor that moved continents. Where the cell arose beneath a continent, it could split it and create a new ocean. Where a cell turned down again, it might pull ocean crust with it to produce an ocean deep. The account is almost clairvoyant in its anticipation of future discoveries. His heat-based scheme was summarized by Holmes as a purely hypothetical mechanism for engineering continental drift. This is almost like referring to Darwin's Origin of Species as a modest proposal possibly germane to the appearance of new forms in nature. However tentatively couched, it did not go down well with the leading anti-drifters, including Harold Jeffreys, who was obdurate about this force being as inadequate as any other for transporting continental slabs. Recall that his own textbook was but a year old. The gap between reading a paper and its publication is one of the running complaints that scientists have, and Holmes suffered very badly with this seminal work. The relevant volume of the Transactions of the Royal Society of Edinburgh did not appear until 1931. It is worth remembering that arguments about who made the critical discoveries of the AIDS virus have hinged on matters of days, even hours. In recent years, priority of discovery has become a crucial passport to scientific glory. This has occasionally led to jiggery pokery, as one research team has attempted to nudge a nose ahead of another, and publication priority is crucial. The leading journals, Nature and Science, keep discoveries under strict embargo until the very day of publication. Less scrupulous scientists sometimes speak to the press before they speak to their colleagues. Perhaps it was as well that continental drift was so profoundly unfashionable in the 1920s and 1930s. Holmes' paper was seen by his critics as being merely the latest folly in a minority delusion. As one of them wrote, "I believe that we Need to apply elementary physics and mechanics to the continental drift. Problem to show how impossible drifting would be. Arthur Holmes would have to wait more than 30 years to establish his priority. But Holmes did not lose faith in mobile continents. Rather, he was sympathetic to the evidence subsequently accumulated by Alex du Toit and the paleobotanist. Perhaps he appreciated better the hardships under which such evidence had been acquired than did his chair-bound critics. He believed that the rocks ultimately would speak the truth and that appropriate theory would follow. When the first edition of his Principles of Physical Geology was published in 1944, continental drift was there in the last chapter. It was a bold move for the times. For the price of 30 shillings or $7, the reader could find a summary of the evidence for Gondwanaland. Problems in the imperfect fit of the coastlines were aired, too. Critics had been quick to point out that Gondwana was a jigsaw puzzle that had to be fudged to fit. Du Toit's reconstructions had improved on those of Wegener, but neither was perfect. It was realized later that the true edges of the continents lay not where the shorelines happened to be, but at the edges of the continental slabs themselves, below sea level the rims of the building blocks of the earth. If the 100-fathom contour was taken to represent the outline of the continent, a much better fit of the pieces of the puzzle was obtained. This was another example of the interplay between sea level and terrestrial geology, with which this book started in the Temple of Serapis. The sea is fickle as to the height it laps on shore. Geological reality often operates at a different scale. Holmes' book sold very well despite its stolid title. The first edition, eventually reprinted 18 times. The reviews were good, but some of the reviewers would have much preferred the last section to have been left out. For them, the mixture of fact beautifully explained with speculation almost smuggled in at the end was disquieting. Some followed the geophysicists' view that what is obviously impossible can never be the case, no matter how the evidence appears to favor it. I am reminded of those irritating stickers that get posted on office walls. Don't confuse me with facts my mind's made up, but as any newspaper proprietor knows, the bottom line is sales. A new generation of students brought up on Holmes, the book became synonymous with the man, would encounter the idea of Gondwana in a less fettered way than their teachers had. The young mind is often a more open one. The post-war years were optimistic and innovative times, a time to jettison received ideas. Technology developed during the Second World War was beginning to make an impact on pure research. Ocean depths were there, to be read for other reasons than the pursuit of enemy submarines. Decoders for intercepting enemy signals were ready to become computers. Thanks to jet engines, air travel to remote lands became commonplace, and so it became easier to organize field trips to establish, test, or clarify geological facts. In the mid-20th century, mobility of continents began to seem like a theory, with a chance of being properly tested. Physicists who had been with the skeptics in that war of ideas about continent mobility were about to become crucial to the campaign on the other side. It is interesting to follow the change in the respectability of continental movement theory in the later edition of Holmes. Like all such compilations of second thoughts, the revised book got longer, and some would say it lost a little of its punch. The bulky 1965 edition is the one I encountered as a student. 20 years of second thoughts. It is still nothing in bulk compared with the 5 volumes of Seuss, but it is a dozen times more readable. The final chapter on continental mobility is still there, as is a section on Gondwanaland. Of course, there was no mention of plates. That was for the future. But there was a section on polar wandering. The Earth behaves like a vast magnet. The magnetic field streams from magnetic pole to pole. From time to time, the field reverses north becomes south, and south becomes north. There is a small number of minerals that readily become magnetized. Appropriately enough, the commonest of these, a simple iron oxide, is called magnetite. This is the lodestone, whose interesting properties have been known since antiquity. It is present in several common rocks, of which basalt is the most ubiquitous. There are also plenty of sandstones that contain tiny grains of magnetic minerals. When a basalt cools from molten lava, it passes through a threshold known as the Curie point, at which the magnetite or a related mineral takes up magnetization from the Earth's field as if it had been freshly minted from a magnet factory. These natural magnets point at the poles like a compass. You have to record the orientation of the rock in the field very carefully for reference, because the quantity of the iron mineral is generally rather small. Any magnetometer recording this fossil magnetism has to be very sensitive. Technical improvements in these instruments made in the 1950s meant that magnetization of ancient rocks could be examined critically for the first time. This allowed for determination of paleomag, as it is universally known. Those who do it are almost as widely known as paleomagicians. What they did was, after all, a kind of magic. The ancient rocks preserved the signature of where the poles of the time lay. The rocks pointed their time-frozen finger at the pole as it was at the moment of their magnetization. If everything in the world had been fixed forever, then so should the positions of the poles. Fortunately, magnetized rocks could be collected from many sites scattered over former Gondwana, where the right kind of basalts and sandstones are common. From these measurements, it immediately became apparent that the position of the poles had moved. At first, it seemed possible that the whole crust of the Earth might have slewed around relative to the poles, like the skin on a thick broth when you tip the pan. However, soon enough it was clear that the tracks of ancient pole positions from different continents took quite different paths. This would not be expected if the whole crust had behaved coherently. Instead, each continent appeared to have a will of its own, and they were indeed paths. The ancient poles did not jump around, here and there, hither and yon. Instead, progressively older poles in Africa, for example, shifted away from pointing at the present pole along a distinct track, a journey through time towards a different place. There was sense in the signal, and it pointed to Gondwana. By putting all this evidence together at last, there was a sea change in the respectability of continental movement theory. Precision of physics and delicacy of instrumentation had finally joined cause with the geological hammer when the apparent polar wandering curves for the different components of Gondwana were compared. They only made sense if there had once, more than 200 million years ago, been a united supercontinent. Zeus. Ancient land had finally been explained, and the explanation was accepted by a majority of younger scientists. As Gondwana split up its component, continents embarked on their own tracks, and each saw the poles in a signature fashion as one geological period succeeded another. Lavas erupting on the traveling continents became magnetized, freezing the details of each journey as a diary written in aligned atoms. But all the journeys started in the same place. That was now evident. Then, too, the fossil and ice age details that had been known for more than half a century fitted logically and convincingly into the same scheme. For paleomag also indicated that the South Pole in the late Paleozoic ought to be in the midst of Gondwana, just where an ice sheet might be expected to grow, and where tillites might be left behind to record the legacy of frigid times. Here was something resembling a vanished Antarctica, and after the ice age had waned, cool forests prospered and spread, with their tongue-shaped leaves sheltering special animals that liked it there. It all added up, and the sum of the facts was more than the parts, as is often the case with momentous scientific shifts. It is difficult to cite a date a particular moment in this intellectual drama when the consensus in the geological community changed. Such transformations are somewhat mysterious. The zeitgeist switches in ways which are not necessarily logical, although the principal players in the drama often like to present it that way, nor does everyone shift together. The later, Holmes pointed out that a Russian textbook published in translation as late as 1962 still berated the total vacuousness and sterility of the hypothesis of moving continents. The crucial work on paleomagnetism was already under way less than 10 years after Holmes' first edition. Keith Runcorn, one of the pioneers of these methods in Britain, was certainly a geophysical convert. Before 1956, the proceedings of a U.S. symposium published in 1962 in the International Geophysics series, under the explicit title Continental Drift, show how far views of the more free-thinking scientists had shifted by then, and there were already inklings of the next phase in the great global tectonic synthesis. On the other side of the newly liberated Atlantic Ocean, a symposium at the Royal Society early in 1964 was also overwhelmingly pro-drift. By this time, Americans were among the most radical of the theorists, a position they maintain today. As St. Luke's Gospel puts it, the truth will set you free. And once the continents themselves had been untethered, so, too, scientific imaginations were liberated to pursue their dreams. Mountain chains could now be seen as the consequence of continent shifts and collisions. Mineral plays might prove to be related to continental movement, too. The truth of the world would be rewritten, and who would be first with the new version? Some scientists were laggards, while others surged forwards. Some geology departments took several years to adapt to the new world, but there was little doubt where the cutting edge of geological discovery now lay. It was in the study of the consequences of continental mobility. What Robert Herrick applied to poetry might apply equally to geology. To print our poems, the propulsive cause is fame, the breath of popular applause, the northern hemisphere equivalent of Gondwana, the marriage of Eurasia. And Lorena was already familiar in Holmes' second edition. These continents, too, had split apart at the same time as their Antipodean counterparts, evidence for that greater fusion of Pangaea. The unification of all the continents followed naturally enough. Both traditional geological and new geophysical facts were employed. It would take a longer book than this to list the detailed evidence, and it would perhaps be nugatory to do so, since the arguments are in many ways similar to those rehearsed for Gondwana. There are still differences in detail about the constitution of Pangaea and for how long it was united at the end of the Paleozoic. Early computers were used to produce best fits of the continental shelf margins, but the labor required to produce a pre-drift map was still prodigious. In the mid-1960s, the latest equipment was in the Geophysical Laboratory on Mattingly Rise, just outside Cambridge, where Sir Edward Bullard presided, over the attempt to use the latest technology to solve the fit of the continents. In 1965, the computer fits of the continents around the Atlantic Ocean were published to the breath of popular applause. The originality of Wegener's vision had been successively endorsed, and everyone in earth sciences felt that they were living in exciting times. But what of the oceans? To concentrate attention on the mobility, or otherwise, of the continents leaves out 2/3 of the world. At the same time, evidence for continental movement was firming up. The distinctiveness of the oceanic crust was being demonstrated by improved sampling of the ocean floor. We have seen how new technology after the Second World War also allowed a clearer picture of the topography of the deep sea floor. It was possible to look at the whole Earth for the first time. We followed the fate of a tiny piece of it, the Hawaiian chain, in some detail to show how movement of an oceanic plate accounted for so much of the local features. How was the link made between what went on in oceans and what was now accepted as happening to continents? The crucial step was the appreciation of the structure of the mid-ocean ridges as the place where new crust was manufactured. The relevant observations were made by sea floor sampling and mapping in the 1950s. One of the sea's principal explorers, H. W. Menard, who worked at the Scripps Institute of Oceanography, has described in The Ocean of Truth, 1986, the kind of discoveries that were made. These were not just details. They were major features, such as the Pacific Fracture Zone. The clearly linear course of the ocean ridges emerged from semi-obscurity. The deepest parts of the ocean, the trenches, were mapped as great lineaments, too, off Southeast Asia, fringing the Philippine Sea. The spot depths already observed by Challenger were linked together as the huge Japan Bonaniro trench system. In their own way, these trenches are more dramatic than the mid-ocean ridges, somewhat like the Himalayas in reverse. The exploratory process at sea was similar to a version of the child's game of join the dots, whereby a picture emerges as more and more numbered dots are joined. You have to be certain that there is a picture to discover in the first place, and for a while, prejudice about what the finished picture might be can mislead. But eventually a likeness is the outcome, albeit a jerky and disjointed one, and the more dots you join, the better the picture. The image is still being filled in today. Modern methods of surveying, such as multi-beam sonar, simply provide a much more accurate and immediate view of the whole scene. The breakthrough in understanding can be summarized in one short phrase: sea floor spreading. The concept grew out of research by two American geologists. The expression was coined by Professor R. S. Dietz, but the pioneer publication was written by Harry H. Hess. This research paper had, like Holmes' 35 years before, a publication lag of 2 years. It had been available in unpublished manuscript in 1960, but did not appear in print until 1962. The earlier typescript is what scientists like to refer to as a pre-print, a kind of moral claim to an idea. If the idea turns out to be a seminal one, a preprint can be dangerous for the author to the extent that it tempts others to try to jump the gun. In fact, Hess' ideas spread indecently fast. The 1960s were a time of extraordinarily rapid progress in the understanding of continental mobility. Hess' paper explicitly stated why the most obvious thing about the Mid-Atlantic Ridge was indeed so. It was median because the continental areas on each side of it have moved away from it at the same rate. This is not exactly the same as continental drift. The continents do not plow through the oceanic crust propelled by unknown forces. Rather, they ride passively on mantle material as it comes to the surface at the crest of the ridge and then moves laterally away from it. Continents are part of processes that entail the oceans too. Thus, at last, the criticism of the physicist Harold Jeffreys was answered about the impossibility of the continents sailing across the basalt oceans like huge granitic barks. They didn't. They were at one with the oceans. New oceanic crust was added at the ocean ridges, where it was known that heat flow was high and that there were submarine volcanics. A moving continent and its contiguous ocean crust moved in harmony. Thus South America moved westwards with its associated slab of ocean crust extending as far as the Mid-Atlantic Ridge, while Africa moved eastwards with its slab of oceanic crust. The increasing width of the Atlantic Ocean was accommodated by new crust erupted, ultimately derived from melted mantle and inserted at the ridge, like caulk in a leaking ship. It was a wonderfully simple way of putting so many disparate observations together. Volcanic ridges, which were buoyed up by hot magma, even the rifts at their peaks, were an expression of the urge for separation of plates. Earthquakes below ridges were discovered to be only 10 To 15 kilometers deep, they become deeper outwards, up to 100 kilometers. Just as would be expected, geologists could go to Iceland and stand astride the mid-Atlantic ridge itself to see evidence of the processes on the ground. The irony was that at virtually the same time as the pro-drifters finally triumphed over the stabilists, demonstration of the mechanism of ocean widening rendered the very term drift obsolete. Continental drift had to be expunged from our vocabulary to be substituted by sea floor spreading. Knowledge and theory moved forward together in a kind of uneasy, shuffling collaboration. In an account of the kind I have given above, it is easy to forget those who were part of the process, but who lurk on the margins of history, because they do not fit into a narrative of brilliant theory anticipation. Wegener, Holmes, or experimental confirmation Bullard Hess. They get forgotten. Perhaps they had espoused an idea that never had its day. Had you been at a conference in the 1960s, though, these figures might have glittered as brightly as any of the stars that history remembers. In particular, I think of Professor S. Warren Carey of the University of Tasmania. Carey was one of those pro-drifters who kept the faith through the 1940s and 1950s, when to do so required courage and determination. His ideas were taken seriously, for example, by Arthur Holmes. Carey, though, believed in an expanding Earth. His notion was that the increase in diameter of the Earth had caused the split up of Pangaea and was the deep cause behind most of the geological phenomena with which this chapter has been concerned. Continental crust had once almost enwrapped the Earth. It was claimed, but with the Earth's expansion it split and buckled and parted company, removing the continents to where they are found today, with the ocean basins filling between. No wonder the continents fitted together, just as the pieces of a peeled orange skin fit together. The idea is not so strange. As we have seen in the 19th century and in the early part of the 20th, there had been a strong school of geologists who attributed tectonics to a shrinking Earth. After all, so they supposed, the Earth had cooled from its hot primeval condition. Thus it would shrink, and as it did so, mountain ranges would result. Seuss evidently believed in such a mechanism when he contemplated the intensely folded rocks of the Swiss Alps. He realized that the recumbent folds there indicated that the surface must have contracted or shortened. Such folds have directed attention anew to the diminution of the Earth's circumference, as he wrote. Recall, too, that early estimates of the age of the Earth were based on the idea that it was cooling progressively. Discovery of radioactive heating turned the tables. There was now a possibility that the world was actually heating up and expanding, fueled by radioactive elements in its interior. Carey later turned his attention to changes in the gravitational constant as the cause. For a while, the expanding Earth was in with a chance. Serious scientists, like the oceanographer Bruce Hezen, believed it. However, the recognition of sea floor spreading made sense of continental splitting without having to invoke Earth expansion. It seemed to be a more economical explanation. More lethal was the recognition that oceans had existed before the assembly of Pangaea. It was only a phase in the history of the planet, after all, and not necessarily its primitive state. If the Earth had been smaller still then, how could there be room for such oceans? The expanding Earth theory had some trouble accounting for those mountain ranges like the Andes that abutted oceans, though it could cope well enough with those marking where continents had collided, as in the Himalayas. Still, Carey gamely defended the theory. I went to a lecture he gave in the early 1970s, and a fine, flamboyant affair it was, a charismatic display of bravado. You could not help admiring his chutzpah, as you might that of a pianist who carries on playing while the ship is sinking. However, he had made a convert. In the Natural History Museum in London, my colleague Hugh Owen, Hugh continued to pick holes in the continental reconstructions favored by computers for the next 15 years or so, and published an alternative set of maps in which some Earth expansion was incorporated. Both Carey and Owen were absolutely convinced of their arguments, and if some twist of knowledge were to prove them right in 100 years or so, they, too, might gain iconic status. For the moment, this seems improbable. The proof of sea floor spreading was in the heating. If the theory were correct, hot magma welled up at mid-ocean ridges. When the lavas cooled, they would pass through the Curie point, and their magnetic minerals would become magnetized. If sea floor spreading theory were correct, such cooled lavas would have the same age symmetrically on either side of the mid-ocean ridge as their respective pieces of crust migrated away from the line of Genesis. So far, so logical. This is where the other property of the Earth's magnetic field comes in, its periodic propensity for reversal, for south and north poles to switch. If such a reversal occurred, its record, too, should be symmetrically disposed in the basalts to either side of the centerline of the mid-ocean ridge. You might expect a strip of oceanic crust on either flank of the ridge that gave a reverse signal, and then beyond it again, a strip with normal magnetization, and so on. Color normal white and reverse black. And the sea floor should be painted with symmetrical stripes of black and white running parallel to the ridge. The ocean crust was like a tape recorder, spooling away on either side from the mid-ocean ridges, with the narrative recorded in magnetism. A sensitive magnetometer was needed to make these measurements, and the right kind of mid-ocean ridge where a good density of samples might be obtained. Two Cambridge University geophysicists, Drummond Matthews and Fred Vine, got the evidence they needed on the Carlsberg Ridge in the northwestern Indian Ocean. The proof was published in the journal Nature in 1963. This paper is always referred to in the trade as Vine and Matthews, and is one of those rare classics that provides a benchmark in the progress of science, like the determination of the speed of light or Planck's constant. My description might give the impression that this was one of those eureka discoveries where prediction met result in a happy consummation. But that is not an accurate portrayal. Fred Vine was far more diffident than one might imagine about the likely acceptance of his paper. He had doubts. He is even recalled saying to his colleagues, if they publish that, they'll publish anything. Nor was the discovery as clear-cut as the publication date indicated. As so often in science, when the time is ripe for an idea, more than one person has it. Lawrence Morley worked as a paleomagnetist for the Canadian Geological Survey and had reached similar conclusions to Vine and Matthews, but his letter to Nature that same year was rejected. He lowered his sights a little and submitted the paper to the Journal of Geophysical Research. In a notorious riposte, it was rejected again with the judgment, this is the sort of thing you would talk about at a cocktail party. In other words, it was not to be taken seriously by serious scientists. Morley was thus to be denied the breath of popular applause. The paper was published in modified version a year later by the Royal Society of Canada, but not one in a hundred who read Nature would have seen this more obscurely published version. And a year is a long time in science when a subject is hot. Science, like life, is often unfair. Then, too, it has to be admitted that Vine and Matthews was incomplete. They had not really demonstrated the required symmetry of the stripes, and there was, as yet, a very imperfect chronology for the magnetic reversals. You need to know just how old a reversal is to approach an estimate of the rate of sea floor spreading, for you require an independent timepiece to calibrate that slow, basaltic conveyor belt. Fred Vine himself was admirably free of hubris, and remained to be convinced by better evidence from better ridges. But by now, this was big science, which meant that the well-funded oceanographic laboratories from the United States provided the next big push. These included the Lamont Geological Observatory and the U.S. Geological Survey at Menlo Park, the big boys. With big bucks ocean, coring does not come cheap. Within 3 years of those first prescient words written in Cambridge, new and more detailed descriptions had been released to the world of the patterns at other ridges that proved to have clearer signals, including the Reykjanes Ridge south of Iceland and the Juan de Fuca Ridge off Vancouver Island. When the reversal stripe pattern was proved again on the Pacific Antarctic Ridge, it would have taken a skeptic of great pusillanimity to deny that a truly global phenomenon was being recorded. By 1967, it had become material for future textbooks. The detailed study of ridges revealed one other fact that proved essential to what would soon be known as plate tectonics. As the topography of the ridges was revealed, so it became clear that they were not as straight as was originally believed. In places, the ridges were strikingly displaced, as if they had taken a hop sideways. Something else was going on here that could not be attributed to sea floor spreading. The geologist Tuzo Wilson realized that the ridges were being moved along faults, but these were faults of a special kind that did not require one or another flank to move up or down. Instead, chunks of ocean floor were slipping past one another. Put 2 planks side by side on a table and draw a line across them. Slide one of the planks, and you will get the idea as one half of the line is displaced. Tuzo Wilson called them transform faults. The dating of the magnetic reversals required experts in radiometric dating of rocks. As so often in geology, once the need was perceived, the end was achieved by a refinement of technology. The goal was accurately to date the lavas and the reverse magnetic stripes. Did the reversals in different parts of the world coincide as they should? The short answer is they did. The longer answer is that a new mass spectrometer was constructed at the University of California at Berkeley that could measure smaller amounts of radiogenic argon than previous instruments, and hence could date the rocks of a given stripe more accurately. Coupled with the new cores derived from recently explored spreading ridges, the way was open to test the question of the age of magnetic reversals. A prominent reversal interval was discovered in several of the profiles, and in 1966 was christened the Jaramillo event. It has proved to be as identifiable as a fingerprint throughout the world. The rates at which new ocean floor is grown can now be calculated. Even this longer answer is a travesty of a detailed story of discovery that has been related by W. Glenn in The Road to Jaramillo, 1982. In this fashion, knowledge begets questions, which beget new technology, which provides answers which, in turn, beget questions. This is the implacable carousel of research. Fossils also came to play a part in confirming spreading rates and dating. Ocean floor. Tiny shells of planktonic animals rain down from the surface waters of the ocean on to the deep sea floor. Among these are the delicate remains of single-celled organisms, particularly foraminiferans and radiolarians. The former are often tiny spirals or collections of chambers, looking rather like minuscule popcorn, while the latter are glassy siliconets, or spheres delicate as lace. They evolve fast, changing shape in subtle ways. Hence their various species can be used as miniature chronometers to measure the passage of geological time. Eocene foraminiferans are very different from Pliocene ones, and even within the Eocene there are many fine time divisions that can be recognized using foraminiferans. It is actually much quicker to examine a slide of fossils to get a geological age than to go through the technically complex business of extracting isotopes, so the fossils have an advantage. Logically, you would expect the very first shells to fall on newly minted ocean crust to give a good indication of its age, almost as if it had been date-stamped. By the same reasoning, you would expect the oldest ocean crust to be furthest away from the mid-ocean ridges, the newest, closest, so it proved to be. Of course, old oceanic crust was often covered by progressively younger fossil deposits. It had to await the development of coring on the deep sea floor to produce good evidence. The results were exhilaratingly consistent with sea floor spreading theory and provided concrete evidence that although the ocean floors were of many different ages, none was older than the Jurassic, since when it had spread into existence, the sea floor was far, far younger than the Earth itself. Some people feel a certain nervousness about mathematics. The world is so wondrously complex that to reduce it to a collection of formulae excites suspicion in many individuals. If the formulae are arcane and impressive, it seems to stimulate further anxiety of the kind that people feel when they are at a party where they know nobody or where everyone else is talking a foreign language. We all like to feel that we know what is going on, and few are polyglot. At the time Edouard Seuss was writing, it seemed impossible that the world might be boiled down to numbers. As he wrote, it is with extreme distrust that the geologist regards all attempts to apply the exact methods of mathematics to the subject of his studies. The implication was that the world was too messy to knuckle under the figures. But knuckle under it has. Arthur Holmes was less nervous about quantification, especially since his work on The Age of the Earth demanded the use of grindingly primitive calculators, but at heart he was still a visionary. In the story I have related, it does seem that vision has always preceded calculation, with inspiration preceding measurement. The lesson of Sir Harold Jeffreys and his unyielding, but honest, and careful, but bogus, mathematics impeding the drift hypothesis is one that every gung-ho theoretician has taken to heart. However, there has been a complete change since Seuss. Today, the way much geological science is done entails proposing a mathematical model, and then going to the field to see whether it is supported in the rocks, or perhaps conducting an experiment to suggest what we should be looking for in the rocks in the first place. This preamble is necessary to explain the final transformation in the story of moving continents, plate tectonics. Plate tectonics splice together all the different aspects of the world we have met within this book into one grand design. What went on in the oceans was linked to what went on in the mountains. The dipping and rising in the Bay of Naples was part and parcel of the fiery trail that led to Hawaii, and that, too, could not be disentangled from the heave of the alpine nappes. Even the genesis of a single crystal in a particular rock might be a response to the bidding of greater forces in the Earth's fundamental engine. It was nothing less than a unifying theory of all the world. And it was once again a visionary who fathered the new ideas. Tuzo Wilson was an unusually imaginative man. We have already met him once, and will do so again. He always seemed to leap ahead to something new, largely because, like Holmes and Seuss, he saw the world as a whole. I met him in London when he was a grand old man a few years ago at a lecture at the Royal Geographical Society. There he reviewed his intellectual progress in a matter-of-fact way. It seemed a little flat because what he said was now part of the way we all thought. I was reminded of a time when the secret of a magic trick was explained to me, to recapture the sense of wonder you have, to stuff the rabbit back into the hat and forget all you know. Tuzo Wilson had invented the trick. He had minted the idea of plates in a paper published in Nature in 1965. Within a few years, plates were everywhere. But first I must add ocean trenches to the plot of the story. As previously noted, these had been recognized since the days of the Challenger from spot depths, but their profile had only become known in detail following the surveys of the sea floor undertaken after the Second World War. The trenches were great gouges in the sea floor, but not holes, rather arc-shaped cuts. The greatest series looped off Japan and the Philippines. It is as well to get their profile correct, as trenches are usually portrayed with a greatly exaggerated vertical scale on classroom maps. This may add to their drama, but it detracts from the truth. But why were they there at all? The explanation proved to be linked to a series of observations made on earthquakes that happen on the landward side of the trenches. Any seismic map of the world shows that a concentration of earthquakes lies along the length of Japan and southwards to the islands of Southeast Asia. This part of the world has the serious shakes. From seismometer readings, it is a comparatively simple matter to calculate the epicenter and the depth of origin of any quake, and in Japan there is no shortage of data. What was revealed got into the guts of the earth. There was very little activity in the trench and seawards of it, but towards the islands the quakes increased. As more data was gathered, it was clear that there was a pattern to the distribution of the quakes. Close to the trench they were shallow, while they increased in depth towards the island. In detail, they lay along an almost straight line, which dipped at an angle away from the ocean and underneath the Japan Sea towards the land. This must surely be a major dislocation in the crust of the earth, a line of failure. Here lay the answer to the obvious question. If new crust was being added at the mid-ocean ridges, or was it being destroyed? The downward dipping earthquake zones were the burial traces of plunging ocean crust. The trenches were dragged downwards, warped tracks of the ocean floor where the crust dived towards a mantle from which it had once emerged. The scrape of the moving crust against the adjacent buttressed margin engendered earthquakes. Crust was born at ridges and died in deep graves at the edges of continents. Where it plunged downwards, it would tend to melt, admixing with partly melted rocks of continental type, perhaps to feed subterranean chambers of liquid rock. Magma would find its way to the surface in explosive volcanoes. Hence the ring of fire that marks the Asiatic margin of the Pacific Ocean. Some of the greatest eruptions of recent years have occurred there. Mount Pinatubo in the Philippines awoke in 1991 after sleeping for 400 years, sending eruption plumes 25 kilometers into the atmosphere. So the edge of the Asian continent coincided with the line where the rim of the adjacent oceanic plate plunged downwards. The ocean crust is said to be subducted, literally led under to oblivion. Even before the topography of the ocean floor was fully known, Edouard Suisse had realized that a crucial boundary lay in the deep seas off Japan. Once more, he regarded subsidence as the key to understanding. He remarked that all marine abysses which sink below a depth of 7,000 meters are four deeps in a tectonic sense and indicate the subsidence of the foreland beneath the folded mountains, and also that they mark the eastern boundary of the Asiatic system. He was, as so often, half right. Where Suisse saw a deep subsidence of continents, a modern observer sees the plunge of basaltic plates. What we see is partly a function of what we believe we see. Our truth is constrained by the times in which we live. The mathematical description of plates required these few assumptions: creation of crusted ridges, its subduction at destructive margins, and transform zones where plates could slip past one another. All were recognizable in the real world. And because that world is not expanding, the overall creation of new crust should be balanced by its destruction elsewhere. It is a matter of reconciling the equation. As we have seen, all the ocean floor today has been manufactured since the Mesozoic began. Subduction has removed all that was older. Hence, it became possible to describe the world in terms of a few rigid plates that moved relative to one another over the surface of a sphere. The The mathematics involved is a spherical geometry based on Euler's theorem. Leonhard Euler was a brilliant 18th century Swiss mathematician who became professor in St. Petersburg at the time of the Empress Catherine. His ideas came into their own nearly 200 years after his death. Imagine to describe the geometry and structure of the world by the movement of a dozen or so plates. Sue's ineluctable complexity reduced to motion, direction, and spreading rate. How to picture it? I like to think of the different plates as distinctly colored swathes dividing the Earth's surface, growing apart at ocean ridges. Imagine that the oceanic parts of the plates are darker, the continental parts paler. You can visualize the plates jostling one another like crowded ice flows. In places, two differently colored flows slide past one another with minimal interaction, but where spreading oceanic crust meets the rim of a stable continent at the edge of an adjacent plate, a subduction zone appears along the join. The darker colored oceanic crust will then disappear into the zone of destruction, plunging down to obscurity. Volcanic islands, a Hawaiian chain perhaps may be plastered onto the neighboring continent, drawn in willy-nilly by the subduction process. Inexorably, the two continents themselves will begin to approach one another as the oceanic part of the moving plate vanishes into the depths. Thick continents cannot dive under one another. Instead, they collide, and where this happens, the Earth suffers, buckles, thickens. A mountain belt arises over millions of years, a Himalayan or an alpine system. The ocean that once ran before the Indian subcontinent has vanished beneath the Himalayas. Now it is the turn of the continents to meet face to face. The mountain belt grows on a line that marks the demise of the ocean that preceded it. Its linear shape betrays its origin. Forced together, the two continents mark their conjunction by squeezing lathes of land in mutual accommodation. Great slabs of crust are folded and ejected, turned over, sliding, slithering, twisting. The light continental crust thickens on collision, then bounces back to rise rapidly. Snows and ice fields gather on the jagged peaks. Rivers gouge downwards to reduce the impertinence of altitude. Deep beneath the mountains, the isobars, depressed by the squeeze pile, return to heat the roots of the ranges. Rocks melt but selectively. There are granites. There are gneisses. Deep in the earth, there is a cooking extravaganza. 100 rock types born of collision, minerals and metals, are squeezed into the interstices of modified country. Rocks. This marriage of two continents is also a refinement, a distillation of rare elements into ichor that can be infused into secret places. The modern mineralogist sniffs out these places with his instruments. He now knows the knitted continents for what they are. They are the true repositories of the Earth's alchemy. In the original formulation of the theory, a handful of plates encapsulated the rocks of the world, permitting enough permutations to accommodate our apparently inexhaustibly varied planet. This may seem almost an impertinence in view of Seuss' caveat about numbering the world, but this is how the plate tectonic revolution wrought a transformation. At the present time, there are many more plates recognized, but the principles remain valid. We shall all be changed in the twinkling of an eye, and so we were at least relative to the 50 years it had taken for the idea of mobile continents to become respectable. I had the curious privilege of being a bystander during the period when formal plate tectonic models were being developed in Cambridge in the late 1960s. There were two inspired scientists who worked on the mathematical treatment of plates at more or less the same time, but on opposite sides of the Atlantic Ocean. Jason Morgan at Princeton and Dan Mackenzie at Cambridge. Cambridge University is organized into colleges, and I belong to King's College, named after its founder, the devout King Henry VI. King's is famous for its choir and its chapel. The chapel lies on one flank of a quad, and two of the other three sides are walled in by academic buildings. The visitor will notice little stairwells, like secret tunnels. Some of them lead to comfortable and cluttered rooms occupied by famous academics and writers. I met E.M. Forster for tea in one such room. He was very old and very polite, and did not say anything memorable, but I was awestruck nonetheless. Mr. E.M. Forster, a painted label said at the base of the staircase, as if he might have been in charge of the plumbing. There were fellows of the college, located in other rooms, who were solving the problems of the global economy, or the fundamentals of matter, or how to understand the difference between ego and I, or things even more important. I was preceded in my college life by Dan Mackenzie while he was solving the problems of the construction of the world. He was a year or two ahead of me, and I was always invisible in the glare generated by his brilliance. After the first degree came the PhD thesis. Dan Mackenzie's on applying Euler to plate motions was instantly famous. At a college function, he explained that he had printed extra copies to sell to the leading laboratories in the United States. The usual form in those days was for the student to take a bank loan to pay for the typing of the great work, which would then sit magnificent but untouched on a shelf in the university library. The notion of people queuing up to read your thesis was bizarre. Within a year or two, Dan was leading a double life, being flown out to California from Cambridge on a regular basis, like a film star, to the rank and file. All this was impossibly glamorous, but it was all deserved. There are those who believe that theories have their time, that they arise with a kind of inevitability because of what has gone before, and as a result of new facts added to the store of knowledge. Notwithstanding, it remains true that there are few people who can grasp the historic moment. It always requires boldness, sometimes a certain unscrupulousness, and it is risky. Everything could be wrong, or half right in the manner of Warren Carey. So credit justly belongs to those who take the first bold leaps. That said, there are usually a few intellectual sprinters who take to the field at the same time, like Morgan and Mackenzie. Ideas lie half concealed, awaiting their historic moment for discovery, at which point there could be several gifted people who independently realize what, in retrospect, seems inevitable. By 1970, plate tectonics was not yet a theory of everything, but there was scarcely any aspect of Earth history that plate theory would leave untouched. Plates provided a new way of looking at the world. Most immediately, there was a great boost for the Lyellian method. Geologists could go now into the field and look for analogies with the present-day world and ancient rocks. Their search focused through the understanding that plate tectonics brought. In the Himalayas, could this, perhaps, be the remains of an island arc like Japan enmeshed in the mountain building as two continents collided? In the Alps, might these be the deposits laid down in deep water on a sea mount? Can we find fossil equivalents of the down-warping crust in front of the Himalayas? Can this particular mineral only grow where the conditions were exactly right during the closure of an ocean? The questions were endless, and answers were often forthcoming. Take ophiolites first. Edouard Suisse had known that there was a characteristic association of rocks that could be found in many mountain belts. These rocks had been studied by an alpine geologist, Jeep Steinman, in the early years of the 20th century. He had noticed a consistent association of dark, basaltic volcanic rocks, often forming pillows, as around Hawaii, with richly green and speckled serpentinite, topped by beds of the dark, fine, grained silicious sedimentary rock known as chert. Sometimes the latter included fossil remains of tiny radiolarians, those single-celled oceanic plankton mentioned previously. So common was the association that it came to be known as Steinman's Trinity. For instance, in the eastern Alps, Suisse recorded that the green rocks gabbro, serpentine diabase, are frequently associated with deep-sea radiolarian of Middle to Upper Jurassic Age. They were called ophiolites from ophis, the Greek for serpent, because of their serpentinite component. 50 years later, Arthur Holmes was to note that ophiolites indicated eruption in deep water in geosynclines. Plate tectonics would show that they were much more significant. In 1994, I visited the Sultanate of Oman in search of trilobites. To reach my destination in the southerly desert, I was obliged to cross the Oman Mountains. From Muscat, the capital city, like many countries in the Middle East, Oman has adopted Western styles but has attempted to make them compatible with the region's cultural traditions. This has resulted in some curiosities. The new outskirts of Muscat are cheerily like Western suburbs, although the white, walled villas are tiled for coolness rather than lined for warmth. But in the middle of roundabouts or in public spaces, there are new monuments. I particularly liked an enormous painted coffee pot, complete with matching cups. In another site, a vast dagger in its ornate sheath commanded attention. My assumption was that these were precious items in the tents and caravans that were formerly the common habitat. You are out of New Muscat soon enough and pass into the foothills of the mountains. There are steep-sided valleys, wadis, with fig trees and almonds in irregular groves wherever there is a little silt on which they can grow. Little brown goats fastidiously pick at spiky bushes. The wadis are dry now, but the large cobbles lying on the dry stream floor tell you that they must be able to turn into torrents when the rains come. How else could such boulders be transported there? Soon, you pass higher into the mountains. The few villages have all grown up around springs and seem to be ancient, uniformly buff or pallid brown, each with a fortress that is all steep walls, punctured with tiny square windows and ranks. There are groves of date palms, making rows of neat canopies. Near the water source are irrigated squares of vegetables looking improbably green against the overwhelming brown. Higher still, and you suddenly pass onto the moon, or so it seems. Here there is nothing and nobody. Even the scrawny acacia bushes seem to have given up the struggle for life. The hillsides, completely barren, are composed of beds of rock and have an extraordinary heaviness about them, an oppressive blackness crusted with umber brown. It is not just that the rocks are dark. They seem to suck out the very energy from the sunlight, which is brilliant at this height. They absorb everything and give nothing back. They might indeed be from another world. Then you notice that some of the rocks show pillow structures, as if some underworld giant had laid out a whole field of cushions for a hellish party. They are identical to lavas erupted on the ocean floor. Perhaps you might see a few patches of chert lying in the joints on top of the pillows. Elsewhere, there are black dikes running like ribs over the hills. A coarser crystalline rock glints darkly in the sunshine and proves to be almost entirely composed of dark green olivine, reminiscent of the green sand beach in Hawaii. This rock is called dunite. Nearby, there are lumps of dark green and reddish mottled serpentinite scattered about on the ground. No doubt about it. Her Dr. Steinman would have recognized this part of Oman as an enormous ophiolite complex. In a sense, it is quite appropriate to think of these mountains as being derived from another world. It is the world of the deep sea. As more was learned about the structure of the oceanic crust, it became clear that ophiolites actually were slices of the deep sea floor wrested from the abyss. In the eastern Mediterranean, the island of Cyprus is centered on the Troodos Mountains. The Troodos are another slab of ocean crust that has moved into the sunlight, and the area has become the classic of its kind. Professor Ian Gass and his colleagues showed that rocks recording the whole profile of the ocean crust are preserved in these mountains. Careful mapping revealed a fossilized anatomy of the lithosphere of the seafloor, pillow lavas that had been erupted under the ocean depths from liquid magma were merely the top of the pile. Beneath the pillows there was a layer of dikes arranged in steep sheets. These were the feeders that supplied magma to the ocean ridge, where sea floor spreading occurred. These dikes were the very struts of creation. Beneath this layer again there was dark, crystalline, igneous rock, gabbro, which underlies the whole of the ocean. In places, there were black seams of the mineral chromite, source of the element chromium, looking like tarry stripes. No wonder plants eschewed these places, for chromium is poisonous to many of them. Crystals of this heavy mineral must have settled out in the magma chamber, like beans fall into the bottom of a soup tureen. And in places beneath the gabbro, there were patches of the rocks that lay at the base of the lithosphere, like dunite and herzolite. We met pebbles of these rocks as messengers from the deeps, where they had been brought to the surface in some of the lava flows on Hawaii, dragged up from their natural home at the margin of the mantle. In these ophiolites the same rocks were hijacked wholesale from the depths of Neptune's, or should it be Pluto's, domain. The whole profile could be more than 10 kilometers thick. So this huge pile was out of place, lifted bodily from the ocean to form the backdrop to the traditional home of Aphrodite, goddess of love, whose temples are so numerous in Cyprus. Coins from Paphos show Aphrodite's emblem, a sort of cone, though it would be fanciful to imagine it represented any kind of volcano. But it is not fancy to suppose that Pluto's kingdom had somehow been levitated to the realm of love and sunshine. No wonder those similar mountains in Oman look so unearthly, darkly glinting in the brilliant light. Surely, though this should not be, ocean crust is destined to be consumed at subduction zones, not displayed layer by layer as in Oman and Cyprus. There was only one possible explanation. In places, slivers of oceanic crust were pushed upwards rather than downwards. They were squeezed out from the tectonic vise like pips from a crushed orange. In some places, a piece of ocean evidently came to rest on continental crust as a displaced chunk, a tectonic refugee. This process is called abduction, a kind of anti-subduction. Plate tectonics completely altered the perception of these puzzling morsels of the earth, and Holmes' observations of their deep-sea origin were explicable in a different way. Even the little radiolarians made sense, because such plankton drifted on the surface of the seas overlying the depths and were preserved upon their death in the sediments above the pillow lavas. Later, these little fossils became invaluable in dating the ages of ophiolites and cherts because they change with the passage of geological time, a fossil chronometer. In a nutshell, ophiolites were the pieces of oceanic crust that got away. Steinman's Old Trinity proved to be 3 times as interesting. Within the Alps, too, there must have been other pips squeezed out as ancient oceans closed when Africa and Europe met. The modern view is that ophiolites are commonly associated with the closure of smaller ocean basins between an island arc and an adjacent continent, for example. It has become clear that subduction is not entirely destructive. Wedges of sediments may become plastered onto the edge of the continent as subduction proceeds. These form prisms of sedimentary rocks, gummed on, or as we should say, accreted to the continental margin. Once more geologists went into the field to decipher plates in action and found evidence of this process on the ground in the Makran Desert of Pakistan. But nobody would have heard the message of these rocks without the plate tectonic stimulus. It could be said that entire cultures are under the influence of the geological underlay. As in Jung's original concept of the collective unconscious, we, the surface dwellers, are moved and bound by deeper things. Japan has now at least superficially, adopted the Western capitalist mode. Earthquake-proof. Technology has allowed for the construction of buildings in Tokyo that are as routinely modern as those in other capitals around the world. However, the classical era of paper and wood constructions was entirely appropriate to living on the quaking edge of a great subducting region. Maybe the Shinto religion with its welter of gods provided a way of propitiating the uncertain. Earth. Iwo Jima is a small volcanic island 1,150 kilometers, 715 miles south of Tokyo, the shore that gave brief haven to the survivors of Captain Cook's fatal voyage of 1779 is now 40 meters above sea level, the height of a church steeple. The island lies in the midst of a caldera hidden beneath the sea that is 10 kilometers across, and that was formed explosively some 2,600 years ago. Magma is evidently rising again and being injected into the crust. There may yet be another cataclysm. Mount Fuji has been stable for hundreds of years, but it is only sleeping. The wonderfully symmetrical cone is a typical stratified volcano built from successions of pyroclastic flows that would have destroyed everything in their path. The explosive lava type is a particular product of its position where plates meet, so the symbol of everything Japanese is in fact a product of the underworld. Even in these secular times, the mountain is dotted with shrines, some of them dedicated to Sengen-sama, goddess of the mountain. There is no question that its presence in Hokusai's inexhaustibly inventive set of portrayals, 36 views of Mount Fuji, is more than merely decorative. The mountain centers the world of his art. In Shinto days, everybody made a pilgrimage to the top of the mountain, which at 3,776 meters, 12,388 feet, is the highest in Japan. The sun goddess, Amaterasu, required it. Today, people still feel drawn to watch the sun rise, looking towards Tokyo 100 kilometers away, or perhaps towards the Pacific Ocean where the unseen plates move. The American journalist and author, Lafcadio Hearn, who married a Japanese woman and took her nationality, was one of the first Westerners to try to explain the virtues of Japanese culture. 100 years ago, he described his emotions on seeing the sun rise from the summit of Fuji in these terms. But the view for 100 leagues in the light of the far faint dreamy world and the fairy vapors of morning and the marvelous wreathings of cloud, all this and only this consoles me for the labor and the pain. Other pilgrims, earlier climbers poised upon the highest crag with faces turned to the tremendous east, are clapping their hands in Shinto prayer saluting the mighty day. I knew that the colossal vision before me has already become a memory ineffaceable, a memory of which no luminous detail can fade till the hour when thought itself must fade. Lush prose, perhaps, but you are left in no doubt as to the importance of the occasion and the importance of Fuji in Shinto cosmology. The Shinto religion may not have the grip it once had, but there are still shy little offerings placed in wayside shrines on the way to the summit, just in case. Geology dictates the lie of the land, and climate controls how the design of the world accommodates to life. But climate itself is enthralled to geology. A landmass over the poles permits ice sheets to grow, and this mediates the sea levels of the world. There have been warm times when much of the land surface has drowned, and such times will come again. Mountain ranges modify weather systems, specify where there shall be deserts and steel rain. Then, too, oceans are great climatic modifiers. Think how the coast of Europe is so ice-free while the icebergs drift off frozen Labrador at the same latitude. The North Atlantic Drift Gulf Stream moves warmth northwards, but only for some. There are climatologists who believe that the warm pump might be turned off in the twinkling of an eye, geologically speaking. Then long Frozen days might turn England's hedge-fringed green fields into birch and conifer scrub. The shape of the ocean basins is the stuff of climate. Deep gyres transfer cool water and nutrients about the world. Yet ocean and mountain are no more than a consequence of the geological foundation, the arrangement of plates in this mosaic of our earth. Change the plates and you will rearrange everything else. Mankind is no more than a parasitic tick, gorging himself on temporary plenty, while the seas are low and the climate comparatively clement. But the present arrangement of land and sea will change, and with it our brief supremacy. Part 6. Ancient Ranges. Newfoundland is a curious island. It hangs off the eastern coast of the North American continent as if it doesn't really belong there. The natives call it the Rock, and it is an apt name. There is certainly no shortage of geological exposure on the island, although most of it crops out along its rugged and indented shores. The coastline is 10,000 kilometers long if you add in all the numberless bays where fishermen have established their outports. Inland, Newfoundland is a mass of rambling rivers and small lakes called ponds. The cover is a scrubby forest, mostly undersized conifers, but relieved by shaking aspens, small alders, and birch trees. Many of the conifers have a sickly look and are crowded together, a working example of the struggle for existence. It is an endless kind of landscape, mile after mile of the same, for hundreds of miles. There are few roads away from St. John's, and if you are foolish enough to leave the beaten track and wander into the bush, you can become disorientated within seconds. In spite of the uncompromising terrain, from an early period the island was colonized by Europeans who displaced the native Micmac Indians. Even the Vikings found their way to Lancer Meadows in the northern peninsula at a time when the climate was more equable than it is now. Hundreds of years later, fishermen from the English West Country and from Ireland followed the first wave of immigration into North America. The coastal villages they settled were isolated from the world and from each other. Some of the place names Trepassey, Torres Cove would not be out of place in Cornwall. Others, Blow Me Down Brook, Fogo, Goose Tickle, Hearts, Desire have a unique charm all their own. The extraordinary Newfoundland accent may have preserved something of its original Tudor twang. Certainly, it is most unlike that of the island's Canadian neighbors. To the incomer it sounds Irish at first, but then other harmonics emerge, a hint of Cornish. Perhaps H's are dropped and added, and words that are obsolete elsewhere are preserved here in common usage. The island only formally joined Canada in 1949. Before that, it was the oldest British colony, founded in 1583. It remains fiercely proud of its own identity. The once thriving cod industry has collapsed, ruined by non-indigenous factory ships overfishing the Grand Banks. Nowadays, the distinctive two-story wooden houses that line the outports are painted brighter than they have ever been. There is little for a beach fisherman to do other than redecorate the house. The cod flakes along the shoreline on which the fish were once split and dried have all but disappeared. There are still lobsters to be had and squid some years, but the great days are over. Newfoundlanders annually receive the vilification of animal rights activists because of their participation in seal culling. But to these men it is a tradition, and clubbing is the most humane way of dispatching a proportion of baby harp seals for their skins. The year I was living there, I saw the Bishop of St. John's bless the fleet before it sailed. This was my first lesson in moral relativism. Newfoundland is a geological textbook laid open to the skies. The traverse, east to west across the island, is a pilgrimage that many famous geologists have made. There is something there for everyone, for the paleontologist, for the tectonician, for the just plain curious. The rocks embrace an appreciable chunk of geological time, several 100 million years, especially spanning the later Precambrian, Cambrian, Ordovician, and Silurian periods, 900 to 419 million years ago. It is a big slice of Earth history, spread across a big stretch of land, making it difficult to select just a few places that reveal the secrets of the rock. Many students have spent their whole lives untangling the complex geology of small parts of the island. It becomes necessary, perhaps, to imitate one of the huge seagulls that haunt the Newfoundland shore, alighting briefly on one rocky outcrop before flapping off to another distant cliff. St. John's lies on the eastern edge of the island. It is built on folded, resistant, Precambrian sedimentary and volcanic rocks that form spectacular, sheer cliffs ribbed and pleated, from the top of which you can watch pilot whales sporting offshore. The old town around the splendid natural harbor is picturesque enough in a scruffy way. Steep terraces of painted wooden houses run down to Water Street, which was once a bustling center for shopping and shipping before the edge-of-town malls and supertankers took their toll. Grand Victorian houses in their own grounds that belonged to the merchants lie uphill. Those whom Newfoundlanders still call marchants were the beneficiaries of the fishing wealth of the island. It is said that there were more millionaires a century ago in St. John's than anywhere else in North America. They kept the fishermen in a state of perpetual debt by an iniquitous system of loans advanced on a year's catch. Older inhabitants still remember running around barefoot through the snow. This is a tribute to their sheer toughness. Because the Gulf Stream passes Newfoundland by, the climate is, to be tactful, frequently inclement. You would never guess it was on the same latitude as Paris. Spring seems to be delayed forever, and a dump of slushy snow down from the north is not unknown even in June. Fog obscures the delightful sea views for what seems half the year, and the mournful lowing of foghorns through the Narrows provides an eerie accompaniment to winter walks. Ice floes brought down on the Labrador Current accompany the brief early days of summer. For geologists, it means that the field season is decidedly limited, and waterproofs are indispensable at all times. When the sun comes out, it is totally delightful, except for the mosquitoes and the black flies and the deer flies. Belle Island is a small island in Conception Bay, a few miles west of St. John's. It is more or less encircled by cliffs comprising dull yellow or brownish sandstones, much less folded than the rocks around St. John's. The cliffs are quite accessible in a number of places, and a brisk breeze usually keeps the biting and blood-sucking flies at bay. These sandstones are the kind of rocks that were originally laid down as sediments in quite shallow seas. A very lucky hammer blow might reveal fossils that look like small black hacksaw blades laid out on leaves of intercalated shale. These are the remains of extinct colonial planktonic animals called graptolites. Every geologist likes to find graptolites because they can be used to date rocks quite precisely. They evolved fast and spread widely around the ancient oceans in which they floated, making them ideal biological chronometers. The ones on Belle Island are no exception. The local expert Henry Williams identified them precisely. They indicated an Ordovician age, more exactly, a part of the early Ordovician called the Arenigian. There were other fossils there as well, including some of my own favorite animals, trilobites. Superficially more complex than the graptolites, trilobites were bugs with jointed legs, arthropods that swarmed in the seas of the Paleozoic era. Sadly for all biologists, they are now extinct, but there were once thousands of kinds of trilobites, individual species of which were confined to the seas surrounding different continents of the ancient world. These ones on Belle Island were old friends. I knew their names as well as I know my children's birthdays. Nezeridus and Ogygenus. Both of them had been yielded up to my questing. Hammer and strata cropping out along streams and roadsides in Wales. I knew them also from France and Spain. I had even been sent a sample of one of these beasts from the remote deserts of Saudi Arabia. Much more common on Bell Island were scratches and burrows left in the sandy sediments by animals on the Ordovician sea floor. Some, called Cruziana, were probably made by the same trilobites that you could hold in your hand. They look like braided plates laid on the rocky slab, as distinctive in their way as many more. Substantial fossils. Exactly the same kinds of Cruziana could also be found in France and Spain and North Africa. It is beginning to look as if the sandstones on Bell Island are trying to tell us something. Move further westwards to Random Island, and it is a similar story. More fossils, a little older, just like those from Europe. On the way you pass over a cheerless, bleak, and empty region where even the hardy conifers have given up trying to take root. These are the barrens. The underlying rock is unforgiving granite, and the soil above it is so poor that little seems to flourish. Little, that is, except a fruit called the partridge berry that clambers over the ground on inconspicuous vines. It is said to be a good source of vitamin C and is resistant to frost. Newfoundland families used to keep a stash of these purple-red berries the size of rabbit droppings under water in a jar by the door, and a few would be taken every day over the interminable winter to keep scurvy at bay. In tough places, everything seems to have a use. The eastern part of the rock comprises two broad lobes of land trending northeast-southwest, connected to the rest of the island by a narrow link of land that is almost an isthmus. This eastern part of the island is known as Avalon. As so often in geology, understanding of the area was dependent on making maps of the rocks, and the unscrambling of Newfoundland began in Avalon with the pioneering geologist Alexander Murray and James Howley publishing the first map of the Avalon Peninsula in 1881. The accounts for 1871 fieldwork submitted to the Geological Survey Office note that 100 pounds of bacon cost 5 pounds, as did a new tent. Murray was able to hire 4 men for 4 months for 120 pounds, but his own salary was 490 pounds. Those geological maps have been under a continuous process of refinement ever since. No map is ever truly finished, simply because you cannot write down all the truth of the world on a sheet of paper. Move westwards again. You will find yourself driving along the Trans-Canada Highway. There is no other way to go. Several hours pass before you. Get to Gander, a remote settlement with nothing to it except a hotel and an airport. Then, when you reach Gambo and look at the rocks cropping out in cuts along the roadside near the village, you notice that something seems to have changed. Gone are the simple sedimentary and volcanic rocks that we saw around St. John's and on Bell Island, which there are laid out in clear layers, even though those layers might have been elevated to the vertical. Instead, the rocks at Gambo present a bewilderingly various appearance, striped and twisted. In places they show a crude layering, though it seems to wander hither and yon. Pinkish layers a foot or so thick can twist and pinch out on a rock face a dozen meters in length. Quite often you see smaller pale veins that seem to be scribbled onto the rock face like graffiti. If the sun is shining, you might notice that many of the rocks glisten and flash briefly as you drive past. If you manage to find a place to get off the road to examine the rocks, you will see that the pink ones are mostly composed of creamy-looking feldspar crystals, which impart the dominant color. Then there are veins of quartz, which sometimes wriggle through the rock like creamy worms, or cut across its grain like petrified flashes of forked lightning. The shine in the sunlight is induced by little crystals of mica with perfectly flat faces that respond like diminutive mirrors to incident light. coarse and irregular layering is often picked out by drifts of dark mica crystals. In places, the rocks look as if they have been stirred by a gigantic spoon. They are gneisses. Such rocks have been changed by baking in a terrestrial pressure cooker, then they have been disinterred. Kilometers of overburden must have been removed. This part of the country is comparable with the Pass of San Bernardino in Switzerland, despite its different geological age. Nowhere near Gander are there marbles, such as those that enclosed S. Gennaro's relics in Naples in such splendor. This is nice country, boggy and impenetrable. Just as marble started life as limestones, many gneisses started out as shales before they were cooked. More specifically, many of these rocks are described as migmatites, in which the pink veins seem to blend insensibly into a kind of swirling granite. Sometimes it is difficult to be quite sure whether you are looking at gneiss or a banded granite. If you take a diversion off the Trans-Canada Highway along Bonavista Bay as far north as Dead Man's Bay, there are huge masses of wholly unambiguous pinkish granite plunging direct to the sea. Some of the coarse gneisses contain garnets. Jewel-quality garnets are pretty, plum-colored stones much beloved by the Victorians for silver settings. Most of the ones you find in metamorphic rocks are a disappointment. The best you can hope for is to find one about the color, size, and shape of a partridge berry. They are interesting to find, though, because they only form under particular temperatures and pressures. Almandine, the variety found here, is stable at temperatures of 540 degrees to 900 degrees Celsius at a pressure of 200 GPa. This has been proved by experiment under controlled conditions in the laboratory, so it is possible both to visualize and quantify something of the suffering the rocks in this area endured in the great vice of the earth. No fossils could be expected to survive such treatment. Between Avalon and Gander, therefore, it is evident that a major geological threshold must have been crossed. The threshold is marked by a great fault cutting through the geology, the Dover Fault, which runs northeast-south, west near the eastern side of Bonavista Bay. The Avalon platform lies to the east, back to Bell Island and St. John's, while to the west lies the Mobile Belt, forming the central part of Newfoundland, a land of complexity and problems. This is where the striped and redoubled gneisses and many other rocks besides all run together and are twisted and faulted up. It is mobile not just in the sense that there must have been movements of strata, faulting, and geological mayhem, but also that whole chunks of the world may have reached where they now lie from some other place. Past the village of Gambo, the road runs along a pond that is big enough to be called a Lake Gander Lake, where there are folded, metamorphosed sandstones, quartzites. The rocks of the apparently impenetrable area north of the lake were mapped in the 1960s by a celebrated Newfoundland geologist, Harold Williams, universally known as Hank, a native of the rock and wise in its ways, with an accent that puzzles those not used to its idiosyncratic inflections. Hank Williams worked out much of the geology of the Mobile Belt the hard way, by foot and Indian canoe, latterly helicopters, made life easier, if more dangerous. Like Murray and Howley before him, he produced geological maps. But what maps? Unscrambling the Mobile Belt was like solving a cryptic crossword, one in which even the clues were anagrams. The resulting maps are speckled and daubed like a painting by an abstract expressionist, but even through the extravagance of colors you can clearly see how many features have a northwest-southeast trend governing the shape of the bays and headlands. The design of the country is clearly written in the geology. Hank employed many students too, and one of his criteria for their selection was the ability to play a musical instrument. There was always a band in the geology department at Memorial University in St. John's, with Hank on banjo or fiddle, and with assorted basses and dulcimer players, all making a fine racket with their jigs and reels, of which there seemed to be an endless selection. When the fog was thick on the North Shore, I am told that Hank used to sit in the bow of the leading canoe furiously, strumming the banjo, to guide the party onwards to the next offshore island. He thought nothing of dumping a student in some remote area until the field season was over, with only a violin and a field assistant for company. But Hank was much more than a decoder of complex geology. He built up a picture of the whole of the Newfoundland Central Fold Belt and extended it far, far beyond the wild shores of the island. Finally, it provided an interpretation of the whole eastern side of North America, from the Adirondack Mountains to the Appalachians. But here I am getting ahead of my story. It is clear that there are fossil volcanic islands within the Mobile Belt, around Notre Dame Bay. On the northern coast, for example, volcanic rocks are easy enough to recognize, even when they have been baked or folded. A number are like those I've already mentioned from Hawaii, including pillow lavas. A few ancient islands still stick up out of the sea as rock islets. Today disinterred, they reproduce their anatomy of 460 million years ago. The detailed chemistry of the lavas can be studied in modern laboratories, and some show the kind of trace elements that are characteristic of oceanic islands at the present day. Others are like those from island arcs close to subduction zones. These elemental ratios are like fingerprints that identify the magma source of the ancient lavas. This geochemistry is a wonderful application of Lyellian principles and a boon to the geological interpretation. Not all the rocks have been as heavily metamorphosed as those near Gander. In places there are beds of rock composed of cobbles, conglomerates, that you can just imagine tumbling off the side of the unstable volcano. Some of the islands had shallow seas around them, and just once in a while, fossils of some of the shelly animals that lived in those waters have survived all the vicissitudes that nature has thrown at them. These speak of Ordovician dates. It is curious to think of seals now basking where trilobites once crawled. Discovering these critical creatures in these volcanic-derived rocks was an heroic accomplishment. For once the needle and haystack analogy can be used without blushing. So this part of the Mobile Belt is a place where all the branches of geological science meet and converse. There are ores and minerals in the Mobile Belt, too, and many of them are associated with the volcanic rocks. Every few years there are rumors of gold finds, and indeed in a few localities there are significant amounts of the precious metal and rather more silver. Sulfate ores have been important, enough to give rise to working mines for copper, manganese, and lead zinc in other parts of the island. For wherever the earth moves, metals are concentrated. A friend, John Bursnall, was assigned an area around Notre Dame Bay as the ground on which to work up his doctoral thesis. He returned from field work each year with his brow progressively creased and with thick notebooks full of sketches. The geology was, he remarked from time to time, a real mess. Everything on the ground seemed to be in a state of flux. The rocks he had been assigned are known as the dunnage melons. Poor John was obliged to share an office with me, where I noisily dug out trilobites from their limestone matrix whilst he attempted to put some shape into a hideously complicated piece of Newfoundland. He sometimes had to retire with a headache. A melange is, I suppose, a polite word for a mixed-up mess. The principal feature of the dunnage melons consists of huge blocks of rock. These now form islands and shoals in the grandly named Bay of Exploits. If you are accustomed to think of rock successions as deposited in a logical order, oldest first, then progressively younger, it is not too difficult to envisage how such successions can get folded, or even, as in the Alps, turned completely upside down. It is not so impossibly hard to conceive of these rocks subsequently becoming metamorphosed by heat and by pressure and changing their character accordingly in the grip of the Earth's inexorable movements. But in the dunnage, there are places where it is almost impossible to make sense of the relationships between rock units in the field. These enormous BLOCKSSOM, more than a kilometer in DIAM, ETER, oceanic-style volcanic rocks rest on a kind of ground sheet of shales which must have originally accumulated in the deep sea. Some of the blocks have evidently tumbled or slid downslope until they came to rest in a confusing array. Fortunately, those useful fossils, graptolites, have been found in the shales to tell us that these events happened in the Ordovician. But then the confused mass is itself folded, even overturned, thus superimposing complexity on perplexity. To make matters worse, there are places where igneous rocks, cooled from magma, have been injected into the shales while they were still soft muds. So there are other kinds of rocks swirling around in the mixture, and then the whole area has been cut with steep faults and pushed bodily northwestwards along thrusts. Hank Williams and his associates divided Newfoundland into a number of zones, each one with a distinctive geological signature. By now we have moved progressively westwards from the Avalon Zone, through the Gander Zone into the Dunnage Zone. As geology always turns out to be more complicated than was thought at first, the dunnage is now subdivided in various ways, the details of which would further tax the imagination. Each of the major zones is separated from its neighbor by a major structural line, often a series of faults that cut deep into the crust. The Grub line separates the Gander Zone from the dunnage, while the Bay Vert line separates the dunnage complexity from what happens further west. Although they wander somewhat, each major fault follows the grain of the land from northeast to southwest. Everything on the surface is enthralled to the deeper order. It is almost a relief that by the time we arrive at the west coast, some of that bewildering complexity is lost. One important road crosses the Trans-Canada Highway in the west. It runs northwards up the Great Northern Peninsula, a great protuberance that sticks up on the west side of the island like an optimistic thumb. This highway runs to the sea at the Gros-Morne National Park. The western part of the rock retains vestiges of French influence in place names like Porto, Port, and Port. AUX Boss, after all, it does face Quebec, but it is still defiantly Newfoundland in spirit, even though the mainland is only a ferry ride away. The Gros-Morne Park is spectacularly disposed about Bonne Bay, a drowned valley flanked by relatively lush forests with cliffs comprising mostly Cambrian-age sedimentary rocks plunging steeply to the sea. Down at Norris Point there is a little ferry that will take you across Bonne Bay to Woody Point. On a clear day the crossing is a delight with the sun flashing the tops of the waves and picking out tree-lined coves up the bay. Woody Point is protected from the winter weather, so it has mature trees, as well as immaculate clapboard houses flanking the hillsides to which some of the more affluent islanders choose to retire. Following the road upwards from Woody Point towards the outport of Trout River, you suddenly encounter a different world. All the trees have disappeared as if removed by blight. There is little up here but sphagnum, moss, and a few hardy plants that seem able to survive on nothing at all on the open, rounded hillsides. The whole landscape has been transformed into a dull brown wilderness. The umber rocks suck out any vigor from the sunshine, while on an overcast and misty day you might easily imagine that you were entering Mordor, J.R.R. Tolkien's blasted and evil kingdom, for so little thrives here. The rocks are clearly of a kind on which terrestrial life is ill at ease. Looking closely, it is clear that there are pillow lavas among them. We have seen those bulbous forms before. Then there are some stratified rocks. Their dark and crystalline character shows them to be igneous, and Some of them are the kind associated with mantle material, whilst a few of the dark grains might be the mineral chromite. Elsewhere, there are densely packed dike-sheeted dikes that closely resemble the stacked legacy of ocean floor spreading. Suddenly, it is obvious that the whole desolate area is nothing less than a piece of ancient ocean floor, an ophiolite suite. Its alien bareness is akin to the landscape I encountered under cloudless skies in the Sultanate of Oman. Small wonder that trees cannot flourish on the malnourished hillsides. Rather than becoming obliterated in the plunging mills of subduction, this naked knob of land on the western coast of Newfoundland has been abducted, squeezed upwards rather than downwards, and thereby saved from destruction, since further westwards lay only the great continent of Laurentia, North America plus Greenland. There must have been an oceanic basin to the east from which this slice of crustal history was derived. How could it be otherwise? To this we shall return. The story continues further northwards up the northern peninsula. From here, you can see the inaccessible long-range mountains that form the spine of the peninsula. These are composed of metamorphic rocks of Precambrian, more particularly Grenville, age far older than anything in the Mobile Belt. These speak of earlier ages, other dramas. They were annealed before the first. Rocks around Bombay were laid down under the Cambrian seas. The village of Cowhead is excluded from the park, so it is an agreeably ramshackle kind of place. Youths hang about on the main street, and even the arrival of a geologist is worth a glance. You used to be able to buy a plate of cod's tongues in the Shallow Bay Motel, and surprisingly good they were, too, but the fishing ban probably put paid to that delicacy. I got to stay in a mobile home and in one of Payne's cabins. There only seem to be two family names on the coast hereabouts, the Paynes and the Crockers, so I imagine marriages do not cause much taxonomic surprise. Cowhead itself is a prominent headland connected to the settlement by a natural causeway, or tickle as the Newfoundlanders prefer it. The rocks running along the shore are extraordinary. From a distance it looks as if some titan had emptied out sacks of massive boulders along the cliffs. Closer to, it appears that the rounded boulders are allied to dipping rock beds, cemented together by smaller pebbles and fine limestone. In fact, everything boulders, pebbles, and all is made of limestone. These are conglomerates of a very distinctive kind. Then you notice that individual conglomerate beds are separated by something altogether softer that weathers back. This rock comprises thin beds of limestone and shale. You may have to grub with your geological hammer to claw out bits big enough to break. But wonder of wonders, the shales are full of useful graptolites. Following one bed of shale to the next above, these fossils show a succession of typical species that prove that the earlier half of the Ordovician period is represented by strata of conglomerates and shales. In fact, similar rocks carry on down into the Cambrian. The shaly rocks were originally laid down under deep water. Then, when you bring a bigger and stronger hammer to bear on the limestone boulders themselves, you discover that they, too, yield fragments of fossils, trilobites. I spent more hours than I care to remember persuading tough limestones to give up their shelly treasure trove. On clear days, such work was nothing but a pleasure, with gentle breezes bearing the aromatic smell of pine woods. On wet days it was necessary to keep reminding myself of the nostrum that genius is 99% hard work. This optimistically based on the classical deductive mantra. All genius is 99% hard work. This project is 99% hard work. Therefore, I am a genius. However, the labor was worth it, since the kinds of fossil animals recovered showed two things very clearly. They were species that lived in shallow water, and they were utterly different from their near contemporaries on Bell Island, where this journey began. The conclusion is inescapable that the limestone blocks originated in shallow seas and then slumped or tumbled down to a shale sea floor in massive flows, carrying with them their cargo of trilobites into the domain of the graptolites. At Lowerhead, nearby, some of the blocks are the size of houses. Journey's End is a little to the south and west, the Port Peninsula. This is a comparatively open part of the island with many grassy fields, in which a cow or two watches the world go by. It was once very poor and is still very Catholic. Small square wooden houses sport the longest washing lines in the world. They are hung with trousers and shirts of various sizes graded according to age. When there is a wind blowing, they look like bunting. As usual, the rocks are exposed along the shore, limestones again, but ones that appear different from the spectacular conglomerates on Cowhead. These are regular limestones in regular beds of rock. The strata are gently tilted, so you can climb up or down the rock succession much as you might go up and down a staircase, respectively ascending or descending through geological time. This is about as simple as geology gets. It is known as layer cake. Stratigraphy, compared with the mobile belt, only the gentlest of earth. Movements has disturbed these rocks. In some places on the surface of limestones, it is easy to see coiled shells of fossil snails, which tell the paleontologist that again the rocks are of early Ordovician age for 170 million years. But on Port there are no deep-water graptolite shales. All the evidence from the limestones points to their accumulation in shallow water environments during the Ordovician. Here and there are beds of oolites, for example, made of little rounded grains like millet seed that form only in agitated warm waters, such as you might find off the Bahamas today. Elsewhere, there are fossil algal mats that grew close to the intertidal zone. They look like rucked paper tissues in cross-section where the sea has polished them through, or the limestones have been replaced by dolomite, which is something that happens in hot lagoons. There is no question about it. Not only were these limestones laid down in shallow seas, but those seas lay under a tropical sun. There were calcareous lagoons and tidal flats and oolite shoals where now the gulls keen over a choppy Atlantic Sea. Similar tropical limestones crop out further north in western Newfoundland, right up to St. Anthony at the tip of the northern peninsula. Further afield, they are widespread over much of North America and Greenland. This was a time when sea levels were high worldwide and shallow seas penetrated into the interior of continents. The whole of Laurentia basked under a tropical sun in the Ordovician, a vast area of shallow seas known as a carbonate platform. However we fashion the Ordovician world, it is evident that we are obliged to place Laurentia close to the equator of the time, and the trilobites, some of the species found in the tumbled blocks at Cowhead, are found also in situ in the contemporary platform limestones. So this is where the blocks must have come from. They slumped and tumbled off the edge of the carbonate platform at the rim of the Laurentian continent, as it was in the Ordovician, into the deep sea and into history. One final fact. Careful geological mapping showed that both the Cowhead conglomerates and the Bay of Islands ophiolites were piled on top of the carbonate platform limestones. This happened along a series of thrust faults, a shove of the earth that propelled huge tracts of land towards Laurentia. Unlike the platform rocks on which they lay, the Cowhead rocks and ophiolites were tipped steeply, folded, and faulted. They had suffered as they moved. How are we to interpret the geology we have seen as we bobbed like a restless seagull from east to west over the rock? Plate tectonics, finally, supplied a satisfactory answer, but understanding came piecemeal. It is necessary to avoid thinking of the progress towards what we now know as a kind of moral improvement It must always have felt as if the tectonic truth were just around the corner, but the confident assertion of today is all too often the retraction of tomorrow. To the pioneering geologists making their first maps, it must have seemed enough simply to lay out the ground into its constituent rock formations. They would have been delighted to find sufficient fossils to put some dates on the rocks of the Avalon Peninsula, just as on the other side of the island, as early as 1865, the Canadian paleontologist Elkanah Billings was uncovering trilobites from the same limestones I had chopped with my hammer more than a century later. Edouard Suess was certainly aware of the integrity of the ancient continent of which those limestones formed a part. That vast region of North America, which is formed on ancient rocks overlain by horizontal Cambrian strata, has received the name of Laurentia. This expresses the idea clearly enough. He noted that Cambrian trilobites overlay the older schists of the northern peninsula in Newfoundland, making that part of the island a sure component of Laurentia. And he was insistent that Greenland belonged to the same continent, too. Greenland is a part of Laurentia was an assertion important enough to be worth italicizing. It was also clear that the geology of Newfoundland connected southeastwards with that of eastern Canada and beyond into Maine, Vermont, and New York State, and thence to the southern states. The whole grain of the Appalachian Mountains followed the same northwest to southeast trend, just like the faults separating the main geological divisions. The Blue Ridge Mountains traced the identical line, as did the Alleghenies. Then there were the metamorphic rocks, those schists and gneisses that gave such clear evidence of having been caught deep in the vise of the earth, but which were now disinterred. They, too, could be followed from Newfoundland to the Appalachians close to the edge of the great Laurentian continent. Surely these rocks prove that a range of mountains, more elevated and dramatic than today's scenic remnants, had once towered above the Laurentian interior. Hundreds of millions of years of erosion had brought them down, exposing their innards to the snows and rains of the 21st century. To be sure, there are places where the mountains are still splendid and wild, especially where granites have bolstered their durability. But there are others where silvery schists crop out along urban roadsides, under the sumac trees, or are dug out to make the foundations of superstores. Geological time is enough to wear down the mightiest peaks and lay low former Everests. It was appreciated early on that there was a contrast between the successive Cambrian or Diivision and Silurian sedimentary rocks that accumulated under the sea on the Laurentian platform, and those that were laid down at the same time along the Appalachian line. James Hall was a great geologist who prepared the first official accounts of the fossils and strata of New York State. In 1859, he observed that the sedimentary rocks of the Laurentian platform were 10 to 20 times thinner than their time equivalents in the folded mountains, where sedimentary piles could be several kilometers thick. It was evident that linear troughs followed the trace of future mountain chains, which were steadily subsiding over millions of years, simply to accommodate all that sediment. In 1873, James Dana, whom we met earlier, called them geosynclinals, literally a sag in the earth, and Suess used the same term, though the alternative designation, geosyncline, is the one that later stuck for more than half a century. For a while, geosynclines were very popular. 40 years ago, the crumpled and complex mobile belt of Newfoundland would have been considered a typical result of a deformed geosyncline. Many different kinds of geosynclines were recognized in the 1950s, most notably by the Prince of Geosynclines, Marshall K. of Harvard. He tacked all kinds of prefixes, taphro dash, poly dash, etc., on the geosynclines to designate what he considered their distinct geological circumstances. Marshall K. is principally remembered rather affectionately by those who met him as the most garrulous man who ever lived, but he did point to Newfoundland as an ideal place to study the genesis of ancient mountain chains, in which regard he was absolutely correct. The problem is that the mere fact of a thick pile of Appalachian sediments alone does not explain how they subsequently came to be folded and metamorphosed, in short, to have all the features of a mountain belt, a great thickness of comparatively light sedimentary rocks accumulating in a geosyncline would ultimately rebound because of isostasy like a depressed rubber duck bouncing back upwards in a bath. The lower parts of the sedimentary pile might have been temporarily subjected to sufficient heat and pressure to become metamorphosed, but the effect would not have been adequate to account for the extreme conditions required to produce some of the minerals found in schists and gneisses, nor for the observable tectonic mayhem and thrusting, such as forced the ophiolites in western Newfoundland over the platform limestones. Arthur Holmes struggled gamely with applying geosynclinal terminology, but found it inadequate. Clearly, as the detective in Locked Room Mysteries is wont to say, it was time to consider the facts in a new light. The acceptance of mobile continents provided more than merely new illumination. It supplied a floodlight. The 1964 edition of Holmes includes a diagram showing what Europe plus America looked like when you closed the North Atlantic Ocean prior to the breakup of Pangaea. An extraordinary convergence happens. The whole Newfoundland Appalachian mountain chain suddenly joins hands across the non-Atlantic with another ancient mountain chain, the Caledonides. Caledonia was, of course, the Roman name for Scotland. O Caledonia, stern and wild, meet nurse for a poetic child, land of brown heath and shaggy wood, land of the mountain and the flood, declaimed Sir Walter Scott, who celebrated its romantic embodiment in the Lay of the Last Minstrel. The Caledonides, however, do not just include Scotland. The ancient mountains have a compass as generous as that of the Appalachians. Like that range, they comprise a complex of lower Paleozoic rocks variously folded, faulted, or metamorphosed. Wild country, for the most part, mountains and brown heaths. Indeed, the chain ran south, west and northeast through Ireland, embracing hilly Wales and the Lake District, much of rugged Scotland, and thence to include the whole of the Scandinavian coastal mountain chain running through Norway from Stavanger in the south to Hammerfest in the north. This section alone spans more than 10 degrees of latitude, close the Atlantic Ocean, and the Caledonides run on naturally north of Newfoundland. The whole chain, when put together, snaked its way through the midst of the ancient supercontinent of Pangaea. Had we been able to peer from a satellite in Permian times, the Appalachian Caledonian line would have been one of the most easily recognizable signatures written on the face of the globe, a seam ancient even. Then, clearly, the opening of the Atlantic Ocean had ripped apart two segments of a single geological monument, not neatly so either, but raggedly, like an incriminating photograph roughly torn in two by a jealous lover. Edouard Seuss had not recognized the northward continuation of the Appalachians for what it was. For him, Newfoundland was the local end of the structure. If anything, he traced the continuation of the Appalachian chain into what he termed the Altades of Europe and Asia. Marcel Bertrand and, later, Arthur Holmes had spliced the Caledonides and Appalachians together. By 1964, when the second edition of Holmes was published, the drifters had finally achieved respectability. The recognition of such an extensive, ancient range could be viewed as another consequence of the acceptance of Pangaea. The Caledonides themselves had a tradition of study that was both more historic and more intense than was the case for Newfoundland's geology, largely because these ancient mountains crossed a major part of Western Europe, where there were many geologists. After all, Britain was where the rocks of the Cambrian, Ordovician, Silurian, and Devonian periods had first been discriminated one from another during the 19th century. The very names still embody country, Cambria, Roman Wales, County Devon, or ancient tribes, Ordovices, Silures, that were part of the human history of the British Isles. This is where the type areas for rocks of these ages still reside. Pioneer geologists did fieldwork in areas they could reach by train or on horseback or by foot. Improvements in public transport, particularly expansion of the railway networks, made formerly inaccessible areas readily available for study, and how those pioneers could walk. When Ben Peach and John Horne exquisitely mapped vast areas of the Highlands of Scotland, at the end of the 19th century, they thought nothing of covering 30 miles a day of brown heath and shaggy wood across some of the most strenuous territory in Britain, as so often geological maps drawn by heroic foot sloggers preceded tectonic enlightenment. Hard on the heels of the first maps were furious geological rows about the interpretation of particular features. In the Northwest Highlands there is a geological line running from Durness in the north to the Isle of Skye in the south that marks out the contact between metamorphic rock gneisses and schists to the southeast, and what I have called platform carbonate sedimentary rocks to the northwest. The latter are of Cambrian to Ordovician age and virtually identical to the rocks that underlay the Port Peninsula in Newfoundland. They even have the same fossils. In a book that records the true density of historical detail accompanying discovery, David Oldroyd has written excellently about the controversy surrounding this single contact, the meaning of which occupied some of the most famous geologists of the 19th century. On modern maps, the outcome of these intellectual battles is recorded by a mere 2 words, Moyne thrust. The metamorphic rocks have been bodily pushed northwestwards over the platform sediments in a thrust movement comparable with that around Bon Bay in Newfoundland at the western edge of the Great Mountain Range. The rocks under the thrust were ground to paste under the weight of vanished mountains, a paroxysm of the earth now marked by no more than a bluff, where a few sheep graze and the wind tickles the cotton grass. Charles Lapworth, who was as instrumental in working out the truth of the Moyne as any geologist, described it thus in 1882, conceive a vast rolling and crushing mill of irresistible power, shale, limestone, quartzite, granite, and the most intractable gneisses crumple up like putty in the terrible grip of this earth engine. It is hardly possible to describe such an historic drama in the dry language of science. Southwards, the highlands themselves are a metamorphic geologist's delight and a paleontologist's despair. Even if the rocks were once full of tiny bugs, what could survive? Schists, gneisses, and quartzites rule, making for wonderful scenery and no fossils. In fact, most of the rocks were originally deposited in the Precambrian, so you would not find large fossils there. Anyway, you are obliged to remind yourself that today's steep hills are but a remnant of the grand Alps that once towered here. It still seems like hard, uphill walking, particularly on wet and windy days, which constitute most of the year. Patient mapping by officers of the Geological Survey of Great Britain has shown that the metamorphosed strata are twisted into great overfolds and naps, comparable with those of the Alps, that are now concealed beneath bogs or partially exposed along the flanks of the wildest hills. Kilometer-long slabs of the earth have been overturned hereabouts. The crust must have been thickened by the earth engine as one fold piled on another as the mountain range rose up, and then the great pile was subjected to heat and pressure deep within the earth. As the rocks cooked, new minerals grew. Which particular mineral appeared depends on the conditions of temperature and pressure that the buried rocks experienced. There are minerals with simple chemical compositions, like aluminium silicate, which produce different minerals according to how hot and pressurized they became. One of the most famous diagrams in geology is a profoundly simple one that shows the different conditions required to grow one of three mineral varieties of aluminium silicate. Enough pressure and you find kyanite. Enough heat and you get sillimanite. Less of either and you get andalusite. It is almost like whether you get fudge or toffee when you boil sugar. This mineral cookery can stand in for dozens, if not hundreds, of experiments carried out in the laboratory that simulate natural conditions in pressure cookers to find out which mineral is stable at a particular temperature and pressure. Natural circumstances are often more complicated. For example, the presence of even small quantities of water as an extra component can change the outcome, but the scientists who like these kinds of rocks can now map out the temperatures and pressures in these metamorphic belts much as field geologists map out rock boundaries. It is a way of peering into the intimate thermal history of mountain belts. The highlands were one of the testing grounds for this kind of science, where the idea of metamorphic grade was refined. The higher the grade, the more profound the tectonic suffering. It is even possible to plot out the subsequent cooling history of the rocks as a high-temperature mineral reverts to a lower-temperature one as it cools, whilst leaving its original signature in the crystal form preserved in the rock. The highlands have seen it all: heating under pressure, cooling, uplift, and deep erosion. These rocks make for thin soil and poor drainage. Then there are faults. The Great Glen follows one of those profound displacements with a northwest-southeast trend that we have seen in Newfoundland. Long, thin. Loch Ness merely fills the gash. The southern part of Scotland has not been heated so much. Endless bleak, rounded hills composed of shales and ribs of tough gray wax make up the southern uplands. All of such rocks were originally deposited under marine conditions. Up on the coast at Ballantrae, there are volcanic rocks that compare with the ophiolites in Newfoundland. For the most part, these rocks are folded and thrust, in places furiously concertinaed and rucked. Were it not for the friendly graptolite fossils, this land would have been beyond decoding. As it is, careful mapping has disclosed its secrets. Following stream beds, delicately chipping at the dark shales, the little silvery films of graptolites betray the ages of this mass of similar-looking rocks. It is not merely that Silurian rocks are concentrated towards the south and Ordovician. To the north, the wild, open country is divided into northeast-southwest segments and bounded by thrusts, as if a gargantuan machete had butchered the whole of it into slices, and within each slice the strata rucked and repeated. It is obvious that if all the folds and all the salami slicing of the crust were straightened out and restored to their original disposition, then this must be a region where everything has been compressed, to use the jargon. There has been crustal shortening. What was once spread out on the ocean floor has been compressed and stacked and folded in the process. It might seem impossibly complicated, but a plate tectonic explanation made it seem simple at a stroke. Southwards again across the Solway Firth into England and the Lake District, those who have queued to have a look around Dove Cottage at Grasmere may well have regretted that William Wordsworth and his friends made the lakes so popular, but you have only to walk up a hill like Skiddaw to get back to wildness. There, the sight of other walkers a few 100 meters away from you serves only to put a scale upon the open landscape and the dark, bald hills in the distance. The rocks themselves frequently resemble the apparently endless marine shales and grits of the southern uplands of Scotland. Although they are less crumpled, they have been heated enough to impart a delicate blue-green hue, which is because of the abundance of the low-grade metamorphic mineral chlorite. The geology of the Lake District is still being worked out. Only 5 years ago it was realized that huge Ordovician submarine slumps or slides, like those in Newfoundland, had affected considerable areas. Fossils other than graptolites are very rare. It requires patience and luck to find trilobites in the early Ordovician slates, and when you do, they are not beautiful. They, too, have suffered with the rocks, but enough have been found to tell us that they are similar to species found from Wales, France, and Morocco. Thus they link also to Bell Island in eastern Newfoundland, but not to Laurentia. It grieves me to have to pass over Wales in a few sentences, for I have spent years working there, and have grown fond of its open hills and fern-choked streams. Fossils have helped unscramble its geological complexities, and my work has helped fill in some of the details. In Wales, you always have the feeling of following in the footsteps of great geologists, sometimes revisiting the same quarry as they did for the same reasons. The rocks are often folded, but there is little of the alteration that has afflicted the Highland strata. To be sure, some of the shales have been changed to hard slates by being squeezed. In the inescapable vice of regional compression, particularly in North Wales, but enough has survived to permit the discrimination of strata. Cambrian, Ordovician, and Silurian fossil animals were disinterred in order, even though there were vigorous disagreements among the pioneer collectors in the 19th century about exactly how the geological time embracing this succession of organic remains should be divided. By the time of Edward Seuss' global compilation, however, such problems of definition were largely resolved. Geological time had labels for the periods on which to pin our understanding. Cambrian described a time interval as well as a region on the map. The classical rock successions of the Principality are usually described as comprising the Welsh Basin, which sounds a rather domestic term for a thickness of several kilometers of overwhelmingly shaly rocks. Of course, this sag in the earth had also been described as a geosyncline in its time. In the midst of the basin are the deposits left behind by Ordovician volcanoes, forming the untamed heart of the Cambrian mountains, including Snowdon, where you feel as if the glaciers of the last ice age melted only yesterday. Small wonder that these wild fastnesses preserved the Welsh language from extinction, while cultures came and went in the softer countryside of England. The fossils, too, have been sequestered safely. On the western tip of southern Wales, there is a tiny blob of land, Ramsay Island, home to many seabirds and a few sheep. On the top of the windy cliffs on the northern end of the island, you can grub out pieces of a rather tough, sandy rock, while far below you the sea boils and seethes against the cliffs. It is the kind of place where you routinely lose your hat. Persist hatless, though, and you will recover specimens of the Trilobite Nezeretus, the same beast that occurs in the early Ordovician rocks on the far side of the Atlantic Ocean on Bell Island, not far from Ramsay Island on the mainland coast in the pretty little inlet of Abercastle. You can find its companion Ogygenus and the Cruziana tracks that are so common in Newfoundland. 25 years ago, I took the coastal steamer along the length of the Norwegian Caledonides. The cruise took more than a week. This is fjord, coastline forma typica. During the Pleistocene, indeed, until a few thousand years ago, a huge ice cap on the mountains fed glaciers that nosed their way to the sea along the length of Norway and carved out their paths deep into the country rocks. When the ice age came to an end, the glaciers retreated, but left their steep-sided gouges behind. As the polar ice caps melted, the sea level rose and flooded the valleys, so that the coastline is today deeply excavated by sinuous marine inlets. Even when the open ocean rages as it often does, at these latitudes the fjords can be spookily calm. The mountain slopes rise steeply and implacably above the narrow shores. As in Newfoundland, the fishing communities led isolated lives in the coastal villages. Different dialects recorded the separation of the populations. You cannot take issue with the tourist blurb, spectacular fjord scenery, picturesque fishing, Villages, unrivaled vistas, that kind of thing. I do, however, recall an excess of trolls. In every fjord it seemed that some troll or other had left his mark. On your left, the guide would remark, you will see the famous Troll Cave. In the next fjord, a looming lump of rock with vague breasts would be described as the famous Troll Wife. A day later, a pinnacle would be the illustrious Troll Castle, and so it went on. When our boat put briefly into harbor at the small towns dotted up the coast, it was something of a relief to escape the trolls and look at the rocks. The random samples presented to us were metamorphic, often high-grade gneisses like those in parts of the highlands. There were also igneous rocks of several kinds. It was clear at a glance that this part of the Caledonides belonged to a most highly deformed part of the Great Range. It is an enormously difficult country to understand geologically, even though the rocks are so well exposed along Trovfjord and on Troll Mountain. Swedish, Norwegian, and more than a handful of British geologists have spent their lives unraveling the structure of the ancient ranges. That they have got so far as a major achievement. It has been shown that the Norwegian Caledonides comprise a series of great naps, somewhat on the Alpine model. A marvelous cartoon shows two Scandinavian professors of geology fighting over which direction the naps came from, east or west. Professor Svenonius attempts to push them one way, while Professor Tornbohm tries the other way, both of them puffing like bad-tempered trolls. The answer is now clear. The root zone lay to the west. Eastwards lay folded rocks of the region around OSL-OA, an area famous for its Cambrian and Ordovician fossils. Eastwards again lay the platform rocks of Sweden and the Baltic states. No, the huge overfolds had to come from the seam to the west that was revealed when the present Atlantic Ocean was closed. Not only that, subsequent work has proved that there are four major naps piled one on another, like some tectonic pickaback on an enormous scale. Imagine the whole country is like a club sandwich of tectonic slices. Furthermore, they are stacked in order. The highest nap has traveled the furthest from the west. Those lower in the pile have traveled progressively shorter distances. Fossils even help with this discovery, since there was one corner of the highest nap that escaped the regional metamorphism, and in one corner of that corner trilobites and brachiopods were discovered. Some of them were like species from the platform limestones of western Newfoundland, such as the briefest of sketches of the Appalachian Caledonian mountain chain. When the Atlantic Ocean opened as Pangaea broke up into pieces, it evidently did so approximately following the line of this ancient range. But there is an enormous time gap. The opening of the new ocean happened well over 200 million years after those ancient mountains had been elevated to Himalayan proportions. The vast time interval in between had been occupied by the ineffably slow grinding down of the mountain range, for whatever presumes to height will eventually be laid low by erosion. Ice, wind, and rain are inevitably attracted to mountainous regions, and by the same token guarantee their eventual leveling. Many Devonian age red rocks record the waste, morass, from the Appalachian Caledonian chain and still survive along the flanks of the old mountain system. In Scandinavia, Greenland, Scotland, Wales, and New England, these freshwater, sedimentary deposits are of more than passing importance in the history of our planet, because they contain graphic fossil evidence of the transition of life from water to land. This is where four-footed animals began, but that is not our story. From the geological point of view, the salient fact is that the widening Atlantic Ocean followed an ancient seam, an old memory revived, a weakness exploited. But the opening did not follow the old seam exactly. Consider that in Scotland, northwest of the Moyne Thrust, the trilobites are like those of Laurentia. This is a fragment of Earth's crust that really belongs On the other side of the ocean, when the Atlantic Ocean opened, this fragment was, as it were, left behind on the wrong side of the widening seas. Contrariwise, the Avalon Peninsula in Newfoundland truly belongs with Wales, Spain, and North Africa, for that is what those trilobites Nesoritis and Ogygenus told us, even though it now dangles off the eastern coast of the rock. You could say that this piece of Newfoundland has been marooned on the Laurentian side. Small wonder, perhaps, that it feels so like Cornwall. You cannot trust the permanence of geography in a world on the move. Now we come to a crucial question. As the Atlantic Ocean slowly widens at the present time at the pace at which fingernails grow, according to a familiar analogy, no new mountain belt is being generated along the old Appalachian-Caledonian line. This is because both sides of the Atlantic Ocean are passive margins. No subduction happens, no volcanoes, no mountain building, just slow drifting apart. This leads you to wonder, how did the Appalachian-Caledonian mountain chain get there in the first place? Mountain belts, like the Himalayas, are associated with active margins. Surely, then, it follows that at one time there were active margins with subduction zones running along the length of the Appalachian chain. This was a conceptual break, though, that changed our way of understanding how the world works. Simple to state, perhaps, but hard to conceive of as an idea. The crucial scientific paper was published as a short note to the journal Nature in 1968. Under the title, Did the Atlantic Close and Then Reopen? The author was Tuzo Wilson, whom we have met previously as one of the crucial players in developing plate tectonic theory. The idea he had was straightforward. 500 million years ago, there was a great ocean. Call it the Proto-Atlantic, separating Europe and Laurentia. That oceanic separation accounted for the very different kinds of Ordovician fossils found on either side of it. The differences between what you could collect on Bell Island and the Port-au-Port Peninsula in Newfoundland, for example. The ocean broadly followed the line of the present North Atlantic. That ocean then closed, probably by the late Silurian Devonian period, involving the usual processes of subduction, and it was this closure that threw up the Appalachian Caledonian Mountains. They were the Alps or Himalayas of their time. This was when Charles Lapworth's great Earth engine ground away at its work. By 400 million years ago, the process was completed. Several hundred million years later, the present Atlantic opened passively along the weakened and eroded line of the ancient mountain chain. Simple as that. The fact that Tuzo Wilson had put a question mark at the end of the title of his paper signaled that his conclusions were speculative, top-notch scientific. Journals do not usually like speculations, but the note survived the editorial review process, no doubt because it came from such a well-known and innovative thinker and made it into print. A few hundred words that changed the way we look at the world. Tuzo Wilson's paper revealed a wholly novel way of applying Lyellian methods to very old mountain belts. Plate rules applied in the distant past. You could now look for evidence of the same kinds of tectonic and volcanic processes as happened today around the Pacific Ocean, perhaps in rocks that had been caught in Earth movements hundreds of millions of years ago. A corollary to the methods that had begun in the Temple of Serapis could now be played out on the bleak shores of Newfoundland or in the Arctic. Caledonides. Of course, Wilson's model was far too simple, although right in essence, but it was the changes it wrought in the way geologists looked at familiar rocks that was important. The world may have stayed the same, but the perceptual glasses through which it was observed had changed. At such crucial moments, we have already seen that there are those who run with the ball, while more cautious souls wait to see who the crowd will follow. So it was on this occasion. John Dewey was a young lecturer at Cambridge in the 1960s. He was quick to appreciate how the whole Appalachian chain, and particularly the Magnificent cross-sections seen in Newfoundland could be viewed in the light of the vanished ocean. He worked at a furious pace to be ahead of the game. He occupied a room adjacent to mine and seldom left it during the crucial period, except to go into the field or to conferences. A kind of metabolic speediness makes John Dewey speak at twice the pace of anyone else I know, as if his tongue were struggling to catch up with the pace of his thoughts. He can give the impression that he is not listening to what you have to say, but I have concluded that he actually absorbs it, processes it, and assesses it as uninteresting, all within a couple of seconds. The only truly disconcerting thing about him is, or at least was, a propensity to do handsprings impromptu and other such athletic feats. As a field geologist, he is superb when his whole concentration is focused on the rocks before him. He has a knack of apparently instantly fitting the detail he has seen not merely into a fold, but into a whole mountain range. To hold the totality of the Appalachians and half the Caledonides in his brain came naturally to him. Dewey had worked in Ireland and had been to Newfoundland with Marshall. He was primed to make the plate tectonic reinterpretation. Hank Williams was open to the new paradigm, too, and in his case the emphasis was on what he was best at, making maps. From maps of small and difficult areas around Gander, he graduated to maps of the whole Appalachian chain, interpreted in the light of plate tectonics, but based ultimately upon what could be seen in Newfoundland. As to complications, Wilson's simple sketch showing the two continents could have implied that their closure was almost like whacking together two blocks of wood. The real world is much more various and complex. In particular, there are volcanic island arcs, perhaps several, that will collide well before the main event, which happens when continent collision eventually occurs. They are outriders, if you like. Basins before and behind such arcs collect sediments that become entrained in the whole tectonic process. When one continent does eventually engage with its opposite number, the relentless pressure and crustal thickening where two thick crustal blocks meet induces the highest grade of metamorphism, making it likely that naps are then squeezed out. This is the furious center of orogenesis. But it is also possible to have a much softer approach of continents. For example, if the opposing sides are concave, you can try an experiment to illustrate this that is valid in spirit, if not to the letter. Make a small, book-sized block of modeling clay. If you press it hard between the flats of your hands, it will buckle intensely. In some tests, part of it will mushroom upwards. But if you use cupped hands instead, you will get much more modest crumpling, and more of the original width will be preserved. The latter case is more like Newfoundland, which is why geologists love it. Less has been obliterated. You get a real chance to find out what happened within the vanished ocean. Then there are major faults. It is rather tempting to assume that closure of an ocean was like automatic doors slamming shut. It does not have to have been like this. Some of those faults may have been the site at which huge blocks slid past one another. Transcurrent movement, rather than moving up and down. This opens up the possibility that rocks that are neighbors now across faults may have had a very different relationship in the past. Everything, it seems, is capable of being somewhere else. Proto-Atlantic is not a very appealing label, too indefinite, and the vanished ocean soon acquired a better one. Lapidus. It is surprising how the provision of a proper name confers respectability on a concept. In a curious way, naming it makes it real. Paradoxically, but appropriately, Lapidus was an entirely mythical name. A Titan, the son of Uranus by Gaia, the Greek Earth goddess, since he also fathered Atlas, which identifies a range of mountains, and Prometheus, provider of fire to mankind. You might say the geological credentials of the name are impeccable, and geologists were happy to accept it. So we can now examine our trip across Newfoundland in the light of Dewey and William's reworking of the island's history. It became the story of the life and death of the Lapidus Ocean. Belle Island and the whole Avalon Peninsula lay on the eastern asterisk side of a wide Lapidus in the early part of the Ordovician period. The trilobites, like Nezeretus, that scuttled over the sandy sea floors, were happy scratching out a living in cold water, for at the time Avalonia was at high, even frigid latitudes. This can be confirmed by Paleomag. We have seen already that these particular animals lived over an area that embraced much of Europe and northern Africa, which is where the South Pole lay at the time, and helped map out the former Gondwana continent. If we now jump to contemporary rocks on the other side of the former ocean, we arrive at the limestones of the Port Peninsula. These rocks were laid down in shallow seas close to what was then the equator. The snails and sponges and trilobites that are found encased within them are all completely different from those on the eastern side of Newfoundland, not just different species, but even different families. Well, of course they are different. They were living in the tropics on a limy seafloor. We would not expect to find the same seashells living today in the cool waters off the rock as in the blue lagoons of the Caribbean. In their own way, these tropical fossils were just as distinctive as the cool water ones on the east of the island. Many of the species are found widely distributed over the Laurentian continent that much had been recognized even before Edouard Suisse. So, in the early Ordovician, Iapetus was wide enough to have one side in high latitudes and the other in the tropics, a massive ocean, indeed, remaining for a while on the western side of the island. The spectacular boulders and their intervening shales around Cowhead can now be seen for what they are: debris that collapsed off the margin of the Laurentian continent, where there was enough of a slope to prompt instability. Once an earthquake set a few large, tumbling blocks in motion, they would gather force, picking up other fragments on their dramatic slide as the whole slurry rushed down the slope into the deep water beyond. Mud may have lubricated the process. It is no wonder that the boulders look as if they had just been dumped out of a gigantic sack. Then quiet conditions returned for a while, and shales were slowly deposited on top of the boulder beds, and graptolites gently came to rest there to provide us with our yardstick for the passage of time. It must have been a good environment for them. I collected dozens of specimens from thin shales around St. Paul's Inlet, laying them out in the sun, something like 470 million years after they had first come to rest on the sea floor. As for the dark and treeless country above Woody Point, this was a slice from the ancient sea floor itself. We have seen the evidence that would be needed to prove the existence of an ocean to the east, and these brown hills comprised a piece of it miraculously preserved. Pillow lavas, dikes and sheets, even the deeper layers of mantle-type rocks, like Lurzelite, the whole cross section of oceanic crust was there. Out of the depths of time and the depths of the ocean, history was preserved in this ophiolite by the bleak road to Trout River. Mapping showed that both the Cowhead rocks and the ophiolite were stacked on top of the limestone platform thrust into place. Furthermore, the ophiolite lay on top of the Cowhead rocks. As in the Norwegian naps, the highest slice had traveled the furthest distance. We can imagine a massive shove from the east, first slicing up and then pushing over the Cowhead rocks onto the platform, and then heave a sliver of ocean crust from far away being piled on top again. This small part of marginal Iapetus was pushed upwards and outwards rather than being doomed to destruction, for which redemption all geologists are grateful. It all proves that there was plunging down subduction of ocean crust in a westerly direction in the Ordovician. Some part of the floor of Lapidus was diving. beneath the rigid mass of Laurentia. It was being consumed just as the Pacific floor is destined for destruction along the edge of Asia. The ophiolite escaped the general destruction, but was propelled in the same direction as the subduction zone. Now, at last, the contrasting rocks that line the shores of Bombay and the northern peninsula made sense. What might seem like baffling complexity when you are standing on a single outcrop of rock, scratching your head at a particular crumple, can be simply explained in a paragraph once you set the ancient plates in motion. The age of the thrusting event was not, perhaps, what you might expect. It stands to reason that the date of the thrust has to be after the youngest platform limestones over which they are driven, since the latter are of mid-Ordovician age. That sets a lower limit. Nothing in the Cowhead rocks goes any younger than that age either. At the very top of that set of rocks there is a peculiar green sandstone full of the kinds of minerals you would expect to be derived from a volcanic island. But there are no such islands to the west, so these must have been derived from the east, towards the open ocean. These features can be explained if a volcanic island arc was approaching from that direction. The major abduction of the ophiolite occurred in the middle part of the Ordovician when that island arc encountered Laurentia, even as it was being carried relentlessly westwards by the motor of subduction. This event was long recognized southwards in the Appalachians, where the folding associated with it is known as a tectonic orogeny. The implication is that the closure of Lepidus was much more interesting than just a collision of two continents. This crunch was heralded by several other tectonic events as island arcs and possibly isolated oceanic islands were all carried alike on the conveyor belt of oceanic destruction. In the Ordovician, Lepidus was still wide but closing. Folding and destruction at the active margin happened over a long time period before continent-continent collision during the later Silurian. Some of the major faults separating Hank Williams zones might well mark boundaries between these different events in Lepidus' history of closure. Now, it is even possible to make something of the mobile belt, moving eastwards over the long range. It would not be too gross a simplification to describe the dunnage zone as the squidge region of Iapetus. This is where residues of the great ocean are crushed together in perplexing ways. In other parts of the Appalachian-Caledonian chain, equivalents of this region have been squeezed or subducted out of existence. It is good fortune to have it preserved in Newfoundland because of its soft closure. In places, the chaos seen on the ground is exactly the turmoil you might expect, where pieces of ocean floor get mixed up with pieces of volcanic islands and all blended with sediments that accumulated off their flanks. The latter tend to give more easily and can be twisted around like so much black lasagna. It is small wonder that some parts of the dunnage are so difficult to interpret. The zone includes volcanic islands that have survived to the present and as many places in which blocks of volcanic rocks have slid down into the surrounding sedimentary shale basins to make that perplexing melange. The detailed geological map of the area shows just about every rock type you can imagine. The fine-grained silica rock, known as chert, is worth mentioning because it is often associated with volcanic rocks and with what Marshall K. would have called a eugiosyncline. But there are sandstones, too, some of them the kind that originally rushed downslope as sand in suspension in the kind of slurries that have been termed turbidity currents. There are even blocks of limestone containing fossils. These were probably laid down on the margins of the islands before tumbling into the depths where they were preserved. A great variety of igneous rocks add to the richness of the geological potpourri. Once upon a time, geological observers who pottered in their dories around the northern bays of Newfoundland were as confused as the rocks. But now we can see that the confusion itself is the outcome of explicable processes. As for the Gander Zone, the heart of mountain building lay there. It was the site of a thickened pile of sediments and volcanic rocks that experienced the full effects of Gondwana colliding with Laurentia. The Crunch Zone, if you like. Initially, the rocks between the two great masses accommodated to the pressure by crumpling, and then by sliding and pushing over one another, shortening the crust but also thickening it. Initially, perhaps the thick pile might have depressed the geothermal gradient deep in the crust. But when the heat gradient recovered, the vast folded pile then heated up at depth and the minerals composing the rocks became progressively uncomfortable. They needed to change in harmony with the new ambient conditions of heat and pressure surrounding them. Metamorphism took over. The mineral legacy of this time is frozen in the rocks today after tens of millions of years of exhumation from the deep cauldron of the earth. The garnets and the micas speak eloquently of the strata's ordeal. They can be read like fossil thermometers and pressure gauges. In some places, the original strata and folding of the rocks can still be discerned through the transforming prism of metamorphism, like faded snapshots in which a vanished scene can still just be made out. In other places, the rocks have been so transformed that any banding they show is only a reflection of the way minerals grew as they adapted to their clenching by the Earth's interior. Those pink rocks I saw not far from the Trans-Canada Highway migmatites were so transformed that they began to melt, to sweat out a magmatic juice that was not far from granite in its constitution. Quartz in solution was squeezed out, subsequently, to infiltrate surrounding rocks, filling fissures and pods. Finally, granite. Magma nudged into the center of everything, and all the while the mountain range grew. For this is how the world bends, with neither a bang nor a whimper. The crust at first winces and buckles, then gives before inexorable tectonic forces, then piles up and dislocates. As mountain building precedes it, heats up and changes its composition in an attempt to adapt to its profound new circumstances. Finally, it may melt. It is hard to avoid dramatic imagery, even in the most sober account of such continental concatenation. There is a shortage of words to embrace all that buckling and thrusting and roasting. So a journey across Newfoundland is a journey back to the time of Lapidus. Stand on the cliff tops at St. John's, and the early stages of this ocean can be imagined, a time when it was wider than the Atlantic. Pause under the fragrant conifers on Cowhead, and you can visualize its subsequent destruction. All the evidence is laid out upon the ground. Hardly a pebble on the beach that could not somehow be related to an ocean that vanished hundreds of millions of years in the past. Now another sea washes upon the old ocean floor, or polishes rocks that once were forged anew in the bowels of the earth. You can pick your way over a shoreline that was once the site of massive slides. Barnacles now encrust pieces of foundered volcanic islands, where trilobites once hung on to a precarious existence. Newfoundland provides but one profile of many across the former ocean, and to explore them all would take a book much longer than this. A brief review is all that is possible here. Hank Williams was able to map out his tectonic zones southwards all the way down the Appalachian chain. Avalon continued into eastern Canada, a connection that had been noted as early as 1887 by Marcel Bertrand, who, with bold hand, traced the connecting trend lines. As Seuss remarked, the other zones expanded or contracted all the way to the Carolinas and beyond. In some parts of New England, the metamorphic belt expanded and fresh mapping revealed huge naps. Old observations were dusted down and examined in the new light of ancient plates. Edouard Seuss himself had recognized lateral movements in the Appalachians and had surmised that they were propelled from the west. He, too, had wrestled with the problem of how to account for such long, linear features as the Blue Mountains He had to have a global mechanism and opted for a contraction of the Earth's interior, which caused the crust above to slide and buckle along. Zones of weakness. It was ingenious, but ingenuous, and there has never been subsequent evidence for a contraction within. But all those geologists who looked again at the Appalachians found the plate tectonic interpretation to be nothing less than a revelation. Disparate observations all seemed to fall into place. This bed of volcanic rock was arc-related. That piece of chemistry was oceanic. Science proceeds by 1,000 small advances when a basis for understanding is in place. Once the big picture is drawn, the coloring in can begin. And the geosynclines? They simply became expressions of different sites along continental margins. The thickness of strata accumulating off the edge of the Laurentian carbonate platform was not so remarkable on a continent edge. It was to be expected that the more oceanic sites included thick layers of volcanics and shales and cherts, especially in basins related to island arcs. Geosynclines became an epiphenomenon of plate tectonics. We can move northwards into the Caledonides, where much the same enlightenment took place. There was no shortage of old field data that could be recruited into the new way of seeing. No less than 150 years of the tramp of boots and the tapping of hammers. England and Wales were part of Avalonia. The fossils that I had collected in stream bed and quarry told no lies. The limestones of northwest Scotland were a part of the opposing side of the present Atlantic, a stranded fragment of Laurentia. They were just the same as the rocks on Porto Port, down to the identical little snails curled up on the bedding plains. Between Wales and Durness, therefore, lay the wreck of Iapetus. There was an ophiolite in Scotland, too, albeit a much more modest affair than its Newfoundland counterpart. This comprised the pillow lavas and Sapenninites and cherts, Steinman's famous trinity, on the coast at Ballantrae. Delete Ballantrae volcanics from the geological map. Substitute Ballantrae ophiolite, such as the mundane end of a great revolution in thought. Then there were the folded and faulted rocks of the southern uplands that formed such uncompromisingly bare hills, beloved only of sheep and masochistic walkers. They, too, could now be looked at in a different way. That the country was sliced up into northeast-southwest trending packages was already recognized, but could they represent an accretionary prism? When a subduction zone plunges downwards, the sediments lying on top of the oceanic slab may be scraped up against the continent in front, rather than destroyed. Jeremy Leggett from Imperial College London showed that it was possible to read the southern uplands in this fashion. He compared the Scottish rocks with those of the Makran in Pakistan, where more recent oceanic events had accomplished just the same kind of accretion as part of the construction of the Himalayan chain. In Scotland, the slices of graptolite-bearing shales and grits were piled up in slivers in exactly the way that might be expected. This meant, of course, that a subduction zone would have to lie to the south of the southern uplands, along the present line of the Solway Firth. When deep geophysics investigated this area, the shadow of a northward dipping line at depth provided just the evidence that was required. A fossil subduction zone. Southwards again, the Lake District had an Avalonian stamp from its Ordovician fossils. The main part of Iapetus, thus, must have disappeared along the Solway line that separated the southern uplands and the lakes and followed the familiar Caledonian northwest. Southeast trend, a short distance now, but the requiem for an ocean, the sliding and slipping of the Lake District rocks, which have recently been recognized by the officers of the Geological Survey of Great Britain, have echoes of the tumbling blocks on the other side of Lepidus at Cowhead. The highlands include the highly metamorphosed belt, toughened up by gneisses and granites. The geology still allows for respectable mountains, even though they are but shadows of their former greatness. It is clear that the original sediments that were variously baked and squeezed in the highlands, originally lay off Laurentia, since unmistakable remnants of that continent survive at the edge of the Midland Valley where younger rocks predominate, and in the southern uplands, the whole area divides into two highly metamorphosed Moyne rocks to the north and less maltreated Dalradian rocks. To the south and east, some of the highland rocks were folded into naps and have been mapped out by a generation of devoted field geologists. The Tay Nap and its ilk will be their permanent memorial. The general push of the structures was towards the northwest, just like the Moyne thrust itself. The history of the highlands is much more complex and extends over a longer period of time than that sketched out for the rest of the ancient mountain system. Still earlier phases of history conflate with the Caledonian continental crunch, and whilst radiometric dating has helped unscramble some of this complexity, disentanglement is still in progress. The Norwegian caledonides are also generally metamorphosed, as I learned many years ago on that coastal cruise. In the context of plate tectonic history, we can now begin to understand its great pile of naps. They had originated from the west where Lepidus lay, squeezed out during orogeny to accommodate closure between opposing continents rather than soft closure as in Newfoundland. Their direction of movement contrasts with the heave towards Laurentia that we have met to the south. Instead, the Norwegian naps were directed eastwards. I have mentioned that there is good evidence from fossils that the furthest traveled and highest naps in the pile had originated from the Laurentian side of Iapetus. This is explicable now that we know the closure story. Squeeze upon squeeze, propelled masses of rock from the center to the periphery, one after another. The most distant last. All that remains of the ocean itself are little pods of ophiolites entrained in some of the naps. They must have been like apple pits squeezed out from a cider mill. This part of the great chain still has an alpine feel to it today, which is appropriate to the geology. This short resume of the history of a whole mountain chain appears to have the neatness of a whodunit, at the conclusion of which all the loose ends are tied up and the perpetrator is unmasked. It seems almost a pity to introduce further complexity, but nature has a habit of never being quite as simple as you first thought. On reflection, it might seem rather surprising that any mountain system that spans a hemisphere could be simply described as the meeting of two massive slabs. It did, indeed, prove more complicated, though the core of Tuzo Wilson's intuition remained intact. The first complication concerned the ancient continents themselves. Further, work served only to confirm the integrity of Laurentia, but the eastern side of Lepidus was another matter. An area centered on the Baltic Sea comprises a number of countries on the present political map: Norway, Sweden, Finland, the eastern part of Russia, and the old states of Estonia, Latvia, and Lithuania. The ancient geology of this whole area ignored our man-made borders. The Ordovician rock succession is very uniform in character, so much so that it has been claimed that you can trace a single Ordovician stratum throughout much of the region. The whole of it was underlain by very similar and very ancient basement rocks, the Baltic Shield. Not surprisingly, perhaps, the name Baltica has been applied to this area as a whole. In the earlier part of the Ordovician, the same time as the strata on Bell Island were being laid, down much of Baltica was covered by a shallow sea. The legacy of this time is thin limestone beds full of fossils. My own favorites, trilobites, are common, but there are other shells, such as brachiopods, in equal abundance. The remarkable thing about them is that they resemble neither their contemporaries in Avalonia nor those in North America. They are their own thing entirely. The limestones, too, are peculiar, being of a kind typically laid down today in temperate rather than tropical latitudes. None of the trilobites. Remember Nesoritis? that were found in Avalonia were found in Baltica, yet we have seen that they were common all over Central and Southern Europe and Northern Africa. What can be going on? After all, with Baltica, continuing southwards into Southern Europe, there seems no reason why the same animals should not have thrived over the entire eastern seaboard of Lepidus. The answer was that there was a second ocean separating Avalonia from Baltica during the early Ordovician. Page 201. Robin Cox and I christened it Tornquist Sea in 1982 after a geologist who had recognized a tectonic line running across Europe more or less where we wanted our ocean to be located. The eastern seaboard of Lepidus was divided into a simple explanation of the differences between contemporary trilobites in the respective halves. Also, we knew that the Gondwana continent, with Avalon at its edge, was in cool waters, yet Baltica was at temperate latitudes. A physical separation provided a simple way of solving this conundrum. It took a while, but eventually paleomagnetic evidence came to support the existence of Tornquist Sea *, a buried mountain belt largely covered by younger rocks, runs through Europe along the line of Tornquist Sea. This line marked the trace of its closure, a closure that happened long before that of Lepidus. In a nutshell, a two-continent closure model had transformed to a three-continent model, more complexity still. It was soon realized that Avalonia, too, was more interesting than merely being a promontory extending from Gondwana. It broke away from the main Gondwana continent and traveled under its own steam, carried on the back of the appropriate plate, across the ancient oceans, rather in the manner of the volcanic arcs that had preceded it. Both fossils and paleomagnetic fixes support this interpretation. I have spent a substantial amount of British taxpayers' money employing expensive computer systems and a postdoctoral assistant, David Lees, in plotting the movement of this chunk of crust which, to recap, comprised England, Wales, Southern Ireland, and a slice of eastern Canada, including eastern Newfoundland. In the early part of the Ordovician, about 480 million years ago, Avalonia was close to Gondwana, hence those similar trilobites on Belle Island and in France and Morocco, our old friend Nezaritis included. Later on in the Ordovician, the similarity to Gondwana progressively declined, while the similarity to Baltica increased. Thus, Avalonia was moving across Tornquist Sea towards Baltica. As the Ordovician continued, it moved northwards. It may have had a soft docking with Baltica near the end of the Ordovician. Only then did the two, united together, proceed to complete the closing of Lepidus. Avalonia was understood to be a fossil example of what is now termed a microcontinent, a comparatively small piece of continental crust with an independent history. It may have had something of the proportions of the microcontinental island of Madagascar. If so, it was pretty substantial. After all, micro is only a relative term. It was certainly large enough to push up mountains. There is much evidence for Avalonia's journey preserved on the ground in Wales. The mountains of Snowdonia are rich in volcanic rocks. Avalonia's grandest peak and its wild bare landscape was once the site of eruption. After eruption, you can see the ancient ash flows as ribs in the hillside as you climb upwards. Rare ferns and Ice Age relic flowers cling on to their damp flanks. These are the remains of explosive ash falls, which prove that violent eruptions once darkened the same skies from which rain now plummets and trickles down your neck. Welsh volcanoes were the subject of classical studies by geologists like O. T. Jones and W. J. Pugh, who mapped their ancient shorelines and identified the sticky rock that had plugged the necks of the vents in the era before continental drift was accepted. With the hindsight of plate tectonics, it is clear that these were the kinds of explosive eruptions associated with subduction and modern chemical analyses on the Composition of the lavas confirmed this. Continental crust was mixed with basaltic magma of oceanic origin to give a characteristic mixed signature. There was, at least for a while, a southward dipping subduction zone under the Cambrian Mountains. The Welsh Basin, often called a geosyncline in the past because of its thick fill of sedimentary and volcanic rocks, was nothing more than the sag behind the series of Ordovician volcanoes that now command the heights around Cardigan Bay, deader than dodos snouting. Supreme among them, the story of our understanding of the face of the earth has been one of increased freedom of movement. First, there was a fixed world, immutable, except for flood, plague, and elemental mayhem, intended to demonstrate the power of the Almighty to point moral lessons for craven humanity. Time still had a human scale, for all that we knew our place in nature and the likelihood of personal obscurity. O time that cuts down all, and scarce leaves here memorial of any men that were. So the 17th century poet Robert Herrick described our obliteration. Later, the appreciation of the span of geological time rendered much egocentricity on behalf of our own species redundant. There was time enough to free the continents from their moorings. The Atlantic Ocean was allowed to open, to split apart Pangea. The earth moved. We were free to imagine vanished worlds and vanished lives. It was a romantic vision, but also disconcerting. So to lose our bearings on historical certainty. Next, it was discovered that Pangea itself was but a phase in Earth's history. The supercontinent provided no deeper reality. It, too, was only in passing. Nothing is permanent except change. The Atlantic Ocean opened, but now it was discovered that its predecessor had already closed long before, at the time when Lepidus had been destroyed. Even the continents bordering Lepidus were not those we recognize. Avalonia and Baltica were not obvious from the map of Europe and America. They could only be revealed by understanding the deeper geological reality. That reality still influences what crops can be grown and what towns can be built from local stone. It has outlasted the present configuration of continents. The geological unconscious cannot be denied, for it still guides the way we use the land and rules the plow. We are all enthralled to the underworld. There is yet one more final mechanism of freedom to introduce. Recall the long faults trending southwest and northeast, like the Great Glen Fault in Scotland or those bounding Hank Williams tectonic zones in Newfoundland. These are great fractures, cutting deep into the crust. They serve to chop the great range into segments. The individual segments often have their own features, unique rock successions not found in their neighbors. For example, it was soon realized that the faults bounding these segments might mark the site of extensive movement. Two adjacent segments may have originally been far from where they are found today if they had slid past one another over a long period of time. There is a precedent for this kind of movement on the Pacific coast of the Americas, the most familiar example being the San Andreas Fault in California, where one slab of crust is sliding past its neighbors. The units between major faults are known as terrains, or, where there is doubt about their original disposition, suspect terrains. The mountain belt came together as an accretion of terrains. Only when terrains were finally docked together would they share rocks with their neighbors, as a single blanket may be spread over sleeping partners. So now, there is not only ocean closure to contend with, not to mention microcontinents and oceanic islands, but also a patchwork of shuffling slices. As well, once the moorings had been untied, what a kaleidoscope of moving fragments had been shaken up. Forget everything you think you know, and you can remake the world. There are continuing arguments about the original location of major crustal slices. There are those who believe that Avalonia was originally situated off Western Africa in the Ordovician It was only brought to its present location by a later movement in the coletonides. For once, the fossils don't help very much because they are similar over the whole of that part of Gondwana. How can we prove Avalonia's previous position one way or the other? What is needed is a kind of geological fingerprint that matches the slice with its nearest neighbor at its starting gate. Current research is trying to identify such critical tests. One promising line of investigation is provided by zircon crystals. Zirconium silicate, is a very stable mineral that is a common minor component of granite. It is so tough that when the granite weathers away, the zircon remains behind to be washed down streams, eventually to reach the sea. Tiny crystals of zircon often finish up as a component of sandstones, 1 grain of zircon among 10,000 of common quartz. However, methods have been developed to rescue the precious crystals from the common herd. Zircons contain minute amounts of radioactive lead and thus contain a clock that gives the geological age of the formation of the crystal within its parent granite. Extraordinarily accurate measurements of minuscule amounts of lead isotopes, however, are needed to give reliable results. Sam Boring's laboratory at the Massachusetts Institute of Technology and Scott Sampson's at Syracuse University in New York are the most up-to-date centers of research in this area. I visited the Syracuse laboratory, and what most impressed me were the plastic bottles. These have to be cleaned continuously for more than 2 years to remove every last contaminating atom of lead. Everything is purified over and over. At the end of it all, they extract dates from within single zircon crystals, so small that they would fit onto the head of a pin, that are accurate to within 1,000,000 years, a margin of error that applies even with dates of up to 1 billion years, which is an astounding technical achievement. Of course, this means that geological dates in general have reached a new level of precision. We now know that the base of the Ordovician is 489 million years plus, or minus 500,000 years. But precise dates on zircons also have a use for terrain location. If Avalonia once lay off Africa, then it should have received sediments from that continent, including zircons. Dandruff shaken from the giant came to rest all around. It turns out that there is a close link in age between Avalonian zircons and those of the Precambrian orogenids that affected the African continent. These have a different age spread from those that happened in Brittany or Normandy, off which Avalonia now resides. The new evidence does suggest that Avalonia did indeed travel from off Africa to its present location. Will other evidence confirm its peripatetic history? We shall have to wait and see. Now let us look again at the whole world. The Appalachian Caledonian chain is a scar marking an ancient ocean, one that has disappeared. Pangaea evidently came together as a supercontinent from a collage of earlier, dispersed continents. The Ordovician world was more like our world than the Permian one of annealed land masses. It had scattered continents. Plate tectonics did not begin at the time of Pangaea. Rather, the slow stroll of continents around the globe has been continuous. The mechanics of the earth have not changed for a far, far longer time than the breakup of the last supercontinent. To be sure, this vision embraces more transformation than Charles Lyell would have ever contemplated, but the application of his principles to look at living fold belts and subduction zones to interpret fossil ones has only confirmed the vigor of his scientific method. The reasoning that began in the temple of Serapis rebuilt the world, and rebuilt it repeatedly. If we proceed logically, wherever there is an ancient scar of a fold belt running across the surface of the globe, we should expect evidence of a lost ocean of past subduction. There will be volcanic rocks on the ground, and the thick successions of sedimentary rocks associated with them will be of the type that would once have been termed geosynclines. An assiduous researcher might well discover ophiolites tucked somewhere into the former range. It is what an advertising executive would call a package. Some of these ancient fold belts are obvious. Any topographic map of Russia shows the Urals almost bisecting it, like a persistent ruck in a carpet. The mountains run from the Arctic island of Novaya Zemlya southwards, dividing the endless waste of the Siberian taiga and the steppes from the Russian platform in the west. This line marked the eastern edge of the ancient continent of Baltica, which was separated from its Siberian neighbor by another vanished ocean. When that ocean closed in the Devonian period, another component of the supercontinent Pangaea was assembled. The Siberian continent was already recognized as an important piece of the earth by Edward Seuss. He called it Angara. Some of the largest copper mines in the world are related to ophiolites along the line of closure between Angara and Baltica. Similarly, across the middle of China, there's a range called the Xinling Mountains. Geologists have come to see this line as demonstrating that the most uniform civilization in the world, that of the Han people, comprises two separate geological foundations, another ocean consumed. Other ancient fold belts are less obvious, although they have been recognized for a long time. The Variscan chain, what Edward Seuss called the Hersonides, we have briefly met before. The fold belt passes west to east, through Europe, from the rugged cliffs and intimate coves of Cornwall in the west of England all the way through Central Europe north of the Alps. Another vanished ocean, one that had once divided Europe until its closure in the Carboniferous. This one has a name, too, the Reich Ocean. For each one of these ancient oceans, I might have undertaken a geological traverse from one side to the other, as I did for Lepidus in Newfoundland. You have to visualize 1,000 geologists crawling over the ground, interpreting these ancient mountain chains in the light of plate tectonics, geophysicists probing ancient sutures with new equipment, trying to read the structure of the depths, geochemists looking at the distribution of rare elements. This is the research program that continues unabated today, whether pursued in the wooded hills of Central Europe or the treacherous marshes of the Arctic. As with the Appalachian story, every question answered spawns a dozen more that need to be investigated. There are arguments about terrains. There are disputes about timing. There are disagreements about the role of oceanic crust in generating volcanoes. But without the plate tectonic model, nobody would have known what questions to ask of the uncomplaining rocks. The course of some ancient oceans opened upon older lines of weakness, as we have seen in the case of the Atlantic Ocean. Time reopened old wounds. We can now see the earth as a crude mosaic, stitched together in various ways. Scars of past tectonic crises cross continents. Some ranges are shadows of their former grandeur. The Urals, for example, have an average height of only 1,000 to 1,300 meters. Other old fold belts still carry glaciers on their heights, although none approach the mighty splendor of the Himalayas, which are the consequence of the latest round of continental movements. But these great mountains, too, will be ground down in millions of years, where lighter continental crust has been thickened in orogenic piles as continents collide. The whole mass rises inevitably into the fierce realm of the leveling elements, ice and wind. The Himalayas, too, will one day be yet another seam upon the face of the old earth, another wrinkle added to testify to its character. New York is the quintessential city, glitteringly artificial. Manhattan is a shop window for capitalism. A city this vibrant and varied is a tribute to what my father would have called commerce, the growth of towers from trade, the vindication of the market. It seems as far removed from the geological underlay as it is possible to get. Nature is pushed into a few holes in the sidewalks Tough trees like ginkgos thrive around a few older houses and churches. But then, these trees have survived from the Jurassic and can face out a few fumes. When you emerge from the ranked stores and offices into Central Park, it is always a surprise. What is this undeveloped prime real estate doing here, in the midst of all this money and endeavor? A winding path or two will take you to where you can view through real trees the peaks and pinnacles of the city, as you might a mountain range from the plain. It does not diminish the sense of wonder a human diligence. Rather, it lends perspective. Then you notice the rocks. Cropping out in places under the trees are dark mounds of rock, emerging from the ground like some buried architecture of a former race, partly exhumed and then forgotten. New Yorkers might sit on a sloping slab of it to eat a sandwich in the sunshine without giving it a thought. The outcrop is as unremarked as a hot dog stand or a fire hydrant, just part of the scene. But look more closely and you will see it is shiny and slick and layered. The light may pick out the glint of mica. The rock is schist, a metamorphic rock produced in the fold belts that have been the subject of this chapter. That New York can be built so high and mighty is a consequence of its secure foundations on ancient rocks. It pays its dues to the geology. This is just a small part of one of those old seams that cross the earth, but the rocks prove that skyscrapers not of man's making once covered the same ground. These are Grenville rocks. We have met them once before in Newfoundland, where they formed the core of the Long Range Mountains. They are older by far than the Appalachian Caledonian history. They are the legacy of a still older phase of opening along the line of the Atlantic, another manifestation of the same scar 1,000 million years ago, deep within Precambrian time. The Grenville rocks make another belt, broadly following the western edge of the Appalachians, Otras Temps, Otras Mers. When these mountains formed, where New York now stands, there were no trilobites, no shellfish. The sea hosted algae and perhaps only the most distant ancestors of animals. Yet it seems that even then plates still moved and the earth still carried on its stately dance of splitting apart and reassembling. How far back can we go? Even here, right in the midst of the most artificial habitat on the planet, a place where every second counts, there are relics of a deeper time when millennia counted for nothing.